Good morning, everyone. We are live at the George Washington University with the opening moments of this year's, the 2025, Humans to the Moon and Mars. I'm Matt Kaplan of the Planetary Society, back once again with you for this live stream, this webcast from H2M2, as we call it now, since we have thrown our own satellite, the Moon, into the title. But we're still very much about Mars as well, and really, as you will probably hear across today and tomorrow, when we have a fantastic program lined up for you, we will be talking about exploration across the solar system and beyond. It's going to be my honor to moderate the very first panel that will be coming up this morning, talking about space science as a vital interest of the United States, in fact, of all of humanity. And boy, do we have an amazing lineup of four terrific scientists for you for that very first panel at 8:40. But before that, we're going to be opening up with a welcome from the president of Explore Mars, J.R. Edwards, and the CEO and founder of Explore Mars, Chris Carberry. I don't think we're quite ready to go to them yet. So let me tell you a little bit more about other things that we'll be looking forward to just this morning. After my panel, there'll be a special video message from Democratic Senator Chris Van Hollen, who they're a little busy up on the Hill, I think, this week, but we know that we have a lot of your representatives and senators who are very interested in making sure that this country, the United States, continues to be a leader in space exploration and space science. Then, a panel that will take us to the Red Planet, led by Tariq Malik, Space.com editor-in-chief, and Jim Green, former NASA chief scientist, is part of that one. Jim is actually on the first two panels because he's on mine as well. Jim, of course, a longtime chief scientist of NASA, and much longer as the leader of the Planetary Science Division within NASA. That's just the morning. We'll take a little break, and as we have done for many years now, I'll probably come back here and talk to some of the major players that we'll be hearing from across H2M2. That'll happen during breaks, and we'll close out the day with one of those sessions later today as well. When we come back from our break, which will be at about 10:40 a.m. Eastern Daylight Time, we're going to hear from Humphrey Price, NASA JPL, Caltech. He is a longtime head of the Robotic Mars Exploration Program at JPL, chief engineer for that program. And then it really just goes right on from there into lunch, which will be taking place at 1 o'clock Eastern Time, but we'll be back after that. And then again tomorrow, as I said, with a very full program for you, real science and space exploration all-stars. We'll talk about some of those next time I visit with you from up here, but I'm going to go get ready for my panel and throw things now to Chris Carberry and J.R. Edwards.
Thank you, Matt. Is the microphone? Yeah, now it's on. Thank you, Matt. And welcome to the Humans to Moon and Mars Summit. As you realize, you probably noticed, we added the word moon to it. We've always had lunar programming. People didn't believe us, so we finally decided to put the moon into the title of the conference. So welcome. Glad you were able to get here with all of the rain. Before we bring on J.R. Edwards, our president, I'd like to first go through a little bit of logistics and thank our sponsors. So 1 second, let me just bring up the sponsors here. So thank you to our gold sponsor, Aerojet Rocketdyne and L3Harris Company. Our bronze sponsors, Collins Aerospace and Draper Labs. Our science sponsor, AIP, the American Institute of Physics. The venue partner here at JW, Space Policy Institute. Our streaming partner, the National Institute of Aerospace, who are obviously webcasting this event. Our reception tonight is being sponsored by Wassel and Wassel, or West. I apologize if I'm mispronouncing it. The law firm here in D.C. And tomorrow night's reception is Victoria Government of Australia sponsoring it. Our supporter sponsors, MDA. Advocate sponsors are Redwire and Honeybee Robotics. Media sponsor, Space.com. Our whiskey sponsor for tonight is Ardbeg, and tomorrow night's reception, our wine sponsor is Olson Wine. And so speaking of receptions, there are still seats available. So if you want to come to tonight's whiskey tasting reception, the 10th year we've partnered with Ardbeg, so you don't want to miss it. It'll also be the signing ceremony for the Washington Compact. And if any of your organizations might want to sign the Washington Compact, there'll be a number of representatives from the Hague Institute of Global Justice who run that document. So please let us know. But once again, please sign up for the reception tonight. It'll be terrific. As you might also know, we are selling, we're going to have a couple book signings. Most notably, Jim Green, with this extremely heavy book here, has this new book that he did with multiple co-authors called Mars. It has wonderful images from NASA, these images from Mars from over the years. I highly recommend it. I will also be signing myself my new book, The Music of Space, as well as the old one, Alcohol in Space. Incidentally, Alcohol in Space has been made into a documentary. You can find it on Amazon Prime. And you can only, because of the rules here at GW, you can only purchase these on the registration site if you're going to get them signed here today or tomorrow. A couple other things. There is Wi-Fi. So just go to GW Guest when you're looking it up and just follow instructions. You have to create an account, and then they'll send you, a link to be able to sign on to the Wi-Fi. For any speakers in the audience, please come 20 minutes before your talk. Please come around back to the backstage. You can get backstage, you get back to the main lobby, go follow around all the way to the left. You'll see an Explore Mars sign there, and go through the double doors, and you'll get backstage, and they'll mic you up. A couple other things. Restrooms are downstairs, and let's see, anything else? No, I'm just going to skip over the rest, and we'll talk about that later. So without further ado, I want to bring on J.R. Edwards, the president of Explore Mars. Thanks, J.R.
On behalf of our distinguished board of advisors led by Jim Green, on behalf of our operating board, on behalf of the office of the organization, for those who are new to Explore Mars, welcome. For those who are returning, in the spirit of Jim, good to see you. We have been advancing conversations about Mars, about human and robotic exploration for many years. But as recent as this year's presidential inauguration, we, the community, became the conversation. The entire world heard our national leadership's bold vision and commitment. We are sprinting into our future. We are on accelerated paths to realizing our visions and fulfilling the greatest of our human potential. Our work is not only bringing us closer to the goals, we are also improving life here on Earth through a dizzying pace of technological achievements and scientific discoveries along the journey. While we navigate the nuanced conversations around which can at times be charged and quite sensitive about space security, global security, planetary protection, we envision a remarkably bright future. Over the course of the next 2 days, you will hear from leading voices who are charting those paths forward and doing the hard work daily, year over year. We celebrate and we amplify those voices, the visionaries, the founders, the scientists, the researchers, the engineers, the technicians, the government and business leaders, the investors, the international partners, and so many more. In this moment, we gather to celebrate the progress made, strengthen our resolve, and intensify our focus. Thank you for being here, and thank you for being part of this very important conversation. Now, before we proceed to our very first panel for the day, I am very honored to introduce our first speaker, who will provide very brief opening remarks. As we move forward to that panel, let's begin by celebrating our scientist, our brilliant nation scientist. You know, that mutualism, that symbiotic mutualism that exists, that has always existed between human exploration and science and robotics, it's core to the vision, and it benefits all of us. So I'm pleased to introduce Dr. Michael H. Moloney, CEO of the American Institute of Physics, AIP, also science partner to the summit. Michael will provide a few remarks. Dr. Moloney, as CEO of AIP, is the 9th to lead the organization. Since joining in early 2018, he has been leading a strategic transformation effort for the Institute in preparation of its centennial anniversary in 2031. Prior to joining AIP, Dr. Moloney was the Director for Space and Aeronautics at the U.S. National Academies of Sciences, Engineering, and Medicine. For more than 15 years at the academies, he was study director or senior staff on about 100 reports on space science, engineering, and technology, aeronautics, material sciences, engineering, and physics, and astronomy, and more. When I talked about those brilliant voices we're going to hear from throughout the summit, we're going to get started in a very nice way here. So Dr. Moloney, welcome to the summit, and thank you again so much for joining us.
Thank you, JR. Thank you for that introduction, very kind, and also thanks for your leadership at Explore Mars and also your volunteer work for AIP. And good morning, everybody. It's a cold, chilly morning out there, but we'll try and warm up this morning. And I want to thank Explore Mars in particular for convening this very important summit. AIP is honored to be a supporter and a sponsor for this important event and the dialogue that will ensue today and tomorrow. And why are we a sponsor of this event, you might ask? And the answer is pretty straightforward. We are convinced that our collective journey to the moon, Mars, and while not with humans, to the rest of our solar system and now beyond, is among humanity's most audacious and inspiring endeavors. We also know that our nation's global technical leadership in exploration and other research areas is a direct result of our great American research strategy that has been so successful over the last 70 years. Exploration is a venture grounded not just in engineering and technology, but also in the deep and evolving pursuit of knowledge through science. As humans, we strive not to just journey beyond our planet, but to explore and peer back toward the furthest reaches of our universe, back even towards the beginning of time itself. This is quintessentially both a human and an American imperative. This morning, it's an honor to represent AIP and to join such an esteemed space and exploration leadership in this hall, especially the panelists on the stage that will be coming up shortly. That includes my friend and colleague, Dr. John Mather, who's also a trustee for AIP Foundation. At AIP, we see space science not just a national interest, but in our national interest, and a profound expression of our shared curiosity and capacity for discovery. It's a great example of our nation's frontier spirit, and we try to play a unique and unifying role in the scientific ecosystem by bringing together over 30 member organizations representing hundreds of thousands of scientists, engineers, and other STEM professionals. We try to act to provide content and context and connection across that community of organizations. We advocate for science that serves humanity, and we know that from Earth's surface to low Earth orbit and beyond into deep space, the insights of the physical sciences inform national security, technological innovation, environmental resilience, economic prosperity, and the bold pursuit of interplanetary exploration. This motivates us while we engage in our work. We also know at AIP that the science and engineering community needs, and we try to provide it, unbiased and reliable policy reporting while they engage in their work, something that's very important in a very active environment currently. We strive to develop the next generation of scientists and engineers and thinkers who will carry forward the mantle of exploration. And we're committed with our flagship program, Team Up Together, to removing and dismantling systemic barriers that we know from our data students face as they try to pursue their education. And some of those students that we've been supporting will be in the audience today. We gather authoritative data on workforce trends across our sciences. We capture space science history as it's happening through oral histories, archival collections, and the support of scholarship. I'm thrilled to see the discussion of space science kick off this conference today, particularly at the moment in time when, as a nation, we're faced with key challenges and opportunities about how we maintain the pace of humanity's reaching for the stars while being thoughtful as a nation to live within our means. It's a critical challenge we need to meet head on, especially as there are policy and budget proposals circulating currently that I personally fear may cause us as a country to lose our secret sauce, our competitive advantage over other nations, by abandoning the decades-long balancing of efforts to extend humanity's presence beyond the atmosphere of our planet by means of space vehicles that both include a human heartbeat on board and those that do not. The history archives preserve a record of when, as a nation, we've been faced with what I believe is the false choice between our nation's space science and human exploration programs. In an oral history, the former NASA administrator, James Webb, recalls a time when presidents seeking budget cuts at our space program. In his oral history, he said, quote, "Yes, he, President Johnson, and Kennedy both would raise the question, why don't you stop these other things and finish the lunar thing to which we're politically committed? And my answer was always, it's too important, and so far as I'm concerned, I'm not going to run a program that's just a one-shot program." Webb recounts in his oral history that he always argued for what he termed, quote, "a balanced program that does the job for the country that I think has got to be done under the policies of the 1958 Act," referring to NASA's founding documents. I share Administrator Webb's perspective and view, and I'm convinced that after working with every part of NASA for most of the last 20 years, the success of our journey to the Moon and Mars requires a vibrant space science program, in addition to vibrant, sustainable human exploration, aeronautical and space technology efforts at NASA. I'm confident this meeting's discussions will lead all here to be convinced that we must continue to invest, not divest, in the whole space enterprise. Our global competitors and allies understand this imperative. Exploration at its core is both a human and a scientific act. At AIP, we believe in this vision of holistic space exploration and in the power of the physical sciences and engineering to shape a better world here on Earth and expand what is possible beyond the confines of this planet. We're honored to support the space science enterprise as it continues to shape humanity's future, and we're honored to support this meeting. Thank you for the opportunity to get the meeting open today. It's now my pleasure to hand over to the panel's moderator, Matt Kaplan, and Matt is the Senior Communications Advisor at the Planetary Society. He was the host of Planetary Radio for many years, and he'll moderate the first session and conversation. Matt, over to you, and thank you again for the opportunity to speak with you today.
Thank you, Michael. Thank you so much for those wonderful opening remarks. We're now moving to our very first panel. The panel will be moderated by Matt Kaplan, a Senior Communications Advisor and former host of Planetary Radio, the Planetary Society. Matt Kaplan loves hosting and producing Planetary Radio. He was just 17, I understand, when he got his first job in broadcasting. So, Matt, we thank you for all that you've done over the years for Explore Mars and sharing this good news with the entire community. Over to you.
Thank you. And good morning. Hello, everyone. I should add that while I started the show and hosted Planetary Radio for 20 years, it is now hosted by my absolutely fantastic colleague, Sarah Alamed, who is my choice, even though she had to beat out 300 people to take over the show, and she's doing an outstanding job. I'm now the what do they call me? Senior Communications Advisor for the Planetary Society. I've been saying, be still my heart because of this panel. And I will introduce them one at a time. Each of them will have a brief presentation to make to you. But just to open things up, how many of you have seen the 1950s movie, The Conquest of Space. It's a classic. It was based on the Willy Ley and Chesley Bonestell book of the same name, The Conquest of Space. I've been thinking a lot about what a comically over-the-top phrase that is, but to attempt to understand the cosmos, to answer those two great questions, where do we come from and are we alone, which we'll be hearing about a lot today. Is there a greater quest than that, or is there one with a better return on investment? Yet every few years, our leaders lose sight of the value of science and exploration, and it would seem that we have entered perhaps the greatest period of that challenge in our nation's history. And that's why I'm really so honored to help open this year's Humans to the Moon and Mars Summit and to welcome these four superb scientists. So as I said, we're going to go right down the line here, beginning with Jim Green, Dr. James Green, the former chief scientist of NASA, and for a lot longer before that, the leader of the Division of Planetary Sciences at the agency. Jim is co-author of the brand new, and I can tell you from personal experience, spectacularly beautiful book, Mars Photographs from the NASA Archives, which has just sold out its first printing, at least in the US. So hopefully there'll be more available soon. And he also chairs the Explore Mars Board of Advisors. Jim, help us get started.
Well, thank you very much, Matt. What I'd like to do is sort of set the context of why we need a scientist to be able to talk about what we do, get the knowledge out. And it's because of the federal funding that we receive that allows us to do these spectacular things. Well, the president has issued what was called the skinny budget. And in this particular budget, there is a mark for reductions, not only in earth science, but in the space sciences. And this reduction is quite large. It reduces Planetary by $3+ billion out of the $7.8 billion that it currently has. It's important to note that the science aspect of what NASA does is really less than 0.5% of the total discretionary budget that is given by the federal government. And the marvelous things that we do with this, we'll talk about, of course, by the wonderful panel that's here. So this is a graphic that gives us a really great overview as to what's in the skinny budget. Not a lot of direction, but some tough things to take. SMD will take a $3.4 billion decrease. That's 47% of the budget. And it's broken up in two pieces. One is the earth science piece, which is a reduction of $1.2 billion. With direction on cutting back or eliminating funding for lower priority climate missions. In the space science part of the budget, space science should be thought of as those four divisions. That's astrophysics, heliophysics, planetary science, and the biological and physical science division. That has a reduction of $2.3 billion. With direction on canceling Mars sample return. Now, what's in these budgets? As a division director, I can tell you we bin things in certain categories that make a lot of sense. There's mission elements. Now, the mission elements, there are several. One is a strategic mission for which the division is responsible for. These are large missions, typically above $1 billion or even higher. These strategic missions then push the limits of technology, are designed to really step out and make some spectacular discoveries, and they all do. They've been all tremendously successful. Right now, the strategic missions that are being considered were Mars Sample Return, Nancy Grace Roman Space Telescope. Landsat and its follow-ons would also be called strategic. Those are designed at the division level and promoted. Then there's a series of competed missions, allowing the community to go after some really well-focused science objectives that are delineated in the decadals. Now, once you have missions up, and SMD has probably at least 100 operating spacecraft in the solar system, orbiting the Earth too. These operating missions you have to be able to fund. You know, they're in the process of being in their prime mission or their extended missions for which they're going after new and important science objectives. Those are important. And then, of course, there's a variety of instruments on other agency spacecraft. And this allows our scientists to connect with our international partners. So NASA as a mission agency has these kind of opportunities associated with it. Now, when the data comes in, flows into the archive, then other scientists that aren't directly associated with the mission can propose to do increased analysis, and that has just been an enormous boon. For instance, today, more science papers are coming out of the Hubble archive than are coming out in the prime mission, where you get time on the telescope, make your observation, write your paper. So these long-term archives are incredibly important. That feeds into the research analysis portion of the budget, and that's about 10 to 25% of a division's budget. Then there's national needs, looking for NEOs, okay? This is very important in terms of knowing what's out there, what are the potential impacts, and do everything from civil defense to even testing things like moving a NEO, which is done recently with the DART mission. And of course, there's other things in that area which include cooperation with NOAA and also facilities that you have to fund. And then finally, there's a technology part of the budget. This is for instruments, this is for unique spacecraft capabilities that the division needs, such as radioisotope power for missions going to the outer planets and beyond, out into the interstellar medium. Now, the management principle NASA uses has to be understood in terms of how do you take a cut that's so large, how do you look at that portfolio and decide what are you going to cut, what are you going to keep, and each of the divisions really work hard to create a balance. Now there's a certain approach associated with it. If you're going to start cutting missions that haven't been launched yet, the basic principle that we talked about a lot at NASA headquarters is first in, is the next mission you have to cut. So this really hurts those missions that are in the development phase if they're not going to make it. And in planetary science in particular, that's incredibly difficult because we have windows we have to meet. And if you delay a mission, sometimes you then can't do the mission at all. So there are large portions of the budget that will have to be taken with these kind of rules in mind, and everyone looks at the decadals. So these are the decadals, and in these decadals there are some decision rules, and they're all pretty consistent. You know, here's an example of decision rules, and in this set you see you cut out the strategic missions or delay them. You reduce your competed missions. Those will be the ones that are currently in the process of being developed. And then you delay your competitions. And typically at the very end is research and analysis because you have your community you have to support. And so this is also true in all the other decadals. There are certain associated rules for which saving the RNA program and keeping the community intact is the best approach. So in conclusion, there's going to be no new starts in strategic missions. That won't be possible. You know, this is why Mars Sample Return, which would be that next big strategic mission, has been canceled. They're going to be canceling some competed missions. Last in, the last one you decided will be the first one out. You delay all newly competed missions because you don't have the money to fund them, even if you can make a selection. And then you have to somehow figure out how to shrink the national needs. So that has to be folded into this priority. So for the divisions, you've got operating costs like the operating missions. You want to be able to support as much of the community as you can through R&A. But the cuts are so deep, half the budget, that even reductions in those areas will be expected. So that makes it a very difficult environment that we're moving into. And so with that, what's happening with our science?
So we will hear more specifically about science, beginning with our other Jim G, James Garvin, Chief Scientist for the Goddard Spaceflight Center. Also had that title for 4 years at headquarters, right, as the Chief Scientist for the Mars Science Program. It's largely due to you, I think, Jim, that we know exactly how tall Mount Olympus is and how deep the Mariner Valley are, thanks to that MOLA laser altimeter. Within what, a few centimeters?
Oh, less than a meter.
Yeah, it'll do, I suppose. Jim, take us to the red planet.
Well, thanks, Matt and Jim, for setting me up. I'd like to look through the lens of the universe of science Jim was talking about, through the ways it's been funded by leaders like him, and focus on Mars, because we're really in a very special moment right now. We're looking at 50 years since we first had the audacity to ask, are we alone, through what we could read in the record of Mars, before we had ever landed on any other world robotically other than the moon. And we did that literally 50 years ago with Project Viking, and learned a lot in the intersection of the science we choose to do, but also the engineering masterpieces that allow us to do that. And that's the legacy that lives on in all these programs that you heard from Jim. So let me just remind you what we did. We went to Mars 50 years ago with our eyes wide open in the possibilities of a very Terra-centric world. And that red Mars we see is not the Mars under a veneer of dust, as you'll hear later. We also saw cycles of what I would call the Mars meteorological system and the climate that we didn't even know were existent. There's the frosty Mars. It happened on a Halloween, maybe. Not really. But at Viking 2, we saw this exchange of volatiles in Mars, and we realized the Mars atmosphere does amazing things every year. And so Project Viking emplaced our engineering and technology power onto Mars to open that frontier. And maybe we didn't know what we'd find, but we discovered the engineering boundary conditions to give us, I would say, the boldness to go after new things. And that set in motion a new Mars exploration program about 15 years later that culminated in many things. I only have a minute or two to talk, but I wanted to remind you, science comes in different flavors. Sometimes the science we measure, and in this case, the topography of the planet Mars in a geodetic framework good to a meter everywhere, gives us enabling powers. Before we had the mission of the Mars Orbiting Laser Altimeter, the knowledge of where to land on Mars, I always use the analogy of landing on a carrier deck with uncertainty at the level of 1,000 feet. I'm sure the great air flyers, the naval pilots, would probably not like to know that about the deck position on landing on a great carrier. But that was where we were before MOLA gave us Mars in 3D at the level where we could see the whole planet, figure out aspects of its interior, and also see magical things like the crater Korolev, seen there with a central mound of ice that rises above the rim of the crater. How does that happen? And these are some of the magical discoveries that a new technology that many said should not be done gave us the ability to see new things about our world that we've now been visiting and landing on successfully ever since that mission. We've also put in place the ability to do the recon for the future. And this is really important because the science questions require context. And you saw that in the workings of what Jim showed. And so we put in place, when we restructured Mars in around 2000, the idea that we would measure everything we could at all the scales that matter, including those that would enable sample return and humans, crew, women and men going to Mars. And so the Mars Reconnaissance Orbiter, now 20 years in its life in space, has done many great things. I can't possibly describe the voluminous papers that have been done, but one thing it did was it mapped every square inch of Mars on a 6-meter digital image framework. That, for the price of literally a small B movie, gave us the ability to put what we do on Mars today into the context of landing safely, driving where we want to go for all of Mars. So now the trade space of where we can go is open to the eyes of where we want to go, thanks to that mission and also the higher resolution data sets. So the Mars Reconnaissance Orbiter is an example of producing science in the context of the engineering boundary conditions to let us go to Jezero Crater, Gale Crater, to imagine climbing Olympus Mons with those giant escarpments that are a harbinger of how Mars worked. So this is just part of the legacy of the program. So 50 years in, we've come a long way. And yes, the rocks of Mars seem to be staring at us with their glasses. They're in a view from Curiosity. But some of the discoveries, and you're going to hear about those from Jen and Danny in the next session, are really transforming how we look at the planet. Not from just, let's see what we get, but to not just following the water, but following the organics as indicators of what it might be like to be there, work there, live there, and return stuff from there. And that connects Mars deeper than just a one silicate rocky planet with a small atmosphere and a changing climate to the bigger cosmos that you'll hear about from John. So let me just remind you then the legacies we have. Petabytes of data that describe the planet from all the scales, covers of literally hundreds of prestigious journals that declare that science in the publication record and in other ways. These are just a sampler of some of my favorites. Please, there's many, many more by many other journals. But it just shows you the diversity of thinking in the science we've had in this Mars program. From organics to seeing fossil river deltas, to understanding the sapping that could occur on hillsides, to Mars in 3D. And so I leave you with a couple thoughts. I know my time is quick. One thing is, we know Mars is a dust world. Critical to its current evolution is its meteorology, if you will. And we see the dust storms on Earth, beautifully seen here from the International Space Station. The Mars dust space is still the nano-Mars we don't know. That'll be a key ingredient to looking to go there ourselves, to living and working there. And I'm reminded of this great little artist piece for Dust on Mars that just reminds us how even the artists have captured that unknown in this fabric and this quilt work. So I'll leave you with a couple thoughts. I think of Mars as we leave our planet and go back to the moon with Artemis as that doorway we will leap from. From that era, set up by these robotic missions we've been talking about, into a new era where Mars will connect beyond just going there ourselves, but through doorways to the bigger beyond. And I'd like to just show you a friend I brought with me. So here is 600 grams of Mars. The beauty of our program in science and engineering is to know that this is from Mars. From experiments that flew on Viking and Curiosity that are still working, to know that we have this artifact of another world delivered not by humanity, but by Mother Nature, is part of the magic of the exploration we do to know that. This is probably more valuable than some of the, the great gems we like to wear ourselves, because it tells us about a history of another world. And our goals in Mars are to understand this and understand what we, with high level of informing, wanted to bring back. So Mars rocks, we're still there with those missions, those continuing missions, and we want to go back ourselves and with robotic emissaries to figure out what Mars still has left to tell us. So thank you, and let me turn it to Britney.
Thank you, Jim. Well done. I'll tell you my story later about Allen Hill's 84001 that I got to hold a little fragment of with tweezers and gloves. We're going to continue on out across the solar system now. If you ever have trouble reaching Dr. Britney Schmidt, it might be because she's a few thousand kilometers from the nearest cell tower. She's an associate professor in both the Astronomy and Earth and Atmospheric Sciences departments at Cornell University. Home campus, of course, of our founder, Carl Sagan, at the Planetary Society. Brittany, how many seasons have you spent now at either the top or bottom of our planet?
9 in the Antarctic and 4 in the Arctic, so just a few.
And why does she do this? Well, in part because it's her lab that has built and deploys IceFin, a robotic submersible whose descendants, I certainly hope, will one day descend down into the warm sub-ice oceans on worlds like Enceladus and Europa. I'm also very proud to say that she chairs the Space Policy and Advocacy Committee for the Planetary Society's Board of Directors. Brittany, it's all yours.
Thanks. It's a really an honor to be here today to talk to you about the solar system beyond Mars and its connection to the exploration of the Moon and Mars. So in these pictures I'm showing here are just some of the work that we've done. But we just represent only a couple of the programs that have been funded primarily through NASA's RNA programs, research and analysis. So in this particular slide, I'm showing you examples of science and technology that's co-funded. So programs through the astrobiology program that allow us to co-develop technology and deploy it here on Earth to test that technology and to get better science done by embedding engineers and scientists in the process. And that's exactly what we do here. So shown in these pictures here are our robot IceFin, which Matt just introduced, which is a technology development platform for future missions, hopefully to Europa. And while it was built by funds from NASA and universities, it actually has turned into being a big climate explorer for our own planet, participating in National Science Foundation research as well as international campaigns. So that's on the left side. So those are a few of the IceFin expeditions, and some of the space missions that we've been able to inspire using our now understanding of how to explore the Earth, particularly in this rare place, hard to get to place underneath the ice. On the right-hand side is examples of, it turns out I actually do some Martian research, but it's also here in our backyard. And so this is Pingo Star, which is my favorite acronym ever. But it's an exploration of the Earth's permafrost using technologies that might be applicable to future human exploration. So here we're dragging things like ice-penetrating radars and resistivity mappers to search for ground ice in the poles of our own planet. So it's helping us to understand how these processes work here for the very first time, as well as proving technology. And as I mentioned, all of this isn't funded through a flagship mission. It's funded through NASA research and analysis grants, and often through logistics through National Science Foundation. So last year, I had the opportunity to sit and watch something I've worked on since I was a graduate student launch to space. So this is Europa Clipper, which is the work of tens of thousands of scientists across the United States at universities, as well as NASA centers. Europa Clipper launched in October and will finally arrive into Jupiter orbit in April of 2030, and then move on to a multi-year tour of the Jupiter system. It was a really cool experience. It's our next big flagship mission, and the first one ever dedicated to the exploration of an ocean world. And one of the most important, unfortunately, this background doesn't show the text that I had, because my background was black, but what I was showing was that the ice-penetrating radars that have been sent to Mars and are now on its way to Europa were built here first and tested in Antarctica in order to study the Earth's climate. So what does this look like? So we've got these beautiful places, Greenland and Antarctica, and if you're less familiar with some of the research that's done there besides the Earth's climate, there's actually a ton of Mars research done there in the Antarctic dry valleys, which is one of the closest environments on our planet to that of Mars. How that really works is that the National Science Foundation actually funds both science and logistics that go to Greenland and to Antarctica to do the science there. They fund all of our presence in Antarctica, and most of the science presence in Greenland as well. NASA also has interest in that because we want to go to places like Europa and to Mars and to understand these environments. So NASA funds RNA programs, which you also can't see here. So this is P-STAR, Solar System Workings, Exobiology, Mars Fundamental Research. Those programs have funding that goes to the scientists. Then there's a co-funding and a logistical support that goes towards that work being done in Greenland and Antarctica. And so indeed, the interplay of these agencies also really matters in the fabric of science and in turn, the fabric of Mars exploration. In fact, most of the astronauts these days have been to Antarctica, or many of them. It's considered one of the great training grounds to work in these extreme environments. And so there's a whole bunch of interactions between these agencies that you might not be thinking about when you think of NASA and space exploration and humans going on to space. I want to highlight here that the National Science Foundation is also under extreme duress. This is just this year. This is before the budget cuts that we expect to come down, which are even more massive than those that NASA's facing. NASA's facing 24% top line. The NSF is facing at least 49%. We don't have the details on that. But I'm showing here this recent article from the New York Times that shows that the Office of Polar Programs has already spent only 22% of what it would spend in an average year this year. So that's before this budget cut. We've already cut science and logistics in Antarctica by 88%. What does that look like? Here's what we did when we wanted to go to the moon. We put a whole bunch of money into it. right? And that trickled down. That actually did work, right? We funded all science because it's all interconnected, because all of these technologies and all of these innovative minds are the ones that will eventually bring us the technologies that we need. That's the backbone of our economy, the backbone of innovation in the United States, and a lot of it was born from the Apollo program. That's what we propose to do there. Here we want to go to the moon, and now we want to go to Mars, an even grander challenge, and we're going to do it by cutting the budget. That should work out well. And here's the biggest lesson here is that the public supports this. So this is a recent Pew study that shows what people think NASA should be doing. At the top of that is monitoring asteroids to protect our own planet, monitoring parts of the Earth's climate system, and conducting basic scientific research. These are on the hit list during this budgetary crisis. So while we're hearing a lot about how we're going to direct science and engineering funding towards the moon and Mars, I just wanted to give you a picture of how we got to the moon and Mars in the first place and how we might think about doing that if we can get back to a budget reality that makes some kind of sense. Thanks.
Thank you, Britney. All right, we're going to head even further out into the cosmos now by hearing from John Mather. He was named MVP when he shared the Nobel Prize for Physics in 2006, thanks to his Cosmic Background Explorer spacecraft and what it revealed about the bath of microwave radiation that we all live in that is the remnant of our universe's birth. John was also the senior project scientist for the James Webb Space Telescope from 1995 until just a couple of years ago, so, no big deal. John still serves as a senior astrophysicist at NASA Goddard. John?
Well, okay, thank you. I'm glad you're all here to think with us about what can we do and what may come next. I want to show you some stories about what we've already been able to do and what we're thinking about. So here is a picture of the great James Webb Space Telescope. The background in the picture has changed a little bit, but you see the great golden hexagon. It's 6.5 meters, about 21 feet across, and we did that. It's an international partnership between NASA, Europe, and Canada, and we did that. About 20,000 people it took to do that. So one of the most amazing collaborations that I can possibly imagine participating in, and I got the privilege of speaking about the science to all of you for a long time. So thank you to the public who supported this. It's one of our biggest science projects ever, and it's been massively successful. I won't be able to show you all that many of our results, but I want to tell you a few of them as we go along. So why do we do all these things? Well, where do we come from? It was already mentioned before. Well, astronomers have been working on this, and it's not only how do we study the Earth, but how do we get to where did the Earth come from? Where did the sun come from? And here's the next question is, what do we, who are we? Well, that's not really my question to answer. Maybe philosophers will be able to answer that better. But we can, as astronomers, work on what is the cosmic history. We know about the expanding universe, which is mislabeled the Big Bang. And we've been working out a lot of the details of it, and we still haven't got it quite figured out because there's more to do. Biggest question that I've had, and I think many of us have had since childhood, was, are we alone? As Fermi asked, well, where are they? And why haven't they been visiting? So, well, some people think they have. But at any rate, astronomers can work on the evidence, and we're trying to figure that out. We have been able to locate thousands and thousands of planets around other stars, and I'll show you a little bit about how we do that. And we're learning something about them. So far, no other solar system just like ours has been turned up, but maybe they're there and we just can't tell yet. Is life a miracle? Well, people used to think so. And now we're beginning to make a little bit of progress on the chemistry and the possibility of how it might have actually occurred here on Earth. Now, Darwin suggested maybe it happened in a nice little warm pond. Well, maybe, maybe not, but anyway, that's an idea. And people are working out the chemistry of how it might have happened. Well, how far can we go? Well, so far we've only thought of chemical engines that we can imagine and solar electric propulsion, maybe the nuclear electric propulsion. And that cannot actually get us very far even in the solar system. It's a pretty big place we live in. So we put the Webb telescope 1.5 million kilometers away, which is only 0.01 of the distance to the sun. It's Seems like a long distance to send a signal than to do astronomy, but it's the right place to go. Mars is a whole lot further away, and the rest of the planets are farther than that. So you could imagine traveling to the rest of the solar system, and we certainly are going to think about how. So far we're sending robots. We've sent robots everywhere. We could, if we really, really tried, go farther than Mars. But that's hard, and it's pretty dangerous, as the way we would do it today. So now I want to talk to you about this discovery of the early universe. So this is a map that got a Nobel Prize for us. When we heard about the expanding universe in 1929 from Edwin Hubble's graph that showed the rate of expansion, the distant galaxies running away from us, it took a little while to get to the calculation that said in 1948, right here in this university, that there should be cosmic microwave radiation left over from those early times, and we ought to be able to see it. Well, in those days, it was too hard to do. Nobody went to look. In 1965, it was discovered by accident. People were working on the space program and trying to start up telecommunications by bouncing signals off of satellites. So that was at Bell Telephone Labs, and they said, well, no, there's a little extra noise in our receiver. What is it? And it turned out to be this. So now we have a map that shows the sky is not equally bright in all directions, but actually has hot and cold spots, which relate to the conditions in the very early universe. When Stephen Hawking saw this chart, he said that was the most important scientific discovery of the century, if not of all time. Thank you, Steve. So why is it important? It tells us the initial conditions, as near as we can get to what is the universe like when it was very young. And if you could figure that out, you could say, well, in that case, we ought to be able to predict more or less what happened after that. How did the galaxies grow? How did the black holes grow? How did stars grow in the galaxies? Maybe how do planets grow from the stars and the debris of stars? All those things that we tell you the story of our solar system should somehow connect to this picture. So working out our cosmic history, our personal history, this is part of it. Where did we come from? Where did Jim and I come from? Started there, and let's work out the story. So, by the way, astronomers do something that we can only do. We can visit the moon, we can visit Mars, we can pick up the rocks. We can pick up pieces of the solar system from farther out. Occasionally, we get lucky, find a chunk on the ground, or even send a probe to get it. Astronomers can travel everywhere, but we can only do it with pictures and imagination. So here's your imagination required to go from that picture to us being here. So what did we see with the Webb telescope? This is one example. That little red fuzzy ball in the upper right corner of this picture is the farthest back in time that we've been able to see. This is a little galaxy. We see it as it was when the universe was only 290 million years old. Tiny fraction of the total age, which is 13.8 billion. So looking almost as far back as we can hope to see the very first things that turned on after the Big Bang. So there it is. We're working on what it is. So we're pretty sure it is a galaxy, and it is not like what we thought it would be, which is one of the cool things about discovery. You build some equipment, you hope to find something, you get a surprise, and oh my gosh, that's not what we thought we would see. I'm glad we built the equipment. We would never have found out without it. And by the way, you cannot make any of this kind of progress without building the equipment, doing the missions that Jim mentioned in the introductions here. Have to build stuff to discover stuff. So there is, as far back as you can see in time, so far. There may be a few more, a little farther back in time, and who knows what surprises may still turn up. We've only been running the observatory scientifically for almost 3 years now. We turned it on in June of 2022. Okay, so beginning of the science of the very first objects. We're looking at these objects. This is a place called we call it the Pillars of Creation. Because it's a pretty picture. It's actually a place where stars are being born today, inside that cloud of dust and gas. There's a wind blowing from the top right down to the lower left, and you can see how it's ripping shreds into that cloud. There are a few places where you can see stars right on the leading points of the cloud that are just their formation has been triggered in that cloud. Well, why are stars born in clouds of dust? Because gravity has to overcome the gas pressure in order to pull something in. So how do you make the gas pressure go down? Keep the object cold. So the dust makes this possible for new stars to be born there. By the way, there was no dust in the early universe, so the first generations of stars, the first galaxy that I showed you, was formed in a completely different way. So we do not know how that was yet. We're working that out. It's one of the joys of discovery and the stories to tell all of our public to share in our beauteous history of the universe. So there's part of it. Presumably, there are stars being born with planets like ours right in there. And here's an example closer up. This is a star that's in the process of being born. What you see is an edge-on view of the new solar system. Edge-on means there's a lot of dust orbiting in the plane of the orbits of all those future objects, planets that might be in there, where it says disk and dark lane, that's the future planets growing in there. The star is actually hidden from us. You can see that it's sending out jets of material north and south, up and down. And there's maybe even a spiral structure growing in there. We do not know really how this works, but we got a picture. So we are, of course, what do we do next? We turn on our imagination. We say, okay, I've got a computer program. I will simulate this, just like we simulate the weather here on the Earth. We simulate the formation of new stars with planets and dust and everything that's orbiting around them. So we're learning. We will be able to tell you sometime, a few more decades, maybe a little more certainly, how something like the solar system could form. Now, the solar system is unique as far as we know. That's interesting. So how do we know? Well, this picture didn't turn out quite so well as it was, but then how do we know about other planets? This is one technique that's very powerful for us. If you wait long enough and stare at enough stars, sometimes they'll blink because a planet goes in front of the star. And I even met a student who found one of these for his astronomy class homework. So it's not that impossible to do, but we've done it systematically. We've got thousands in the catalog. And what we especially do with the Webb is we know when it's going to happen. We point our telescope at it and we say, okay, how much light is going through the atmosphere of the planet on its way to our telescope. We spread that out with a spectrometer at the different colors, the different wavelengths, and do the chemistry on that information. And so we can now work out, are there planets out there that have atmospheres? And do they have chemicals in them that are interesting to us as possible signs of life? So yes, so far we've been able to analyze large planets, Jupiter-class, Neptune-class sizes. And they do have interesting chemistry. There was a big hoo-ha lately about a planet that has an unusual molecule called dimethyl sulfide. Some people said, well, that's a sign of life. Well, probably not. But it is formed here on Earth by living things. So that got everybody excited. But that planet is a hot planet. So very unlikely. It's got hydrogen and water and carbon dioxide and methane and things like that. Probably no surface under that. So not another home. Mars is possibly like home, which makes it super especially interesting. So let me just wrap up here and say there's much to find out. I'm really interested in the Mars program because it lets us find out the answers to things we could never do just by imagination. We could go pick up a rock like he has and say, I see that, I analyze it. Maybe we'll find one that has microbes in it. Maybe they're alive, maybe they're dead, but there's something. This is the first chance we really have to do that. So I'm hoping for the best.
Thank
Thanks.
you, John. I don't know about the rest of you, but I would just sit up here on the carpet at their feet and just listen. Because to me, just what we've heard, which is such a tiny fraction of what has been delivered by the dollars that this nation has put into space science and space exploration, seems to be worth it on its own, just for the sense of wonder that it generates. I mean, speaking for myself, I'm willing to put $2 or $3 a year into making sure this continues. I got a question, and by the way, because we got a little bit of a late start, I've been told we can take a couple of extra minutes here. I'm also almost embarrassed to ask because it's such a cliche question now, but we are in difficult times, budget-wise. USAID is gone. The Consumer Financial Protection Bureau is hanging by a thread. Medicaid, NASA's sister organization, NOAA, lots and lots of priorities. How do each of you answer people when you get that question that all of us get in this business? Why should we be spending money out there when we have so many problems here and so little money to take care of them? Jim?
Well, from my perspective, we're just becoming aware of life on Earth's fragility, in the sense that when we look back at our history, major changes have happened on Earth that have been climate change, have also been the fact that the Earth goes through a variety of different phases. For instance, there's near-Earth objects that we're now becoming aware of. Our orbit is not really a very good orbit. Turns out it's full of maybe 60,000 or more near-Earth objects, many which cross our orbit. They're going to hit us. It's not a matter of if, it's only a matter of when. And that realization only occurred when we really recognized features on Earth that were impacts, related that to what we now know about the moon, dominated by impacts, and therefore what's our history of going through mass extinctions. So all those things are related, and it's because of the orbit that we're in. In addition to that, as the sun moves around the galaxy, it's going through a variety of molecular clouds. This changes the heliosphere. Now, the heliosphere has been a wonderful protective globe around us, but there's perhaps a time when we've gone through molecular clouds for which that has shrunk to the point which has popped the Earth out into interstellar space, where we receive a major increase in cosmic rays. And so we're just becoming more and more aware of the history of the Earth and how it has survived and how it will have to survive into the future, with humans being the dominant species. So that awareness really comes from space. And then in addition to that, of course, we monitor the Earth from space. Satellites roll over countries, look at how much food is under cultivation, and can estimate, are you going to export or import food by the end of the year? So there's so many benefits by going into space. We've got to have it. Our future is there, or we won't survive.
Space science, science about Earth from space, enlightened self-interest. So let's get Neo Surveyor out there, which is, that's why the dinosaurs all died. They canceled their infrared satellite that was looking for those rocks. Jim Garvin.
Well, I was just going to say, Matt, first, it's a privilege to do what we've had the joy of doing. And really, that's a privilege the taxpaying public have given us. So, it's to be cherished. And so times change with investment strategies. We all have 401ks or whatever. It goes up and down. But I think for me, there's a couple of things that build on what Jim said. First, we live in space profoundly. And this universe is collisional at every single scale. We don't even know the energetics of the most recent impacts of asteroids in Earth history. We do not. Some of them we could be missing by an order of magnitude, which may have had more perturbations in the history of what we call life. So that's one thing. The other thing is, by doing what we've done for the last 60 plus years, we've established a situational awareness of our place in space. And that transcends everything we've done, whether it be Mars or the bigger universe, as John was saying, what Britney was saying. And that situational awareness gives us the ability to understand aspects of that destiny question that John was asking. And so whether we know everything, we know a lot. You looked at that picture of Olympus Mons. There's a 3-kilometer cliffside around this thing. What the heck? Well, it turns out a lot of ocean island volcanoes have the same thing. Go off the coast of Hawaii, just under the water, and there's a huge one. We didn't know that. But we went to Mars and we figured that out. And so sometimes by that situational awareness of comparison, however we use it, samples from the asteroid Bennu, things in deep space that John was talking about, how solar systems form, seeing solar systems in other states of habitability in time, because they haven't progressed to the state ours is in the places we think it had been habitable or is habitable, is a profound possibility. Those things will ensure our destiny. And the final thing I'll say is, we all like to run the numbers, okay? So if you run the numbers through the eyes of the brilliant economists at business schools, and you run them and you say, so what's the force multiplying value of 60 years of this investment? Just take the robotic investments. you can slice it and dice it in many different ways. But if you use just simple deep learning, looking at 60 years, you see the numbers are 4 to 5 to 1 for every invested dollar. And we can turn it around and make it other things. But those investments come in intangible ways and intangible ones. So we can now land where we want to land on Mars, good to a kilometer or less. Not the size of a basin on Mars, but that's going to enable those steps that we are so anxious to take to get humans there, to return samples, to look for extant life or not. Those things are enablers. And so this legacy of engineering and technology, I call it the T's, technology, engineering for applications of science for exploration. The big T's has worked. And by being leaders in that domain, we know more about where we live and how we live, and we know how to discover some of the things that you heard from John and others. So to me, that's fascinating. It's an investment that's to be cherished. I hope we can continue.
Not $1 has been spent in space, unless it was between a cosmonaut and an astronaut playing poker on the ISS.
That's true.
But Britney?
Yeah, I think there's kind of three things. We've talked a little bit about the finances, as it makes good financial sense, and we tend to think about it as that we do this now because we're so successful. I would argue that we have been so successful because we chose to make these investments when we made them. This is a backbone of our economy. Research and analysis, fundamental research in this country is responsible for like 10% of our GDP, even though it costs less than 1%. It's a huge return on investment. So if you just want to be self-motivated, you don't want to take the backbone out of the economy. But I think it's more than that, because we crawled out of the cave, right? That's the whole identity of humankind, is that we're motivated by curiosity. When you don't know what you're going to find, you won't know how to use it, but we figure out a way. And so those fundamental investments are really linked together in how we see ourselves and in where we see ourselves going. We have the chance to save ourselves. We talked about asteroid impacts, to go looking for the killer asteroid, but we also have a chance to see our own planet and to make changes that we need to make in order to save ourselves from a major disaster that's part of our technological advancement. But I think the other thing is that it's just inspiring, right? At the end of the day, I don't get up out of bed because I need to make a 9 o'clock meeting. It's the results that are coming from that, right? Not everyone who studies science ends up as a scientist, but they learn techniques. Many of my graduate school colleagues are bankers, are coders that are working on safety for humankind, that are working on health innovations. Innovations in looking and searching for life through astrobiology are related to discoveries in cancer and to medication. So these interconnected nature of science and discovery is who we are as people and is a part of us financially and as our motivation. So I think you can't really pull those things apart from each other, and they provide people kind of direction and an inspiration, right? That's a personal engine as well as an economic one.
John, anything to add?
Yeah, my perspective is what we do as scientists and as scientist engineers as part of our national science program has been the key to national prosperity. Senator Mikulski used to say it was always about jobs, and I still think so. When we decided as a nation that we were going to go to the moon, the first time, Jack Kennedy was really worried that it was going to bankrupt the country. Well, it made the country prosperous. So all the technology that we have today grew out of the immense investment that we put into the space program. The government's the customer that will pay whatever it takes to do the job. And in 8 years from the speech at Rice to landing on the moon, 8 years we did that. That was an immense investment. It cost us a lot and it gained us a lot. We gained us national prosperity and national security all at once with the space program. It wasn't a fundamental science research program, it was a huge engineering job, and we got them there, and they came home. And I'm so impressed that we did that. I think we should keep on doing that.
Hear, hear. I'll just throw one more at you, because I don't think we should go beyond about 5 minutes over. You're all so passionate about your work, your research, and why this is so important. And there are hundreds, thousands of other scientists who could also have been on this stage expressing the same feelings. What more should scientists themselves be doing to communicate this to the people who matter, which is the folks who vote and the people up the street here who decide what bills get passed and what budgets get approved?
Well, from my perspective, it's all about communicating the science. Science isn't done until you communicate it. Scientists have science meetings to communicate science that they're doing to others, and that spurs new ideas, new science. But going beyond that is absolutely critical. Talk to your neighbor, get them excited about what's happening. Go to local schools. The inspiration that occurs is unbelievable. I had a podcast called Gravity Assist. I interviewed 100 scientists and engineers, and I said, what was those things that got you so excited, that enabled you to change your direction from whatever you were doing to become the scientist you are today? And every one of them came up with inspirational ideas, whether it's talking to an astronaut, seeing a program, reading a book, having parents that are excited about the science and getting you excited. Those are the things that we have to be able to think about doing more of.
I see Chris over there. He wants us out of here, but please, we'll take another few seconds, just a few seconds each. John?
Yeah,
And then we'll come
wanted
back.
to say that science isn't the only area that's being threatened by cuts in the budget, and all of them matter to all of us. So health, retirement, Social Security, all those things matter to everyone, and the government has a major job to maintain those. We put those in place for a reason. It was a national consensus for like 50 years, and we like it. So we should keep on going all of those things, and that's my feeling. We're not especially just complaining about or worrying about science. The whole nation has got a decision to make.
Great nations, it's not about this or that, it's this and that.
Also,
Jim Garvin, I'll come back to you in a moment, Brittany. We'll let you wrap up. Jim?
So I think it's also the messaging in what the engineering has given us. I think it's, John, we all were saying that indirectly. The quest for the science pushes the engineering. And for me, in communicating that, I think of the IT revolution we're in and the possibilities. We're in a digital exploration era now. We weren't at the early Apollo. We barely were. I mean, we were, I guess, to be fair, even though some certain computings failed on terminal descent and things. So those are some of the byproducts that we can communicate, because we take it for granted that the compute power in our cell phones and things like that now can be projected into space. Space is the place to push those boundaries and to communicate that. That is going to be an economic engine too, to the backbone point. And I don't think that's communicated enough, because every time I think of rovers on Mars and I told the stories, it's the engineering successes where people said, well, that can't be done. They told us we could not fly a laser altimeter to map Mars. It seemed to work. I mean, I think people are pretty happy with it. And gee, it did well on the moon. We prepared the place on the asteroid Bennu. I mean, so those who say not, I think I've always found in my experience, the engineers can make it happen. And that story is, it's the American ingenuity story, the world ingenuity story, really. And, we should talk about that and communicate it as Jim said. So thanks.
Brittany, you get the last word.
I think we need to remind people that we're also talking about people, right? We're talking about scientists and engineers and people with kids and people who are teaching colleges and people who are building things and people who are building teams. This is a human endeavor, and it's one that's been distinctly American and distinctly motivational. NASA's the best brand in, the universe that we know at least, and that's because of what it did for everybody. So it's this call to action that really is very human, and it's done by people. Every one of those dollars spent on the space program or in fundamental science in any of the government agencies is one that's spent on the jobs of people and on things that are going to make everybody's lives better. So removing humans from the equation, we can't separate the science from the scientists, and we shouldn't want to do that, because it really is amazing that a bunch of self-organizing chemistry got up one day and said, who am I and where am I going?
What is it Carl said? Carl Sagan, we are a way for the universe to know itself. Please help me thank these 4 inspiring leaders. We are way over. And it is my pleasure now to introduce a special video statement that we have received from Democratic Senator from Maryland, Chris Van Hollen.
Hi, I'm Chris Van Hollen, and I represent the great state of Maryland in the United States Senate. And I'm very pleased to join all of you today for the Humans to the Moon and Mars Summit. I want to thank all of you for your interest in this topic because our space program is a win-win-win for everybody here on the ground of Mother Earth. It spurs innovation and boosts our economy. It expands the boundaries of human knowledge, and it inspires us to believe in our capacity to achieve great things. But as you know, it's one thing to dream about traveling in the solar system and beyond. It's another thing to get off the launch pad. In the United States Senate, I've made it one of my missions to continue the legacy of my predecessor, Senator Barbara Mikulski, who acquired the nickname Madam Space for her decades of advocacy for Maryland's incredible space assets, including NASA Goddard Spaceflight Center, the Space Telescope Science Institute, the Johns Hopkins Applied Physics Laboratory, the National Oceanic and Atmospheric Administration, and Wallops Flight Facility, which while in Virginia is run mostly by Marylanders. It's thanks to leaders like Senator Mikulski and leaders like all of you that our government has had a proud tradition of investing in space exploration and science, and reaping the rewards for the American people and humankind. As the lead Democratic senator on the Commerce, Justice, and Science Senate Appropriations Subcommittee, which is in charge of funding for NASA, I am committed to working across the aisle to ensure that the United States government's support for space science and space exploration remain bipartisan priorities for our government. We know the United States won't maintain its edge as the leading nation in space unless we keep our foot on the accelerator. That's why I'm a strong supporter of the Artemis program to return to the moon, not just to plant flags and take samples, but to build sustainably and collaboratively in accordance with the Artemis Accords. And I'm very excited about realizing the goal of setting foot on Mars. I do want to emphasize that these achievements and future endeavors in space are only made possible because we have had a robust space science program. So when we look at the budget, we must not pit funding for space exploration and space science against each other. It cannot be either or. It must be both. Space science is the bedrock of every giant leap for mankind we aspire to take. It gives us the tools we need to read the ancient geology of Mars and other planets and to understand their climates. It gives us the knowledge we need to detect water ice beneath planetary surfaces and to find habitable worlds. It is fundamental to understanding the heavens, but also to bringing new innovations here on Earth, including things like GPS systems and breakthroughs in material science and robotics. And of course, the amazing images brought to us by Hubble and Webb help inspire the next generation of curious students. That is why we also need robust federal funding for STEM education and scientific research. As we speak, the individuals who will one day be the first to walk on Mars and the thousands of people who will support them in mission control are probably sitting in classrooms, from elementary school all the way to graduate programs. If we want their mission to succeed, our mission to succeed, we need to give them the very best education and preparation they can get. In this time of chaos on Capitol Hill and uncertainty for the federal budget, I am still more determined than ever, not only to maintain but to expand federal investments in space exploration and science. And in the coming years, I'm excited to watch NASA search for life on Europa, deploy the Nancy Roman Space Telescope to discover the secrets of the early universe, and continue the Artemis program to return Americans to the moon, and fulfill our plans to land humans on Mars. So I'll end in the spirit I began, thanking all of you for believing in the promise of space science and exploration. Generations of Americans have achieved impossible dreams in space, and it's thanks to you that we will uphold that legacy. Take care.
All right. For our next panel, and one of the most important questions we've been asking ourselves for centuries, really, is there life on Mars? And I think you will find our panel will have some really compelling new evidence kind of indicating that there might actually be life on Mars. Leading the panel today is Tariq Malik, who's the editor-in-chief of Space.com, and who are our media sponsor here at H2M2 this year. And he started at Space.com in 2001 as an intern and worked his way up through the ranks, eventually becoming editor-in-chief. And he'd been a lifelong passionate person about space. He was an Eagle Scout who actually got a space exploration merit badge. And he's worked at multiple different press organizations before eventually getting to Space.com. So, ladies and gentlemen, Tariq Malik and his panel.
Good morning, everybody. Hello. Well, thank you all for joining us for our panel today, and welcome to our discussion about the search for life on Mars. The search for life, as I'm saying right now, has been one that has long driven space exploration, and I think we only have to look to Mars to see why that fascination there is so enticing. It's a red planet that has driven the imaginations of scientists and science fiction alike, and we've got an esteemed panel of experts to explain where we've been, where we are, and hopefully where we're going in the future. I'm your monitor, as Chris mentioned, Tariq Malik, editor-in-chief of Space.com, a future publication, and I'm joined by Dr. Jim Green, who I don't know if I should introduce again because I think he's been here for a while, former NASA chief scientist. Also, Dr. Jen Eigenbrod, an astrobiologist specializing in organic bio and geochemistry of Mars and ocean worlds at NASA's Goddard Spaceflight Center. And rounding out the crew is Dr. Danny Glavin, an astrobiologist and senior scientist for sample return at NASA's Goddard Spaceflight Center. Thank you all. Welcome. I think we've got some presentations. I have a fancy little doodad here for you, Jim, to start us off.
All right. Wonderful. Thank you very much for having the opportunity to talk about one of my favorite subjects, which is searching for life. And let's go to the next slide, which, if we can connect this. Can we just go ahead and change to the next slide, please? All right, super. I'm going to try to set the context of what's happening in the area of searching for life on this fabulous planet. The planet that's most Earth-like, the planet that humans can go, live, and work and return from. And the history of that, based on all the missions that have flown there, orbited, landed, roved, we've been roving since 1997 on the beautiful red planet Mars, have enabled us to put together its history. So a broad stroke of its history, its early history after it came together, really it was a blue planet. Much like Earth, it had greenhouse gases that kept it warm, even though the light from the sun was very dim, much dimmer than it is today in comparison. But over time, it went through rapid climate change and has now lost its ocean, and it's much more arid with a much thinner atmosphere associated with it. But what was happening on Earth during this time period? Well, as you see, at about 3.8 billion years ago, when Mars was a blue planet, life started here on Earth. So we're probing by going to Mars those early conditions that supported life here on Earth. What was it like on Mars? And we're finding enormous similarities. So is life so unique to Earth, or are conditions like could have occurred on Mars that made it habitable actually started life there too? All right, so let's try this. Oh, great. Well, a couple things about Mars over time that we have to understand is its rotational axis relative to the orbit plane called the ecliptic changes wildly from 15 degrees to 45 degrees. Ours is much different. Ours only changes by a couple degrees from 22 degrees to 24.5 degrees. So currently we're at 23.5, coming off 24.5, going back to 22. So very small changes, but we see major climate changes that occur globally. That must have been occurring on Mars during its entire history. And the reason ours is so stable is because the moon has been just a wonderful factor in stabilizing that rotational axis called the obliquity over time. So we have to put that in context of how the climate changes. Well, one of our first life-finding missions dedicated to going to Mars and looking at the biology, in addition to some of the aspects of chemistry, etc., was the Viking mission. These were 4 elements, 2 orbiters, 2 landers. Viking 1 had an orbiter and a lander. Viking 2 had an orbiter and a lander. Now, the lander had the opportunity to bring in soils and do action to those soils. Look at gas exchange, look at other kinds of processes that are occurring in these 3 experiments. And each of these were life-finding experiments. And in fact, the concept between the project was, well, we need to have at least a couple of these experiments indicate that there are some life signatures going on before we would claim that there's indeed life on Viking, or on Mars, as measured by Viking. Well, it turns out only the labeled prolytic release experiment indicated some positive result, and therefore thought that there might be life, but neither one of the other 2 experiments did. Didn't find the organics, there wasn't the reaction we expected in the gas exchange experiment, and therefore it was inconclusive. We now know today, based on a better understanding of the chemistry in the soil, that perhaps the labeled release experiment actually measured a chemical reaction and not something associated with life. All right? But now, as we've gone to other places, these are places that we feel, because we can get to them now, because of the new technologies that we've put in place, the ability to shrink our landing ellipse to go into more hazardous areas, like Gale Crater, going down to the bottom of the crater. And Gale Crater sits on the shore of an ancient ocean. So water poured over the crater wall, filling up the crater. And over seasons, as it would go up and down in height, it eventually pooled down at the bottom of the crater. And some fabulous things had the opportunity to be discovered by Curiosity. Well, Curiosity went to Mars, and as Jim Garvin mentioned earlier, as soon as it drilled below that first few millimeters of soil, that oxidized soil, we found a whole new environment. Gray Mars, we called it. The soils had all kinds of wonderful stuff. It had carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Everything you see between my 2 fingers. So it had the right kind of stuff, like Earth did in the early period when life started here, on Mars. And so this means that it's an environment that could have been habitable in its ancient times. Other life signatures were also being observed. The Goddard scientist, headed by Mike Muma, looking using the Keck telescope funded by Planetary Science, was observing Mars in a certain wavelength regime that methane emission was occurring. And he could get a global view of methane distributions, and found that Mars, at certain periods of time, plumes of methane were being found. Well, that's actually a biosignature, but methane could be generated biotically in addition to abiotically. So it doesn't rule out that it's not a life signature either. Plus, it's a remote observation. How good really is it You're looking at methane on a planet through methane here on Earth, in our own atmosphere. This is why going there with Curiosity enabled us to bring in that atmosphere and indeed made the measurement that methane was observed on Mars and actually had this cyclic intensity over time, where more methane would accumulate in the atmosphere during the summer periods than at other periods. Curiosity is observing methane all the time at some level, above its background level. Well, what does that really mean? Have we found a life signature? Well, we really have to move into a process for which we determine a confidence level in the life detection. We call that a COLD index, confidence of life detection. It's a scale that a number of scientists proposed that we start using, where COLD level 1 is we see the biosignature. Remember methane, we said we see it, but COLD level 7 says it's definitely life. And we have to work our way up that to be able to gain the confidence of each and every one of these measurements, because there's no biosignature, at least that I know of, that can't be generated abiotically. And that's part of our problem. So once we got to Mars and began seeing that methane actually was being generated, we moved up that COLD scale. And in fact, the methane observations on Mars is a COLD scale level 3. We're making enormous progress walking up that scale, but we have a lot more to do. We have many other ways and processes that we have to put in place to be able to make a definite move up that particular scale. So this is part of our scientific process, and we're going to now talk about some of the other fantastic things that are being discovered, not only by Curiosity, but also by Perseverance. Jen?
Thanks, Jim. All right, so...
did you introduce Jen?
Yeah.
Yeah.
From
There you go. That's me. All right, so let me give you a little bit of context. Let's step it back a moment. We have been interested in the life question. Is there life on Mars? Either in the past, the present, even the future. We've been asking that question pre-Viking. But at the time that Curiosity landed on Mars, most of the scientists actually didn't think we'd ever come across organic carbon. This is the key building block for all of life, all of the food that life wants to eat, all of that stuff is organic carbon. And it's a very, very fundamental part of that habitability story, and we weren't sure we were going to find it. Well, lo and behold, when we got to the base of Gale Crater, we did. And the first thing that we found was something called chlorinated organic molecules, such as chlorobenzene. So I'm showing that here in the middle here. This was a 3.5 billion-year-old lake bed and had every indication that it was habitable. And here we find a compound that is unnatural at Earth. Can I tell you how stumped we were when we found this? What does this mean? This is bizarre, and we didn't know how to make sense of it. It actually would have smelled a little bit like almonds. And it's a very bizarre compound. And we didn't see much more. So we moved on. And we kept on working our way up the crater to a place called Pahrump Hills. And here we found, in another lake bed, a different lake, where most of Gale Crater was probably filled with water. Here we found much more organic material. And in that, we found a diversity of little components. And I call them little components. They're all these little carbon molecules. And I show them here just for, so you can see what these structures look like. They're small little things. And when we found them by heating up a sample that we put into an oven. And these gases are produced by the breakdown, the thermal breakdown of that material. And what you get are small compounds like this. But really, because of the temperature that we saw these when we heated it up, what we know from that information is that these small molecules like benzene and propane actually come from something much bigger called kerogen. This is really important because if we want to go look for life somewhere else, especially past life, it's something like this that is going to lock the molecules that tell us that life was there. It's this material that self-preserves that signature. And so now that we know that that macromolecular material is there, that these big organic molecules are there, now we have something to go target. Now we have something to go aim for and take the right type of instruments to go look at that a little bit further with more detail to look for the things that we associate with life. Now, from what we knew of the observations we had with the instrument called the Sample Analysis at Mars, which is on the Curiosity rover, we weren't sure where that organic matter came from. What we did back here in the labs was we looked at things like the Tissot meteorite, which is an igneous meteorite. It's something that it's more basaltic in nature. It's something that comes from the geological processing of the planet. Maybe it has some hydrothermal fluids in there, and it has organic matter in it. And we looked at that using a SAM-like approach, a same experiment, and we saw similar things, all these small little bits and pieces. We looked at the Murchison carbonaceous chondrite, which is a meteorite. And meteorite material is always falling onto the surface of Mars. And at this lake bed, it would have been a catchment to collect all of that. It's a likely source of organic material if it was not Mars originated. And it produced the same type of signatures. And then we pulled out a paleosalt. So this is an ancient soil bed. And it had organic matter in it that had gone through geological processing. So it's biological material that had gone through processing over eons on Earth. And it also produced similar signatures. The instrument we took was perfect for detecting organic material and the type of organic material that's there, but it was not ideal for getting at the details of the source. It accomplished that giant step forward in saying, hey, there is organic material on Mars. It's in the sediments. We know it's in the igneous materials like the Tissot meteorite. We know it's there. Now we need to understand a little bit further with different observations what it's telling us. Now, we go back to that question about life. Why do we even bother thinking about life on Mars? Sure, there's a history there, but the surface of Mars is sterile. It's sterile because of ionizing radiation. It's so intense. And there's also not much water around. But what we have found on Earth is that extremophiles live in almost every single environment. Somehow, some way, life finds a way. And here is an example from Chernobyl. Of all places, there are fungi that use the gamma radiation left behind from that horrible event. And they're using that radiation to live. You take their radiation away and they don't do much. They use it to live. Talk about extreme. Then there's the cases of extremophiles living in the deep subsurface. We have permafrost that's melting today. And what are we finding? We're finding organisms that are in that. Some of them have been there for 500,000 years. They're still producing. They're still there. They're surviving. So if they can survive here on Earth in those extreme environments, we have every reason to suspect that they could be on Mars, but maybe they're not the surface. Maybe they're just below the surface. Maybe they go through phases where they're active when the obliquity is warming at the subsurface and there's ice that has melted and there's groundwater around. Maybe they're down there in the subsurface doing their thing, and then when the obliquity changes and everything freezes up, they kind of get locked in place. That's important. You know, there is a possibility that there is life on Mars. And we are going to Mars. So the question is, are we going to be alone when we get there? And if we aren't, how are we going to find out? Now, of all of these things, that life question is a key one, but there's so much more. Context is everything in trying to understand if there's life there. Scientific discovery comes in a lot of different shapes and forms. We do exploration, we have investigations. It reveals to us the resources and the risks for everything that we want to do at Mars, no matter what your goal is. Science is the backbone for establishing what we can and cannot do. It not just enables everything, it provides us with the strategy for which we achieve it. Okay, it's fundamental that we have that science. It gives us an opportunity to define our technical requirements, identify and find resources, mitigate those risks. Think about things like Martian life, organics, the nutrients that might be there, water, perchlorates, oxidants, dust, the weather, How about things like ionizing radiation and rock compositions? All of those things, all of the science that investigates that feed forward into things like farming, construction, life support, filtration of all that dust. How about energy capture and energy storage, or even a fuel source, and even hazard mitigation? And then my favorite, what if there is life there? How about an Earth-Martian biome? What's that going to look like? So is there modern Martian life? I certainly would like to know. If it's present, it could be hugely advantageous for us because life depends on life. And it might not be there, or it might be hazardous. It's important for us to go and find out. Okay?
Great. Thank you, Jen. Yeah. I sure hope there's life there. I'm going to be blunt about that. Let's see, go to the next slide. So I want to hit on kind of a recent discovery just reported in Proceedings of National Academy of Science 2 months ago, so literally hot off the press. Jen talked about the Cumberland mudstones in Yellowknife Bay that were analyzed by the SAM instrument on Curiosity and focused on the smaller molecules. But now we know there are actually much larger molecules there. In fact, these are the largest organics discovered on Mars to date, and probably the closest thing we've come, in my opinion, to a biological organic signature. These are long-chain alkanes. We think they were derived from fatty acids. And you know from your biology course, fatty acids are important components of cell membranes in all life on Earth. So very tantalizing hints there of possible ancient fatty acids in this mudstone, but not definitive, not conclusive. We know that these compounds can also be formed by geological reactions, the same ones that can produce the methane. And so we're being a little cautious here. I'm personally pretty excited about this. We need to get samples like this mudstone back in labs on Earth so we can use the techniques that we have available to try to determine whether these organic compounds are biological in origin or not. Next slide. One of the reasons this was so surprising, finding these large organic molecules, was because of the radiation problem Jen was just talking about. This is a challenge for organic preservation, especially in these 3.7, 3.8 billion-year-old rocks that have been exposed to ionizing radiation. Mars doesn't have a magnetic field like the Earth does to shield us from this radiation, and it can penetrate down to a meter depth or more and literally break apart organic molecules. So the fact that we found these 12 carbon alkane chains that have survived this radiation definitely makes me much more optimistic in our approach to search for evidence of ancient traces of life in the near surface and potentially even larger molecules. Fragments of DNA, who knows? We need to keep looking. Next slide. Of course, another strategy to deal with the radiation is simply to drill, and that's the philosophy being taken by the ESA Rosalind Franklin mission, very appropriately named. Rosalind Franklin was a British chemist whose research kind of led to the understanding of the structure of DNA and RNA. So this is a very exciting mission. Hopefully we'll launch next 2028, land on Mars in 2030 in Oxia Planum, which is this ancient Noachian, clay-rich region that may have preserved ancient signs of life. And again, the ability to drill and access materials that are below that ionizing radiation, maybe more pristine material, is really important. I also want to highlight one instrument on this rover called the MoMA instrument, new technology, an ion trap mass spectrometer with a mass range about double the SAM instrument. So we'll be able to detect molecules up to 1,000 Daltons, built right up here up the road at NASA Goddard, coupled with a laser that allows us to actually desorb larger polymers and feed them into this mass spectrometer to detect them. SAM uses the pyrolysis oven approach, and we've heard from Jen how that breaks apart molecules. With the laser, you avoid that. So a very exciting mission, looking forward to this. Next slide. Oh, do I do it? Oh, I get to do it now. Okay. I want to turn attention to Perseverance, the other Mars rover on the surface now, targeted at Jezero Crater of Mars. This site was selected for a couple different reasons. One, obvious evidence that it was an ancient lake, a habitable environment. You see the inflow channel, the outflow channel, and then the mineralogical diversity, just the diversity of rock samples here is really tantalizing. You've got igneous rocks on the crater floor, can be used to determine the age of the crater. You've got sedimentary rocks as part of this well-shaped delta with clays and carbonates. These are minerals that we know from our experience on Earth can preserve signs of ancient life. So Perseverance is no doubt in the right place trying to answer these questions. Next slide, or I'll do it. Is it the green? Okay, there we go. Okay, so Jim talked about this cold scale, which, to be honest, it's kind of a pain. This is really a pain in the butt. I feel like we're close with Mars, but the bar has been set so high for life detection on Mars that we've reached step 3, okay, from the rovers. We've got these interesting signals. We've ruled out contamination. We didn't bring this stuff there, and biology is a possibility. But we need to take that next step. We need to rule out all non-biological hypotheses. We need independent confirmation of some of these results using other techniques. That's an important part. And really, to get up this scale, samples in the lab are really the way that this is going to be accomplished. Oh, let me go back. Sorry. And I just want to show this image. This is just striking. So these are the cores, some of the sample tubes that Perseverance has already collected in Jezero Crater, 21 here. I think they're up to 28 plus now. And just look at the diversity of the minerals in these rocks. All of these tubes are telling an interesting and unique story about Mars. And it's incredible. Right now, the rover is actually outside on the crater rim, exploring a region called Crocodilin, which I think is crocodile in Norwegian, looking at actually some really interesting sediments that are 4 billion years old, right? So these were clay deposits that were there even before the crater formed. And what excites me about this is now we're going to have rock samples that are 4 billion years to, say, 3.7, 3.6 billion years. So we've basically capped that period of time in the early solar system when we know life started on the Earth. Wow. So whether or not we detect life or not in this sample set, we're going to learn about the chemistry that potentially led to life on Earth. And that personally just gets me really, really excited. Returning samples is important, of course, for other reasons. We can drill samples, we can make powders, crush samples, get cores, as Perseverance is doing. But we can't make a polished thin section. I mean, this is art in and of itself if you talk to folks and geologists doing this in the lab. We can't do a lot of the wet chemistry and extraction that we need to get those fatty acids out of the rock without decomposing them into alkanes. This is stuff that we routinely do in the lab now. And of course, having the instruments, the unlimited set of instruments that only improve with time to really search for these biosignatures and nail their origin is critical. I want to have just one quick story about the Apollo missions. 1972, Apollo 17. I wasn't even born then. And up at Goddard, we're analyzing cores that were just opened after 50 years, pristine sample cores. And by golly, we're detecting extraterrestrial amino acids in these soils that were delivered from micrometeorites to the lunar soils using techniques that didn't even exist at the time of Apollo. And so this is, in my opinion, the power of sample return. And here is just a few of the instruments that can't be flown in spacecraft, again, that we routinely use in the lab to answer these really tough questions. Some of these instruments, like the synchrotron facility in Livermore, is the size of a building. Requires a huge staff, a lot of power to operate. Something like that is never going to fly in space. And we're using these techniques right now to analyze samples from asteroid Bennu, from NASA's OSIRIS-REx mission, pristine asteroid samples. We're learning about the formation of the solar system and even the chemistry that led to life, just from tens of milligrams of samples. So again, the power of bringing samples to Earth. And then just to end up here, we know what the future of Mars is, right? This is humans and robots working together on the surface. This is, I think, why we're all here and what we all want to see. And the science that's going to be enabled by human exploration is going to be unparalleled. I mean, they're going to be able to drill down not just 2 meters, but probably hundreds of meters, right? Maybe even get down to an aquifer where there could be life today. They're going to be able to bring tools and fix them when they break that we can't do robotically. Of course, the low latency decision making, there's simply no substitute for a geologist or astrobiologist's eyes on the ground to select the right samples. And then, of course, bringing back much more sample mass and actually preserving the samples. Many of these rocks that we're exploring in Jezero have never seen temperatures higher than minus 20 C, right? And so it actually behooves us to try to keep them cold, to preserve them. And that's something that could be, of course, accomplished with a human mission. And I will leave it at that.
Thank you. Thank you so much, Danny. I have so many questions. So, but I guess my first one would be for Jim, because when I talk about life on Mars, my daughter, she's 16, she asks, why haven't we found it yet? And when I was growing up, life on Mars was Marvin the Martian, some weird tentacle aliens from H.G. Wells, some canals that were in a telescope. But now that search looks very different, and I'm curious how the evolution of science, the evolution of these processes that you've all been talking about, has shaped that push and given you maybe a bit more of a refined targeting for where to look now and next.
I think what's critical to understand now is that since the surface has no life, when the environment gets extreme, life goes into the rocks. That's a fundamental thing that we find here on Earth. As Jen mentioned, over time in evolutionary states, though that life changes based on its environment, and then it's an extremophile. It lives in very difficult environments. The key with perseverance, coring rock, enables us, when we bring that back and put it in the laboratory, to begin to look at every aspect of it, the mineralogy of the rock. Here on Earth, there's 5,700 minerals that we can delineate, and 347 of them are made with dead life. They become the fabric of rocks. And now we have a record that we can go back and see not only environmental change and when those conditions on Mars became severe, but look back and see, hey, this is a perfect opportunity for that life to then go into the rock, and then in its own life cycle, perhaps there's traces that we can find. So we now know so much about Mars. We know, I think, where to look, and bringing back those samples is one of the best aspects of it. The other thing that we find here on Earth is, from an astrobiology point of view, everywhere we find water, we find life. You can go 2 miles down in a cave, and if it's seeping water, there's life there. And Mars actually has an enormous amount of water trapped inside the crust, trapped inside the rocks. And so that's our next approach in looking for life.
Great. Well, speaking about life going into the rocks, I think, Jen, you mentioned in your talk about looking at what you see in meteorites from Mars, the Thyssen meteorite. There have been others. And some would ask, why isn't that enough to tell us if there was life on Mars? Oh yeah, there's organic compounds in these meteorites. Surely that's proof, right? And the case is closed and we can all go about our day, but it doesn't sound like that's the case.
No, that's not the case. Organic matter can come from all sorts of places, and a lot of it is non-biological. And organisms can use that organic carbon, but just the presence of organic carbon doesn't mean it is biological in nature. So what we feel as, or scientists want to have a strategy towards looking for life. It's not just about finding the right sample and going to the right place. When we go to make our measurements, we want to make sure that we measure the organic materials that might tell us if there's something biologically, something we associate with biology there. But we also need the context to understand, how did that organic material get there? Does it make sense that that organic material is coming from biology? We need the whole package. It's a system, and we need to be able to understand that. And so as time has gone by, our ideas on how to do that have evolved. It's a working strategy that keeps moving forward, and we keep getting better at it. Our instrumentation is getting better and better. And we now have the tools to do this type of an investigation on Mars. There will still be limitations, because we're limited with size, mass, power, all data. We have all those limitations still. But we have enough tools with a good idea of what we want to look for and where we want to look for it. That's there. We've gotten rid of a lot of the risks and increase our probability of learning something very important. Is it there or not?
Speaking about the tools, I forgot to ask earlier, if there's an inconclusive result from something from like Viking, for example, why not just fly another experiment, the same one, on Curiosity, on Perseverance,
From my perspective, you're going to get the same answer. So the fact that the really key next step would be bringing back those samples and performing that experiment again in your lab. And then you have a complete idea of, well, it is just chemistry, or wow, maybe it is a signature of life. Because you then have complete control of the conditions and you know what the input and output is.
It sounds like it's pretty clear that you want to have your hands on some of these samples, like scientists did with samples from the moon.
Absolutely, but also even atmospheric samples. Now, right now, we know methane is in the atmosphere. SAM says it's there, but SAM doesn't have the ability, because there's not enough methane that it gets, to look at the isotopes of carbon. Life loves carbon-12. If all the methane that is emitted is from carbon-12, and there's no other carbon-13 or 14 in that, that is a huge step up that scale, up that cold scale that says, wow, now we've increased the probability of our understanding that it is coming from life.
Well, speaking about sample return, Danny, I mean, it sounds you made a pretty good case for why you want to do extra science on Earth of samples from Mars. Just the different equipment that you have here, I guess the more sensitive, the more capable those instruments are. But it sounds like it's really hard to bring samples from Mars back.
Well, I mean, we're working on it, right? There's a plan to do this, but yeah, none of what we're doing is easy. This is a first. We've never brought samples back from another planet. This is the first time we're doing that. We have the meteorites, so we talked about the Martian meteorites. If I could touch on that maybe a little more as well. People think, you got all these rocks. There's 400 Martian meteorites, right, we have in our collection. But most of these are igneous rocks, volcanic rocks. These are not the types of rocks you look for evidence of life, right? They were at high temperature, et cetera, et cetera. We don't have the context. We don't know where on Mars they came from. They were heated by the impact ejection event itself that sent them to Earth. And then when they hit Earth, they were rapidly contaminated by Earth's biosphere, right? Biology finds a way, including eating the organic matter in the meteorite. So the story gets very complicated with these samples. And it was incredible what they were able to do with ALH 8401, which I think bears on the power of laboratory instrumentation, right? Even to be able to pose the question that it could be extinct life required the ability to have this instrument capability. So for me, it's clear. The next step is we need pristine samples. We're learning that right now from OSIRIS-REx with the pristine asteroid sample. We've been studying meteorites. In many cases, we've been fooled by contamination. It's only when we had these pristine samples of asteroid Bennu in the lab that we realized that. And I'm sure the same will be the case for Mars.
But for the Allen Hills meteorite, the contamination is it sat on Earth for
13,000 years.
Yeah,
on the ice.
Thousands of years.
Yeah.
And life, once again, loves these environments and can go into that. So is it Earth life or not? We might have come up with a completely different conclusion if that ALH 84001 came from Mars directly. Now we'd have more opportunity to understand it and know where it came from.
Yeah.
And know where
it was from that ancient lake they had,
Right, and so that's really critical. When you think about the concept of bringing back samples, we have to have a Mars ascent vehicle, all right? We have never blasted off, other than the moon, but samples like this from another planet. That's really critical for us to be able to start the process of an ever-increasing ability for a Mars ascent vehicle if we're ever going to have the hope of bringing humans off. I mean, we all watched The Martian, right? And Andy Weir really ducked the biggest problem, and that is, how did he get this huge rocket down on the surface of Mars? And not just one, two. And so we've got to be able to work our way up, and the start of that process is bringing back the samples.
Well, I have questions about that as well, but I did want to ask you, Jen, about the risk of false positives, both with a sample return, both with an in situ experiment on like a super perseverance or something, or by the astronauts themselves once they're actually there. Because it seems like in this day and age, like one false positive could be a much bigger deal, if you will, than perhaps ALH was in the past there.
It's a huge deal. And everything that we do, it is constantly in our minds. And we have to train ourselves in designing the missions, the engineers who are working on every single piece of hardware that might engage with the sample and influence that sample path. Everything we think about what those false positives would be. Life is just ubiquitous here on Earth. Even the air has enough biology in it that if we just took a swab and sampled it, yeah, we'd get a false positive if we were on, if the same type of thing was happening at Mars. Their instruments are so sensitive that we're now detecting, a few cells at a time, or maybe even down to single cell, depending on the instrumentation. So when everything that we do, mitigating that contamination from the very beginning, trying to keep everything as clean as possible, and knowing what the contaminants are is very important. I think of contaminants like weeds in our garden. We can tolerate a few, especially if they're the little ones, but if it's one giant weed and it's overtaken, the tomato plants that you have there, it's a problem. Or if there's a whole bunch of them, it's a problem. So we have to avoid all of those extra weeds as much as possible, and they come in places that you wouldn't expect them. So we have to understand how they enter into our sample paths. But we have ways of doing that. We have ways of monitoring it and keeping tabs on where are we in terms of how clean we are. And then when we get to our destination, let's say it's drilling into a sample in the subsurface of Mars. Now we will probably have a positive control and a negative control, where if it's the negative control we know is absolutely pristine, and we're going to use that as a test to make sure we didn't bring anything with us. And we're going to bring the positive control to make sure that the signals that we expect to be there for something that we did bring deliberately are there. And that is how we sort of stabilize our baseline for interpretation. We know how to do that. I won't kid you, it's incredibly difficult to do. And as our instruments get more and more sensitive, it gets harder and harder. But we know how to do it.
Yeah, I want to make one point just to follow up the contamination knowledge aspect of this, because you can never clean hardware perfectly, right? But I want to point out that the Perseverance rover actually has 5 tubes called witness tubes, witness tube assemblies with witness plates inside that are documenting the environment from launch all the way when these samples come back, the contamination environment. So there'll be a very good record of what was added to those samples that we'll compare to. So I think that's going to greatly reduce the risk of false positives for the samples.
And that enables us to walk up that cold scale.
Absolutely.
In a very quantitative way.
And there's another aspect of this. We think about bringing those samples back, and maybe that will happen. Maybe we're going to have humans at Mars, and they're going to be engaged in the science. Now that is a whole nother book that we haven't really opened up yet to try and understand how do we control human contamination that we deliberately take with us as part of a habitat, as part of our instrumentation. We may even have humans running the equipment that is sampling to look for Martian life. That's harder to do. And this is part of the reason why robotic missions, perhaps with humans, are so important, is because we can have a better chance of controlling contamination using a robotic interface between the human and the sample. We can do that. But if you have a human sitting there grabbing a sample, I can tell you that if I breathe on a sample, we'll pick up my breath. It's that sensitive. So there is another book on what is that strategy if we go that far. Instead of bringing the samples back to look at them here in a controlled environment, we have to figure out how to control the environment at Mars with humans.
And you kind of touched on it, but is there a safety aspect to that too? Because the sci-fi fan in me always leads to space plague, right? If you dig deep enough on Mars, what are you going to find? Is that like something that we need a rule book for as well?
Certainly. A lot of the equipment and instrumentation that we'll probably have to have in a habitat to try and maintain the stability of that habitat and the sustainability of the cleanliness of it, monitoring for things that have changed, a lot of that same equipment could be used for trying to understand Martian samples. And if there is Martian life there, what's going to happen? I mean, you can imagine having a habitat, and while everything is at the surface, it's probably going to be fine. If there's any Martian life there, it may not have any interaction with humans and habitat equipment and architecture. However, what if we have excavation, whether it's natural or human excavation? Now we get into the subsurface. Now we've brought something down below to the surface, and now it has an opportunity to engage. And it's not just the inorganic materials, the minerals and whatnot that we'd be concerned about. It's also the organics and perhaps life being there. Imagine on Mars, it's really hard to live. It is habitable, but it's not super habitable. Otherwise, we'd see, green stuff probably at the surface. That's right, it's not pervasive. But if we all of a sudden present it with an environment that has everything at once, because the human habitat is that type of space, what's going to happen? I don't think that we have any idea. It's a grand experiment.
Yeah, in fact, when our astrobiologists look at the amount of biomass we have on Earth, there's more biomass, in other words, mass from life, below our feet in volume than there is walking on the Earth. So going into the rock produces an environment where these extremophiles can grow and stay active for millions and billions of years. Far longer than life, sometimes even on the surface. So these are all important considerations. So planetary protection is a critical aspect of it. But the things that help us, I think, in the area of planetary protection is that those things that are harmful for our own life evolve with us. Mm-hmm. Life on Mars has evolved however it's evolved. And there may not be the problems that we may have, but we have to anticipate problems, no matter what.
I think we have a few minutes left, and there is one question that I did want to ask everyone, so feel free, each of you, to touch on this. And it's a little philosophical because clearly we've been talking for the last hour about how difficult it is to do this search. But if you are driving a rover and it finds a flower on Mars, something that is unmistakable, right? A dormouse or whatever, I'm curious how you think that would change things, not just for science, but for all of us here on Earth.
Well, that raises it up the cold scale pretty far. Indeed, one of the things I wanted on the rovers early on was a microphone, because I wanted to hear the crickets at night. Either that means no sound or there is sound. But the bottom line is there are tools like that we've taken to Mars, and we indeed can verify that we haven't seen or heard any life on Mars. What's critical to understand is we're now narrowing down what we need, and we need these samples back to make huge progress, and I think we will.
Jen?
When we think about life elsewhere beyond Earth, we think about all of those other galaxies that are out there. How many are there? I don't even know if we have a number. And in each one of those galaxies, there's solar systems, and they have planets, and some of them are probably habitable by our standards. And it just seems to make sense that there's probably life out there, but we don't know that. And if we go and look for life on Mars and we find it, now it gives that whole idea a little more credibility. But if we don't, wow, why not? It should be there. There's life in our solar system. It should be in these other planets, Mars, Enceladus, Europa. It should be in these places based on everything we know. So I think what we do and do not find with a credible search shapes our perception of who we are and how we got here in our own universe.
Debbie?
Yeah, to me, this is one of the biggest questions, is there life elsewhere? How did we get here, right? And I think Mars holds the clues. We're talking about these ancient rocks on another planet, right, that have potentially preserved this chemical record of either prebiotic chemistry or the origin of life itself at the same time that we know life started here on Earth. And we've got one example, right, Earth life. We don't know if there's life on Mars. That rock record on Earth that we need to try to figure out where we came from is gone. It's been destroyed by plate tectonics and weathering. And so Mars is is our hope to try to understand that. And there are few outcomes here. We go there, there's no life. Well, that tells us something about how difficult it is to go from a prebiotic chemical soup to life itself. I think probably more likely, maybe we find traces of ancient life. And then the question is it related to us or not, right? If it's related to us because the planets we know have been swapping material, that would be a profound discovery. Great, we're not alone, but it's not an independent origin of life. If we find life on Mars, either dead or alive, that has evolved independently from life on Earth, oh my God. I mean, that has the potential to be the most profound discovery in all of science, right? Because it means two origins of life in the same solar system. There should be life everywhere. Anyway, let's find out.
Well, let's find out. I'm still hoping for my conversation with Marvin, but we'll see. We'll see. Well, thank you so much to everyone for your time today. Thank you all for listening as well, and I look forward to how that search is going to go in the future. Thank you.
Thank you.
Thank you. Wonderful panel. We're going to take a 15-minute break. Before you take off, just a few scheduling changes. Since we're 10 minutes behind, we're going to move the panel that the lightning talk, short duration crewed mission, Mars mission lightning talk, that'll be moved to the afternoon, so we'll get back on schedule after break. Also, if you haven't registered for the reception tonight, please do so. And any speakers in the audience, remember that please come backstage 20 minutes before your presentation. Enjoy your break.
So we have reached the first break on the first of 2 days here at the Humans to Mars and the Moon Summit, coming to you from on a pretty wet Wednesday from the nation's capital, Washington, D.C., George Washington University, to be precise. I'm Matt Kaplan. If you've just joined us in the last few minutes, you've already missed some great conversations. So we're live, of course, but all of this will be available at exploremars.org. Explore Mars, of course, the sponsor, the producer of the Humans to Mars Summit for so many years, and now the Humans to Moon and Mars Summit, expanding our scope a little bit to Earth's own satellite. We've got all kinds of great stuff coming up later today, but before we do that, while we're in this break, we've got a couple of people to talk to who I'm looking around. There's one right there. Come on over, Joe. And then hey, Joe.
How are you?
Great to see you again.
You as well, yeah.
Executive Vice President for Explore Mars, but also the head of civil space for Aerojet Rocketdyne.
Yeah, that's it.
And not new to H2M or H2M2.
No, this is, over a decade now, I think. And always exciting. So great to hear those great science panels this morning. That's really why we do this. It's all about going out there, learning those things that we have been asking, as John Mather said, almost since the dawn of humanity, and it's so interesting now to see that some of those questions we're that close to getting the answers, and it's a very exciting time.
Is this also why Aerojet Rocketdyne has been a sponsor of this summit for so many years?
Yeah, it certainly is. I mean, I think we look at Explore Mars as an organization that's vital to getting the word out there. As we heard, Jim Green say, one of the most important things about the science is that we communicate the science. And so certainly being an engineering company, enabling a lot of those scientific missions. And as you know, I always like to say, nobody lands on Mars without our engines. But yeah, we're always very excited to be a part of this community. And, the role that Explore Mars plays in that is why we continue to participate.
We also heard people in this last panel talk about that challenge of getting stuff down to the surface of Mars. which is partly, I think, what you'll be talking about. Your panel is up next.
Yeah, that's right. We're talking about some of the major hurdles, and one of those is entry, descent, and landing. Absolutely. And I'm going to harken back a little bit to one of the workshops we did under the auspices of Explore Mars back now 10 years ago almost. It was our Achieving Mars 4. Where we considered the long poles in getting humans to Mars. And we'll see a great panel talking about 4 of those coming up here in just a few minutes.
I'm as worried about the human factors that we aren't designed for space as anything, and you have that represented on your panel too.
Yeah, in fact, Dr. Eric Antonsen is going to speak about that, and he's got a fantastic background in human health program within NASA, and now he's at Mass General Hospital. He's an emergency medical physician. He's also an engineer. I met him when he was a grad student at University of Illinois. I sometimes wonder if he's secretly Buckaroo Banzai, because I'm going to ask him at the panel if he has a rock group as well.
You know, wherever you go, there you are, even if you're on Mars.
Exactly.
Thank you, Joe. Thank you, and thank you, Aerojet Rocketdyne, for being back yet another year to make all of this possible.
Oh, it's our pleasure. Thanks, Matt.
You bet. Joe Cassidy, Executive VP for Explore Mars, and also head of civil space for Aerojet Rocketdyne. Like he said, you don't land on Mars or go to Mars without one of their rockets. One of those panelists who's going to join us on Joe's panel is also here. Hoppy, come right over here. That's a perfect spot.
All right, Matt. Good to see you.
You too. Hoppy Price, Chief Engineer, Robotic Mars Exploration, JPL. Right. Did I come close?
That's exactly right. Yeah, so I oversee the engineering for the 3 orbiters and the 2 rovers at Mars now, and they're all doing great.
And you are coming up with a lightning presentation later today. We thought you were next, but it's been pushed back, right?
No. So the schedule's changed around, so I'm not going to be giving a lightning talk, but I'll be on Joe Cassidy's panel.
Oh, all right.
Yeah,
well,
yeah.
Here's your lightning talk, Hoppy. You are all about getting us to Mars, yes, particularly our robot emissaries. We just heard a lot about sample return and how important it is. And I love that slide that was presented with all of those laboratory devices, which you can't possibly fit on a robot that lands on the surface of Mars. This is such an important priority, and there's no telling whether it's going to go forward.
Right. What are you talking about going forward?
Specifically sample return. But
sample return, yeah. So I think that we are going to return those wonderful samples that Perseverance is collecting, and right now the NASA is moving towards the idea that the first human exploration to Mars would actually bring back those samples rather than bring them back robotically. So that's the current approach that we're being asked to take, and we're certainly willing to rise to that challenge. If humans can collect all the sample tubes and bring them back, that's fine. We could also bring them back robotically. It all depends on what Congress decides to fund.
And they're just sitting up there waiting for us, strewn across the surface of Mars and inside Perseverance.
That's right, yeah. And one particular example is the tube from Chayava Falls. And so that has those rocks with those mysterious leopard spots on them. And on Earth, when we find rocks just like that have the leopard spots, we typically think that those were formed by microbes inside the rock. And so on Mars, it's very tantalizing to think that it could be the same thing, or maybe the leopard spots came from some other process, but sure would like to get those samples back. And if we send astronauts there, I'd like the astronauts to bring back like a bigger rock with the leopard spots on it from Chayava Falls.
So if we send astronauts there, there's still different profiles for those missions. You were going to talk about short duration human missions to Mars. What does that mean?
So there are different options for how you'd send humans to Mars, whether it's in a more traditional NASA-type vehicle or whether it's in the SpaceX Starship or some other commercial vehicle. So there's long-stay missions, there's short-stay missions, and they have different propulsive requirements. But in 2033 and 2035, there are opportunities for doing some very short-stay missions, like a year and a half, that could be done with less propulsive requirements.
And don't I remember talking to you at least once or twice in the past about other options for human missions to Mars that wouldn't necessarily land, but there was even one that would get us a bonus trip past Venus?
Yeah, so 2035 gives an opportunity actually to redo Dennis Tito's Inspiration Mars mission idea, which is to do a flyby. So that requires more of a minimal type propulsion to get there, and you don't land on Mars, but you do a flyby of Mars and a flyby of Venus coming back. And it's a 1.5-year mission, which is not that much longer than astronauts have already proven they can survive on space stations. So it would be an interesting mission. It could be done by a Starship or by a Mars Transit Habitat, but that would be the first crew to go to both Mars and Venus. So that would be quite a historic first.
So lots of options.
Yeah.
I guess we're all waiting to see how it's actually going to happen.
Yeah, so there's proposal for the new NASA budget and going to Mars with humans sooner rather than later, and we'll see what Congress actually funds NASA to do. But I'm excited about humans going to Mars, and I think that will happen someday, hopefully soon.
Hopefully soon. So I would ask you about the challenges, but that's the topic of the panel that you're going to be appearing on in a few moments, so I won't ruin the surprise. Thank you. It's always a pleasure to talk.
Always good to see you, Matt. Yeah. All right.
You too. Okay, we are going to retire for a few moments here, but stick around because we are very close to picking up once again with this afternoon's, the late morning's program, the program you just heard about, the panel headed by Joe Cassidy. But then one that I always look forward to hearing from Dr. Robert Zubran, the founder and CEO, of course, of the Mars Society. And he's here to talk about making the Mars Initiative successful. His latest book was published just last year, The New World of Mars. I happened to talk to him for the Planetary Society online member book club about that book. I think there is an amazing innovation on just about every page of that book from the amazing mind of Bob Zubran. And then we're going to wrap up just before lunch anyway with a panel called How Big a Priority Should Beating China Back to the Moon Be? Well, we know that China at least says that it wants to put the first taikonauts on the moon by 2030. And the current plan calls for Artemis 3 to reach the moon in 2027. It's a bit of a space race. There's a term we can coin. That's going to be fascinating, and that one is going to be moderated by Kara Kunzman of Aerospace Corporation, has a terrific panel. And then we're going to break for lunch, and there's much more left on this first day of the Humans to Moon and Mars Summit. So I hope that you'll stick around with us right through tomorrow, the second and final day of H2M2. Thanks for joining us.
Joe Cassidy, and Joe is the Director of Civil Space at Aerojet Rocketdyne at L3 Harris Company. So Joe, you want to introduce your panel?
I think we're just going to walk in and take our seats, and
that's fine.
We'll
Perfectly fine.
We'll do it in the Tariq Malik model.
All right.
Right. All right. Yeah, we've got a timer and everything. Good morning, and thanks for joining us. Today we're going to talk a little bit this morning about the major hurdles for getting humans to Mars. And I'm very pleased to have the panel here joining. Some of the guys I know really well. I just met Caleb for the first time backstage. But let me just introduce everybody while we're gathering back. And then I'm going to just talk a little bit about a workshop that we did almost 10 years ago now under Chris's guidance and the auspices of Explore Mars. And then I'll kick it over to the panelists to talk about each one of their significant hurdles that they want to speak about. So first, to my left is Eric Antonsen, Dr. Eric Antonsen. I've known Eric for a long time. I think we met first when you were a grad student at the University of Illinois. So his background is engineering and medicine. And I wanted to ask you if you have a rock band. I kind of feel like sometimes I'm sitting next to Buckaroo Banzai. But at any rate, he's now at Mass General Hospital, and he's also lecturing in engineering at MIT. He's a member of the Spear Medicine Division in the Department of Emergency Medicine. He spent some time at NASA, where he was element scientist for exploration medical capabilities in the Human Research Project. And he'll have a really good talk on some of the significant hurdles for humans and the deep space environment. Next to him is Hoppy Price. Hoppy's the chief engineer of NASA's Robotic Mars Exploration Program. Hoppy is another one that we've spent a lot of time thinking about these things at these various workshops that we've held over a decade now. And so he's going to have a really interesting discussion about the transit hab that has to house the humans as we spend these long, extensive journeys in deep space getting to Mars. But Hoppy's got a background working on a lot of different missions, including the Grail mission and the Cassini mission to Saturn, as well as Prometheus and the Jupiter Icy Moons Orbiter mission. So really an extensive background in space missions, and I think prepares him well to talk about the transit hab. Tim Sheehan is space exploration architect at Lockheed Martin. He was previously the Orion system architect. So again, Tim's going to talk to us today about nuclear, both power and propulsion, which is another one of the things we heard about earlier that are very significant in terms of how do we get people out to Mars as rapidly as we can and then get them home safely. And then finally, Caleb Weiss is a systems engineering and project management leader at ULA, United Launch Alliance. He's responsible for systems engineering, integration, and test for upgrades to all the ULA launchers. And I know he had a lot to do with the Starliner qualification for Atlas for the first two Starliner launches, which was obviously human rating the Atlas. So Caleb's got a great background to talk about another subject that we've looked at, which is the entry, descent, and landing of payloads for the Martian environment that would support human exploration. So with that, great panel. Again, I want to thank them all for being here. I'm just going to go to my slides and talk for a moment about this workshop we did back about 9 years ago, where we talked about the long poles. And let's see, it works. So if you go online on the Explore Mars workshop, on the Explore Mars webpage, and you look under workshops, you will find these reports. And I just wanted to make that statement so that people realize there's an archive of really good work out there that you can go and access on the Explore Mars website. And I really recommend, going back, I reread this report recently and I said, wow, that actually still is very interesting stuff. And you'll note that some of the folks here are also noted and were part of that workshop as well. There we were in December of 2016, I believe out in, I can't remember if that was Washington or California that we met. Oh, that's right, that one was in California, Monrovia. So there's our group photo, and you could do Where's Waldo and find Hoppy and I in there somewhere, and Tim, I think you're there too. But these were the long poles that we actually reviewed at that workshop and wrote the report about. And I won't go through them all today, but you'll see that for one thing, in 9 years, those haven't really changed. We are still thinking about all of those. And today we're going to get the opportunity to do a little bit of a deep dive on 4 of those subjects. I just wanted to point out that on the 4 subjects we're talking about today, these were some of the things that we noted in the report. And I think it's important just to sort of be a stage setter. So for instance, on the transit hab that Hoppy will talk about, you need to have this a lot packed into a small space. You've got to be able to protect the crew from the radiation environment. You want to have things that keep them healthy and productive. Obviously, they've got to have things to eat. And you got to store all the logistics that they're going to need on that entire trip, which is going to be probably around 500 days. So it's a pretty tall order. In terms of EDL, Caleb's subject, that is a tough nut to crack right now because, as folks have described, we've been able to land a pretty significant capability in the Curiosity and Perseverance rovers, but they're about 1 metric ton. To do human missions, we're going to need to land probably 20-ton blocks of payload and multiples of that to support a human expedition. At the same time, you've got to do that so that those things aren't too far apart, because we don't want to have people having to do several kilometer treks to find their spare underwear or whatever other supplies they've got to have that were landed ahead of time. Or the MAV, as was brought up earlier by Jim Green. The MAV is their way off the planet. So these are all things that we consider. And then finally, for surface power, I think this is a really interesting subject because we have seen this actually come to some fruition since we did this workshop, where we've considered over the years the various power options. I think at Mars, the biggest hurdle that we saw for solar power, and we saw this with the rovers, with Spirit and Opportunity, Vice, Curiosity and Perseverance, dust will kill you, and over time, if you have solar arrays as your primary power source. So we believe that nuclear fission is a very enabling power technology for Mars. So at that point, I think, I forgot, the last but most important, my colleague to the left here, human health and biomedicine. This one, obviously, as we talk about humans to Mars, is the one we haven't tackled to date significantly. We've had just a limited number of folks who've actually been beyond the Van Allen belts with the Apollo program. So I think Eric will enlighten us on this because we don't have a big database to go on here. And we've done a lot on the space station, but there again, that's kind of still down under our little protective cocoon in some respects. I'm going to throw it over to you, Eric.
All right, thank you. I think I have some slides if you're able to bring them up. As you mentioned, the number of people that we have sent places and demonstrated a capability to do some of these things with is limited. Less than 20 people have ever flown for more than a year in space. And getting to Mars, our shortest duration mission right now is probably looking like 730 days. The longest we've ever flown one person has been 438. So demonstrated capability and the assumption that folks make about what we can do and what the humans are going to be capable of when they get there, I think are there's a broad gap between those. And so as we start to talk about the significant hurdles, while there's been a huge amount of work by lots of different groups looking at some of the engineering challenges, I think it's really important for us to stop and think about the humans. And they're intimately tied with the engineering systems. So much so that one of the areas that we've really pushed on from the human health and performance side of not only NASA, but other places, is learning and demonstrating that we can do better and better human systems integration. Because in our experience, although we've done amazing things in low Earth orbit to date and even going to the moon, a lot of times the human has often felt almost like an afterthought. And the reason why that has occurred is because we've been able to do good enough, and most of our space flight has been short enough and with enough advantages that we really haven't pushed the humans beyond their limit. So the biggest long pole in my mind, coming from that human health and performance community, is demonstrating that we can actually achieve Earth-independent operations. And the reason why I say this is because the loss of real-time communications puts us into an operating domain that is completely outside of our experience base. And there's other things that you can see up on the slide that start working against us. As we move from low Earth orbit out, we lose a number of advantages. The real-time communications is a big one, and I'll spend a little time on that. The evacuation capability, right? It's almost like our warm, fuzzy blanket in low Earth orbit to say to ourselves that we can actually bring somebody back and evacuate them if they get ill or injured and it becomes a bad day, right? And the other thing that is really concerning is the limited consumables resupply. So the challenges that we have in low Earth orbit, one of the biggest things that astronauts love is occasionally when we can send up fresh fruits and vegetables, right? As soon as you go to the moon with the Artemis program, that's gone. And that's a morale booster as well as a really critical nutrition thing. So a couple of things about the human that we take for granted are things we still haven't solved. We don't have a food system right now that can get us to Mars and back. It's just something you gotta realize we're still working on that. Can't assume that we're there yet. The health and medical system, right? How bad is it gonna be and what are they gonna need to do? But more importantly than that, the humans are the people who maintain and repair everything that goes wrong that didn't get fixed throughout the entire 10 or 15-year design phase leading up to the vehicles and the habitats that we field. So this is out of the NASA's architecture definition document from last year. The ESDMD, Najud Moranzi, they've been doing an amazing job of pulling together not only all the opinions from all the different groups of expertise that need to inform a Mars mission, but also organizing it with a process. And this one, I think, tells a really unique story. Look at how much experience we've had in low Earth orbit. And that is still, by the way, a very small amount of data and information that we've gleaned about how the human system actually adapts to space flight. And it's primarily been done in astronauts who have been primarily white and male and who have been in a certain age range, right? And certain fitness levels. And we've demonstrated a lot there. And we have amazing capability, but taking the next steps is truly next steps, and they're big ones. Going back to the moon, yes, we've had some capability there that we flew in the 70s, that we've now had to rebuild to go back and do that. But also our experiences and our data from partial gravity transitions and the ability to not just go there for a few days like a camping trip, but to start building out sustainably and do things like construction. Those haven't been demonstrated yet. Okay? The spacesuits, the things that are getting redesigned, they affect how well humans work. And then when you look at the Mars domain, where we have 12 successful robotic landings and about 1% of the Mars surface explored, but what do we have in terms of actual human experience doing these things or demonstrated ability, right? And this is why I want to disabuse people of the assumptions that they have that the humans are going to be fine. So what does that mean? We often talk about human health and performance as a specific domain, but I hate using the word performance here because it sounds like we're trying to get the humans to a point where they can be Olympians doing superhuman things. And that's not the case. What we're trying to figure out is how to keep them from being deconditioned in the spaceflight environment over the entire transit time in microgravity and partial gravity at Mars and another transit time back to Earth. That deconditioning occurs as soon as you launch them into space. Then the longer you go, the more deconditioning happens. And most of our human system risks that are shown up here are things that are pushing on the humans and making them less able to do their jobs. And that's really what we mean by performance. Are they going to be able to do the jobs we send them there to do? Because they're getting deconditioned every step of the way. And we need them to do very unique and specific things. We need them for that complex procedure execution. We need them for risk assessment, contingency planning, all the things that go wrong. And what happens today on the space station, if you're not aware of it, is that we have most of the things that they're doing being guided in real time. Most of the problems that arise with the space station are detected by mission control in real time. Most of the analysis to determine what actually happened is performed by mission control on the Earth in real time. And most of the diagnostic and then the next step, what intervention are you going to do, is recommended by mission control real time. So when you take away those around 80 experts working the first hour of a critical situation, because at the farthest between Earth and Mars, we're going to have about a 45-minute round trip communications lag, right? What does that mean for our astronauts' ability to identify problems, determine that they've occurred, deep in these complex systems, diagnose what happened, and figure out what to do about it when they don't have that team of all that expertise supporting them in real time? How do we do that? I mean, we're all hopeful that AI is going to play a massive role in that, right?
Will fix it.
However, we have to see to what extent that's actually going to fix it. Because we can't stuff all the things that are in the brains of all these people into 4 people's brains and expect them to be able to maintain, repair, and in addition to that, do all the science and other things they need to do. So, pointing this out because this to me is the biggest long pole, right? How do we design the systems that actually identify where the crew are in their deconditioning curves, that counteract that to make sure that they don't decondition as much as they otherwise would? And how do we make sure that they have system insight and the ability to take care of their own challenges with system failures? Because on the ISS, one thing that I didn't throw up here is some of the graphs that show how often these things happen. On the International Space Station over the last 20 years, the average for the number of urgent events that probably would have killed the crew if we didn't have immediate real-time telemetry and capability, averages about 1.7 times per year. That's over 20 years, and we got better at it. The first 6 years, it was about 3 to 4 times a year. So we're not talking about this being a cakewalk. We're talking about trying to make sure that the crew can do that stuff that is fundamental to keeping them alive in a massive complex system. And everything that everybody else is going to talk about, the crew is going to either be dependent on or play some part in actually making it happen. Ascent from the surface, it'll be the first time we're asking a crew of 4 potentially to fuel a vehicle and do all the prep work without the ground crew that's there, right? The science that's there. Hopefully we have the scientists who are superstars in their fields as part of that mission, but then they're going to have to also learn how to be mechanics. So this is part of why I see that as a massive long pole and why I'm going to pass this to Hoppy next.
So now, Hoppy, obviously we've set up a pretty tall challenge for that transit hab.
Right,
Let's hear how it's going to work.
For sure. Let's see, waiting for the charts to come up here. But yeah, as both of you pointed out, the transit habitat is going to be a small vehicle. Maybe it's the size of a typical camper somebody takes out, or maybe the size of 1 or 2 space station modules. But it's going to have everything that they're going to need for a mission that might be 2.5 years to over 3 years long, and it's got to have all the food, all that stuff. And so whether that is a solid-walled can, whether it's some kind of inflatable kind of habitat, or whether it's something that's incorporated into the payload area of a starship, it's going to have the same kind of functionality. So if I look on the right side of this chart first, you're going to have to take care of space radiation and having people live in lower gravity, a large distance from Earth. And then there's the aspect of food. And I think it would actually be a great idea if on the transit habitat, there was at least some capability to grow food, whether it's hydroponic tomatoes or something, and maybe not really that significant in nutritional value, but just for morale, to have some fresh food. Because as Eric pointed out, it's a real treat when a cargo vehicle arrives and it has fresh fruit or fresh vegetables, but to be able to grow some of your own and just have that treat every now and then, I think would be great. And telecommunications is certainly a big issue. As Eric pointed out, there can be like a 45-minute or longer round-trip communication time. But one of the things we're planning for the Mars robotic missions is Mars solar conjunction, and that happens in January of 26. So every 2 years, we get all of our Mars projects together, and we have a review, and we figure out all the things that we need to do to get through solar conjunction, because during that time, we can't really communicate with our vehicles for 2 or 3 weeks because the sun is between the Earth and Mars. And so for a Mars mission that's 2.5 years, you're going to have a solar conjunction in that mission sometime. And so, it's going to be even worse than this 45-minute round-trip delay to your team in mission control on Earth. It may be 2 weeks. So they'll be on their own. Certainly that's true for getting data up and down, probably for videos. Maybe you could get some voice comm that might be a little distorted during some of that time, but you'd have to count on them being on their own for a couple of weeks. So that's definitely a challenge there. So once you have a transit habitat and it has all the different things that you need, power, food, radiation protection, you have to get that transit habitat to Mars and back. So whether that's on a Starship vehicle or whether it's on other kinds of propulsion, whether it's a nuclear thermal propulsion system or an electric propulsion system, there are different trades that you can make for those different propulsion systems, and they all have their pros and cons. And I know Tim will talk more about that. But I think one of the things you have to trade off between the traditional propulsion or methane LOX, which is the Starship uses, or LOX hydrogen, or electric propulsion, solar or nuclear thermal propulsion, is you need to trade off not only the performance, but also the risk of that system. There's the risk of developing the system, how much it costs, the schedule to bring that system online, and also how reliable is it. Certainly we worry about things that might hurt the crew due to health reasons going there and back, but another big thing that might affect the health of the crew is if your systems fail, and so you certainly don't want your propulsion system to fail. It needs to be very highly reliable. So that's a key aspect too. So I think that's about all I have to talk about now. And there's a lot that you covered, because a lot of the issues of the transit habitat, we covered at AM4, and you talked about some of those things.
Right.
So I think I'll hand it over to Tim now.
Thanks, Aubrey.
Sure.
So, and I'm going to talk about nuclear power and propulsion. And I think that this is one of the areas that has made a lot of progress since that time that we did the long polls. And I think part of that reason is that nuclear power and propulsion, it's not just for Mars, and it's not just for the moon. It is a capability that, because of the energy density in nuclear, really allows us to do things that we can't do, say, with chemical propulsion or with solar power. Having constant power during the 14-day equatorial lunar night, or because of that pesky rocket equation, trying to do aborts during a Mars trajectory, and you just ending up needing to bring a seemingly infinite amount of propellant. And so we've been working on both the concepts for the long term as well as technology development for nuclear. This is actually a picture from our water-based lunar architecture on the moon of what I would say is the beginnings of industrial scale fission surface power. And those are radiation protection berms that you see there. But we have to start a little bit smaller. And so right now, NASA is getting ready for the fission surface power program to start. And that's super exciting. We're at the point in the technology development we're ready to start a flight program. And the first Mars architecture decision by NASA has been made, which is we will use fission surface power to power the human visits to Mars. And I think it was Opportunity's experience where literally the sky darkened because of the dust storm that really pointed out that for human missions, we're gonna need constant power even through dust storms. And we need it for the moon, and we even need it for Earth. And I think that's partially one of the benefits of nuclear is if we can get to a whole of government development program and flight programs for nuclear power and propulsion, I think there'll be benefits all around. So let me talk about some of that. So the bottom part of the hexagons is the civil, scientific, and commercial missions. The top part is national security. I'll start with human exploration, right? So nuclear propulsion, whether it's nuclear electric or nuclear thermal, can transport humans to Mars 1.4 times faster, and also enables aborts. And we did a paper a little while ago. You get about 50 or 60 days after you leave Earth to be able to turn around and come back, which is really big. And then there's a zone where we can't abort. And then as you get closer to Mars, you can do a maneuver and basically do a quick flyby and come back. But in order to make that work and be able to carry the propellant to make that work, you've got to have the efficiency of nuclear propulsion. And the two types of nuclear propulsion, so nuclear thermal propulsion is where you take a very hot reactor, you flow hydrogen through it, and expel it as a propellant. And we're careful to use propellant and fuel when we talk nuclear. Fuel is the uranium. And that's a relatively simple system. And at Lockheed Martin, we favor NTP for human Mars missions because of that simplicity. Nuclear electric propulsion is where you're making power and you have very large electric propulsion thrusters. And often you need supplemental chemical propulsion to get in and out of the gravity wells. And then high power science and exploration on both the moon and Mars. As we talk about getting to industrial scale on the moon, we're talking about power grids and operating, and transferring power at, 1,000, 3,000 volts across the surface, doing power beaming with lasers, say, from the rim of a crater into the bottom of a crater. And we've been exploring what NASA calls the sustained evolution phase when we're at industrial scale and we're producing propellant for the Mars missions. And I think that NASA's actually advocating we get to that sustained evolution phase on the moon pretty quickly. We've also looked at in-space debris removal, whether we're using high-power lasers to take care of small debris, or we've got an NTP tug taking care of big upper stages. That might be one of our solutions. And then on the national security side, space domain awareness, being able to move quickly through cislunar space is a key mission, as well as being able to do orbital maneuvering or servicing. We can do things we can't really do today, like, okay, let's go into one constellation plane, deploy a couple spacecraft, and let's change our inclination and go to another plane and deploy more satellites, or do really high delta V missions where we're moving fast and we're carrying a lot of payload. And then high power capability, satellites always want and need more power for all the things that they do. And nuclear keeps scaling. Eventually solar arrays they get bigger and they get bigger and they get bigger. Nuclear, because of its power density, eventually is mass and volume efficient compared to solar arrays. But of course, we want to talk about Mars and what those systems might look like. And the way that in space nuclear power works, we don't have a river and a big cooling tower that Homer Simpson works at. we have a hot source, which is the nuclear reactor, and we're flowing some sort of fluid through it to pick up that heat. And then we have an engine that converts that heat to rotational energy that drives a generator. Relatively simple stuff. The two types of engines we're thinking about is a Stirling engine, which is actually a piston that's moving back and forth between a hot and a cold area. And that's good for it's most efficient at lower power levels, sort of 10 kilowatts. And then there's a Brayton engine, which actually has compressor and turbine to be even more efficient at higher thermal loads to create that electricity. And so for just habitation, maybe 10 kilowatts is okay. For a small pressurized rover or a small habitat. But for Starship to be able to take off from the surface of Mars and return home, it needs to make all of its propellant on the surface of Mars. And if you want to do that in about a 500-day window, you need 1 to 2 megawatts of power to make that much propellant from the Martian atmosphere and from ice. So we want to get to scale, and that's where nuclear power really helps. Right now we're developing technologies. We're working with reactor company, particularly BWXT, but the power heat transfer, the power distribution and management, the control of the reactor, all of those things that we're actively working on, and we're ready for flight. We're ready for that fission surface power program. So a lot of progress in the last 10 years since achieving Mars 4. So
that's really great, Tim. Thanks. Well, and of course, none of this works if we can't get it down on the surface and do it in a way that allows the astronauts to access the capabilities that we bring. So Caleb, over to you.
All right, yes, thank you. Another area that's made a lot of progress in the last 10 years, and that is in the HIAD development, or hypersonic inflatable aerodynamic decelerator. So that's what I'm going to talk about a lot today, and some of the new technology that we'd like to use to actually land on Mars. So we started out with the DRA-5 mission. I think a lot of people are familiar with that. We go, oh, that's right, I'm changing it. This is an architecture from about 10 years ago, but still really applies in that you have a series of launches to launch cargo missions, and then another series of launches to support habitat and crew and everything for about that 500-day mission. So what we're looking at here is this, when you take it into really simple terms, it's a large delta V problem to solve, right? You're sitting on the launch pad at 0 kilometers per second, and when you get to Mars, you also need to be at 0 kilometers per second. But you have to speed way up and slow way down in between. And so we're looking at, from an energy perspective, we're putting all this energy into the system, launching hundreds of metric tons over to Mars. How do we slow all that back down and land on the surface? One way you can do it is with chemical propulsion, but where are you going to get the propellant, the fuel, right? You carry it all with you. So now you have even more stuff to launch and more stuff to get up there, more stuff to accelerate to Mars. So instead of doing that, why not use something that's already there at Mars that you don't have to carry with you? It's atmosphere. And we're building a very large drag device. That's essentially what the HIAD is. And we're just going to use the Mars atmosphere to aero capture and slow ourselves down and safely land on the surface. And that's really where the technology has advanced over the last 10 years in being able to develop that capability, these large aeroshells, much larger than what has flown before, a 4 or 5 meter type scale aeroshell for some of the landers on Mars today. So this is what it looks like. Why is HIAD important? Well, it's a deployable aeroshell. It can be stowed in a small diameter and then deployed prior to orbital entry. So just looking at a depiction of MSL there, shown in the Atlas V 5 meter fairing, a rigid aeroshell, you could obviously have a deployable that once you're out of the launch vehicle, you could deploy it to a much higher diameter. The other interesting thing about this is it allows you to land on higher elevations of Mars. So maybe whether this is for a human mission or for some other robotic application, you can build a larger drag device so that when you're descending through a smaller amount of atmosphere, you can still slow down enough to safely land. So this would actually open up some areas of the highlands on Mars that we previously have had trouble getting to. So in a 2009 study, really looked at a few different architectures, and the baseline, number one being rigid aeroshell, chemical propulsion to the surface, and then a lot of series of different options of aeroshells, and hyads and syads, syad being a supersonic version of a hyad, and really landed on this number two architecture, which is have a large hyad for aero capture, and then the supersonic regime, and then switch back to chemical propulsion for final surface landing. So with this, we're at an architecture of about 80 metric tons to arrival and 40 metric tons to the surface for each one of these. And of course, like we said earlier, we would need multiple to get all the crew and cargo there. Little depiction of what that would look like, at least probably 3 vehicles landing somewhere in that 30 to 40 metric ton. The MAB, the habitat, the rover, everything you need for the mission on the surface. So talked about how the technology has really advanced. We actually were able to demonstrate it with a 6-meter hyad called Lofted, which launched and returned in 2022. And so you see the depiction there, the inset there on the left. It was about 1.5 meters when it launched in diameter, and then expanded up to 6 meters for reentry. Largest blunt body ever to reenter the Earth. And this was a successful mission. I'll show a little bit more on the next slide. It launched on the JPSS-2 mission out of Vandenberg in 2022. It did an orbit and then came back just a couple hours later, landed about 500 miles east of Hawaii in the Pacific Ocean. And just picture perfect mission. Everything went super smooth. JPSS spacecraft was deployed. Lofted was along for the ride. And so after the spacecraft was safely in its orbit, we used the commands from the Centaur upper stage to inflate Lofted, separate it, and then send it back to Earth. And you can see it landing there. Recovery team was able to reach it within a few minutes. There was a ship out there waiting for it. And you look at it here on the ship, and it's just in what almost looks like pristine condition. It just really looked almost exactly the same as pre-launch testing. Survived very well. It's basically made up of stacked tori, and then those are strapped together, and then it has a flexible thermal protection system over it. So all of that, it's flexible and can be packaged very nicely. And so we really saw that the tori structure was in excellent shape. The flexible TPS glassified a little bit on reentry as expected, but all in all, this was a really successful mission, and glad to see how good it looked when it came back, and really demonstrated that hyads are a real thing. They can work, they can survive reentry. This was about a 3,000-pound payload. And so what we're doing at ULA is we're scaling this up to about a 50,000-pound payload. And we are really interested in hyad development for Vulcan engine reuse. So I'll touch on that for just a minute, but the neat thing about this is that the work we're doing is already going to be at the structural capability needed to land on Mars. Now, maybe the diameter might be a little bit different. We can talk about that. But the hyad we're developing today is going to be actually packaged around our BE-4 engines on Vulcan. And as we ascend, we'll go through boost phase. Our Centaur upper stage will continue on and carry the payload to orbit. Meanwhile, we'll actually separate off the back end of the booster, deploy a hyad, and re-enter and recover our engines that way. It's a really efficient way of doing launch vehicle reuse. We don't have to carry any fuel with us to do a deceleration burn, fly back, and land. We're using atmospheric drag to slow down. That's what's so great about this, and is that you're using something that's already there. It's free. Deploy the hyad, re-enter, slow down. We do deploy parachutes at the end, land in the ocean, and then bring the engines back, recertify them, and put them onto a new booster. So that's really our application, but again, it works for Mars. So this is really the hyad development over time. Started out with about a 3-meter hyad with IRB-3. Lofted was a 6. ISS down mass would need about an 8-meter hyad. That capability exists. And so there's other applications, whether it's reusable satellites, down mass from ISS or other missions, or our application, which is Vulcan engine reuse, which is about a 10-meter hyad. So again, we've already solved a lot of the problems needed for structural capability on how to build larger tori, the materials that we need to build them out of, how to strap them together, different stacking configurations to get more strength out of or more structural capability out of the aeroshell. Those are all solved. So really, when you get to Mars and you see a depiction of the MAV there landing with a HIAD, it's really just about what diameter do you want in order to get the drag surface that you want. And that's an easy problem to solve. That's just, different diameters of tori. We can do that very easily. So somewhere between an 18 meter, you probably need an 18 meter for aero capture, 16 meter to land. If you had a fueled MAV or heavier mass that you wanted to land, it just larger diameter, maybe up to 23 if you really needed to. And so this kind of just shows lofted up against the inner tori of our HIADs, or our HIAD that we're going to use for Vulcan reuse. The inner diameter of this torus is larger than the outer diameter of lofted. And there's 4 of these, and they just get bigger from there. So this is a really, really big aeroshell, lots of structural capability, and already suited to go to Mars, already would exceed the 30 metric ton capability that you need to get to the Mars surface. This is just a little bit, I think I've mentioned most of this stuff. Lofted was a great demonstration, reduces our risk. The Vulcan engine reuse HIAD is going to do that even more. We've got a credible path to the 80 metric ton arrival and 40. I had 30 on the previous chart, but again, just scale the diameter. You get somewhere between 30 and 40 metric tons to the surface. Use it for aero braking and aero capture. And so just looking on the right there, different concepts of mission architectures, whether it's 2 landings of 30 metric tons, 2 landings of 40, 3 of 30. Those are all kind of decisions we can make as we get the technology ready. So to conclude, HIAD provides a significant benefit over chemical propulsion for landing on Mars. I mentioned that. We're going to use the atmosphere to slow down. We're not going to carry a bunch of fuel with us. Because of the problem that we're solving with delta V at Mars and getting velocity out of the system there using a HIAD, it means fewer launches required from back on Earth. So while we set out to solve an EDL problem, we actually helped a launch problem too, in that now we need to launch less stuff and less mass to LEO and beyond. And so it really helps with that too. And actually, there's an architecture. We can do this with LOX hydrogen systems already ready to go today, which of course, big fan of nuclear propulsion. But if that was something where we said, we want to focus on the power, the propulsion piece isn't ready or whatever, this is an architecture we could actually do with the systems that exist today. Full habitat and cargo infrastructure just delivered in 7. It's really probably closer to 9 launches if you really want to get everything set up ahead of time. And then just want to reiterate that this is a significant technology step. ULA has been partnering with NASA on this. We talked a lot about the NASA budget recently at the start of this conference. And this is one area where ULA sees a commercial opportunity, and we're investing a lot of dollars to make this happen that ultimately can help get humans to Mars. And so we're excited about that, and that this is now starting to see commercial applications, whether it's ours on Vulcan engine reuse or somebody else picks it up for LEO downmass or whatever. This is happening, it's real, and it will be ready to support humans going to Mars because of the commercial investment that's happening today. So we're really excited about that.
Great. Thanks, Caleb. So I would like to invite anyone in the audience who would have questions for this wonderful panel of experts to step up. There's a microphone, I think, on the aisle here. And while you're getting there, I just wanted to kick it off with one question. I think Tim and Caleb both alluded to some really great steps that have been taken in terms of burning down the risks that we see and that we saw back in the workshop 10 years ago. I wanted to throw to Hoppy and then maybe Eric, what are some of the things with the Artemis program that we're looking at right now that we might be able to use in conjunction with our going to the moon to prepare, like the transit hab, Hoppy, and also then Eric, to get some of that data that you were talking about that we need on the humans? So Hoppy, maybe start with you.
Yeah, so the Artemis program is looking at surface habitats on the moon and also for habitats that would be at the gateway and things that might be tested on ISS. And so, Artemis is going to further advance the art of the life support systems and I think also of some of the food systems. Clearly, the Artemis program will have astronauts with more exposure to galactic cosmic radiation. I think it would be valuable to have a series of missions on the surface of the moon or at the gateway, if we still have a gateway, to increase the duration that people are in a deep space type environment, just to figure out what the effects of radiation might be on cognition and other health aspects. And that would be a path forward for Mars. There were some other tall poles that we looked at for AM4. One of them was supersonic retropropulsion. So even if you use the HIAD, you still need supersonic retropropulsion for any of those. But actually, a lot of that risk has been retired because the SpaceX Falcon and also Starship, they've demonstrated supersonic retropropulsion in a regime in the atmosphere that's similar to what you would see at Mars. So to me, that also has retired some of the risk moving forward to Mars.
Great. Yeah, Eric, go ahead.
Yeah, and to add to that, I think that the key thing that we struggle with on the human side is simply data, right? Data to characterize the risk, because how much are people going to decondition on these processes? How effective are our countermeasures going to be? Are we going to be able to even supply the countermeasures that we really want to? Up on the space station, we've had a treadmill, we've had a cycle ergometer, we've had a ARED device for resistive exercise. Do we have the room for all that stuff? If not, how much of a decrement are we taking? And we've just had a small n problem on the human side of this for so long that everything that we can do within Artemis in terms of gathering all the information that we can about humans, their vitals and their capabilities and their performance, is something that helps us to characterize the risk and then understand what we're burning down.
Great. Well, let's go to a couple of audience questions. Yeah, could you say your name and then ask your question, please?
Yeah, fantastic. Thanks. I'm Chris Temby with the Agnostic Life Finding Association, or ALPHA. I have a couple of questions. I think the first is for Mr. Hoppy Price here, is to avoid the loss of comms with crew for a Mars mission during the Mars-Solar conjunction. Is there consideration to put a relay communication satellite at either the L4 or L5?
Yeah. So we've looked at the options of having a relay system that's actually in another orbit, a heliocentric orbit, that could actually be a relay to maintain that. But again, that's a resource that you have to plan for and you have to launch it, so it costs money. But yeah, that would be an option.
Is that a priority or not so much?
Right now, it's just an option.
Yeah, sure. Okay.
Hasn't been prioritized.
Thank you. My second question is about the HIADs. So the Alpha is developing a mission concept called Impress to basically deliver a swarm of probes to really reduce the EDL complexity to enable high mass to the Martian surface. With the HIAD architecture, I'm not exactly sure how you're planning on landing on the Martian surface. Is there a chemical propulsion, basically final stage? And do you plan to also dish the HIAD right before that? Or maybe we can have a more in-depth conversation about that as well.
Yeah, there is a chemical propulsion for final landing, for final deceleration and landing. Whether or not you ditch the HIAD, that's open. There's certainly ways you could design it where you leave it, but you'd probably want to keep it all the way down. On engine reuse, we're using it because it doubles as a boat. So it's actually it actually keeps us floating in the ocean. There could be some benefit similar to that for landing on Mars, where maybe it's kind of your soft landing airbag if you wanted to dual purpose it. But yeah, you'd probably keep it attached.
Fantastic.
Great. Thank you
all so much.
Thanks.
Hello, this is Issam Mehmed. I'm a reporter with Agence France Presse. Perhaps for Dr. Antonsen, I know this panel is about sort of the first steps, and we're talking about the 500 days, but just wondering, with looking over the horizon, is there any sort of existing research on the minimum G threshold for successful human reproduction, mammalian reproduction, and embryo development and live birth, which would be necessary for the future colonization of Mars?
So no is the short answer. I think there's a lot of people questioning about that. I'd say that the Human Research Program at NASA is an applied research program. That's been the dominant funding source for what we're doing human-wise. And space biology at NASA Ames has also had some role in trying to understand that at the animal level. But the Human Research Program has never looked at that because it's never been a key part of planning for the first mission to Mars. And so I know that got a lot of notoriety from the book, Building for Mars or Building a City on Mars. That's just a lot of we don't know is really what's out there. And so if and when we get to that point, and I think it's really important to take that seriously, because even if you don't plan on having it happen, people are still gonna have sex and somebody might get pregnant, right? And then it becomes a medical issue. So it does need to be said that this is an important topic that needs to be looked at.
Thank you.
Thank
you. How much stuff is in the space between Earth and Mars that could be scooped up and used, like if any?
Yeah.
Hydrogen, dust, whatever.
Ramjet technology.
Yeah. So people have done studies on like the interstellar ramjets trying to use the hydrogen as fuel, and I don't think any of them have ever really worked out when you actually look through the nuts and bolts of how that would happen. But for practical reasons, for going to Mars and back, over the next 100 years or so, I think we're more worried about trying to avoid the stuff in between here and Mars rather than trying to use it for something.
Yeah, it would be amazing if there was an ice-rich body somewhere there.
Right, we could just go tap.
But so far we haven't found that.
Well, yes, so there might be some ice-rich bodies, but the delta V to get to them is really high. They're not really on the way.
The payoff isn't there, right?
Yeah.
Next.
Yeah. So my question is about, in the EDL, you said for the last stage you would use chemical propulsion. Is there a reason why it's chemical instead of a nuclear or some other form of propulsion there?
Yeah, just the impulse that you need very quickly. I think it'd be chemical. I mean, I don't know if you've even looked at something like that, but.
Yeah, nuclear propulsion is best suited for when you need a lot of delta V and in actually a pretty long amount of time. So really high energy states is when you want to harness that nuclear so you can be super efficient. The terminal descent propulsion, you don't actually use that much propellant. You want it to be reliable.
High thrust.
And high thrust. And so it's not that big a deal to use chemical, and that's the right tool.
Yep.
All right, our final question.
Sorry, I'm loud. My name is Dr. Alexandra Arce, and my question is directed to Dr. Antonsen. So given the issues that crop up with human health and performance in space, particularly how human health is affected by microgravity, issues with inflammation that develop, and given the logistics of long-term space missions and the impacts that have on long-term human health in space, I noticed that you are trained in emergency medicine. And from what I've noticed is that a lot of programs, a lot of the current space medicine fellowships that have cropped up are mostly directed at emergency medicine physicians. I'm mostly complaining because I'm family medicine. But generally what I'm trying to ask here is, if everything we're looking at is, holistic in nature, if what we're looking at is systems medicine to some degree, how are we better able to open up the entryways for physicians from other disciplines to get involved in this? Because if what we're looking at is at the totality of human health, and people with experience in IBS and IBD are able to contribute to understanding the gut microbiome and how that affects human health in space, how do we get those people involved?
So I'm going to try to give a short answer, and I'm happy to talk to you, because there's a lot of things that you just touched on there. I'm happy to talk to you more outside afterwards, but most of the actual space medicine that's been done to date, the training programs have been actually founded in preventive medicine. And the way that we've selected astronauts have been to select people out, not to select people in. And it's a barrier that commercial spaceflight is breaking now because their business models depend on selecting people in. Probably for Mars, which is a little bit different from the LEO economy developing, it's going to be a different story, and we're going to have to see how that weighs out. But it's actually been a very transition to including broader physician training in this to go to emergency medicine in addition to preventive medicine.
So we'll talk more outside.
Yeah. Thank you. Please help me thank our panel. Thanks, guys.
Thank you, Joe and everybody. That was terrific. So I think it was in 1986 or 1987, I was going in a bookstore, and I came across a book called The Case for Mars. And I'd always been interested in space, but I was working as actually in a research library as an archivist. But I'd always wanted to get more involved in space exploration, and I read The Case for Mars by Robert Zubran, and it really kind of enlightened me on that it's not just the engineers and the scientists we need, but policy people. And so within a few months or a few weeks after that, I'd reached out to the National Space Society and eventually ended up joining the Mars Society, which of course Robert Zubran founded and is the president of, and eventually took over the politics of the organization and eventually was the executive director for about 18 months, I think, at the Mars Society. During that time period, worked with Robert on a lot of different programs, lots of conferences, including we did a lot of political work. I remember talking with Robert back in the 2000 campaign. We created a program called Operation President, where we ended up speaking to every presidential candidate. And in the end, the Mars Society, our work with the Mars Society, actually ended up playing a significant role of getting Mars on the agenda, where it is right now within the administration, the Bush administration at the time, and it's remained official U.S. policy since then. So, at any rate, I'd love to bring on the stage Dr. Robert Zubran to talk about his perspective on how we can get to Mars. Thank you, Robert.
Thank you, Chris, for that kind introduction, and thanks to all of you for coming to this conference. And I should mention, by way of advertisement, the Mars Society is having our conference at the University of Southern California, which is in Los Angeles, October 9th through 11th. You can find out more details about it on our website, and also there's an open call for papers if you have something you'd like to say about Mars exploration. And also, if you're interested in finding out more about my ideas on how Mars exploration can and should be done, I've of course written a number of books on it. My best one is The Case for Mars, new revised edition. And I'll have a few of them on sale when we're having lunch. So if you want to pick one up, you buy it, I'll sign it. It's great. All right, so I want to talk about how to make the Mars initiative a success. We have a unique, potentially generational opportunity right now to get a Humans to Mars program actually started. But the question is whether it will be carried off successfully. That is the reason why we have an opportunity to get it started, and a very good opportunity. I would think the chances are actually quite high right now that we will get a Humans to Mars program started, is because of Elon Musk has achieved a position of tremendous influence within the current administration and has gotten them, Trump has said in his inaugural address, he's going to send humans to Mars. And they are rapidly moving on developing the Starship, which creates a technical foundation, it creates a good part of the technical foundation needed to send humans to Mars. However, there's a lot of problems with this program as it's currently conceived. And in fact, I believe as it's currently conceived, it will fail. And in order for this program to succeed, it has to be put on the right political, intellectual, and technical basis. And so I am going to address all three of those points. Now, as I said, the political basis to start the program actually exists. But Musk has defined himself in a hyper-partisan fashion. And by the way, not just here, but internationally. And if this program is conceived of and remain conceived of as a Musk hobby horse, it will fail. It will be destroyed as soon as the fortunes of political war shift, which could occur as soon as next fall, and to some degree are certain to change after Trump leaves office in 2028. So this thing has got to be changed from a Musk program into, at minimum, an American program, okay? And better would be a free world program that helps pull together the nations of the free world. I do not believe at this point that a fully international program of all the nations together is a realistic proposal, but I do believe that if with proper leadership, this could be made a program that pulls together and is participated in by all the nations of the Western Alliance. However, at a minimum, it has to become an American program, not a Trump-Musk program. And I want to be very clear about this, because there's a lot of people out there, maybe not so much in this room, but a lot of people are listening to this out on the internet who think that Musk can do this all by himself, and we don't need NASA, this is all going to be done by good old Elon. Okay, that's not happening. Okay, it's not happening for a number of reasons. Okay, because while Musk is developing, and of course yesterday's flight was not fully successful, but they're making incremental progress, and I think it's a fair bet that Starship will reach orbit this year. Okay, but he is developing the single most important element of the Mars mission. There's many other elements that need to be developed. All the surface systems, including, as noted, surface power, my calculation is that to execute the Starship mission as Musk has defined it, it needs at least 600 kilowatts of surface power, which has got to be nuclear. It's 12 football fields of solar arrays, and they'd be unreliable because they'd have no power in a dust storm. It's got to be a nuke, and to develop nuclear power requires government involvement, because space nuclear reactors involve highly enriched uranium-235 or else plutonium. These are tightly controlled materials. That's a government job. And many other things that need to be developed, like surface spacesuits, surface vehicles, the ISRU equipment itself, one could go down the list, while they could be developed privately, won't be, because a launch system has a commercial basis outside of the space program, and it can be developed commercially. But Mars surface systems right now really don't have a commercial basis. It's a job for the government. So this needs to be a public-private partnership. And beyond that, okay, there are so many things about this mission that even if Musk could develop all the technology, requires a favorable government environment. Because, for example, existing planetary protection rules could be interpreted by those hostile to the program to simply forbid it. Okay? Existing planetary protection rules would rule out landing humans on Mars, full stop. Okay? You actually have to have the US government, at a minimum, wanting to do this, and foreign governments not want to intervene against Musk, and well, in other words, we want to have this be an American program. We want everybody on board. All right. Now, this gets us to the intellectual basis of the program. Musk describes his program as an effort to create a city on Mars which will allow humans to survive after the Earth is destroyed. Okay. Now, he gets this. His intellectual basis for this comes from the Isaac Asimov Foundation trilogy, which, if you haven't read, it's a great read. I'm all for Isaac Asimov, but it's wrong as the basis of a Humans to Mars program. Now, in that trilogy, what happens is there's this grand galactic empire, and this one scientist, Harry Seldon, realizes that it's going to collapse, and so he gets together a bunch of scientists and put them on a planet called Terminus at the far edge of the galaxy, and they're to be there to reemerge and reestablish human civilization after the galactic empire collapses. That's the plot line of Foundation. And this is where Musk is coming from, and he even calls his proposed Mars city Terminus. Okay? Now, this is a false basis for a Humans to Mars program. It's false technically because, first of all, a Mars city of 1 million people could not survive as an autarky. Frankly, the United States can't survive as an autarky. That's why the stock market crashes every time Trump says he's going to try doing it. But certainly a 1 million person city would not have the division of labor and technology required to manufacture all the things to sustain a modern technological civilization. The artifacts that you have are created by a worldwide division of labor of 8 billion people, and absolutely could not be created in a city of 1 million. So a Mars city, and I believe there will be cities on Mars, and I think initially the cities on Mars will be tens of thousands, not millions. There were a couple of person cities on Earth, like Rome, but million-person cities were not common on Earth until there were railroads, because you need long-distance transport to bring together the materials needed to sustain 1 million people in one place. But in any case, the technical basis isn't there. But in addition, the rationale is repugnant. Okay, we are not going to Mars to desert the Earth. Okay, we are going to Mars in order to establish, I mean, when we go to settle, okay, which follows exploration, but if we're talking about the issue of settlement, we're doing it to establish new branches of human civilization which will add their creative capacity to that of humanity as a whole, expanding our ability to deal with challenges of all types, including, yes, extraterrestrial challenges like asteroid impacts, but also all sorts of technical challenges. America, as a new branch of Western civilization, invented, steamboats and telegraphs and centrally generated electrical power and light bulbs and airplanes and nuclear power and computers and the internet and iPhones. And the same Mars could be a great creative addition to human civilization. And that's why it's important for humans to settle Mars. But going there to hide, okay, going there out of despair. We're not going to Mars out of despair. We're going to Mars out of hope, okay? And, rather than the people there being viewed as like the heroes of Foundation, be more like the protagonists of Edgar Allan Poe's story, The Mask of the Red Death, who go into a castle to party while everybody outside dies of the plague, okay? So this is not what it is, okay? Now, while, as I said, the goal of Mars settlement is to create is to expand the capacity of humanity to deal with all challenges. The immediate goal that I believe can get buy-in, that can make this program bipartisan, is science, okay? Because human explorers on Mars and the heavy lift and heavy payload delivery capability that is a necessary precondition for humans to Mars could be an enormous boon for science, as I've said. And see, look, right now, with this program being pushed at the same time that this administration is pushing on killing NASA's space science program, in particular, essentially zeroing the Mars science exploration program, because they're canceling sample return, but not proposing to replace it with anything else. I mean, there is a valid case for replacing sample return with, 20 smaller exploration missions, landing rovers and helicopters and things all over the place. You can make that argument, but just canceling it and having nothing, that's a disaster. And and basically, they would be putting the mark of Cain on the Humans to Mars program, as it would be seen as not merely a must thing, but a must thing that murdered American space science. Okay, so it would be dead. Instead, we have to make this program be seen not as the enemy of space science, but as the welcome best friend that space science ever had, and I will explain how that can be done. Now, I'm going to get a little bit into the technology. The Starship plan, direct flight to Mars, direct return from Mars, is a variant of the Mars Direct plan, which I first laid out in Case for Mars and some papers that preceded it back in the 90s. However, instead of coming back in a relatively small Earth return vehicle, which required a 100 kilowatt reactor, the Starship is much bigger and require at least 600 kilowatts of power. Okay, and that's a big challenge. Now, I also should mention that the Starship architecture for Artemis involves depending upon how it's done, between 10 and 14 Starship launches to launch Starship to orbit, refuel it on orbit, get it to lunar orbit, refuel it in lunar orbit, then land it on the moon and come back. And that's because while Starship is potentially quite attractive as an Earth launch vehicle, it is extremely unattractive as an ascent vehicle for use on the moon or Mars because it's so heavy. It's 100 tons compared to the Apollo LEM ascent vehicle, which is 2 tons. You want something smaller. And what that smaller thing is something I call Starboat. Okay, Starboat, as I conceive it, would be something a lot like Starship, except much smaller, at least a factor of 5, perhaps a factor of 10 smaller in mass. And so, which is, say, a factor of 2 to 3 smaller in linear dimensions. If for the lunar architecture, you would deliver Starship to lunar orbit, and you'd have a methane oxygen-propelled Starboat that could go from orbit to surface and back, and Starship operating in lunar orbit as a tanker for it. That would be a vastly more effective Artemis architecture. Similarly, for Mars, okay, if you want to do direct return from the Martian surface with Starboat, and Starboat is scaled down by a factor of 5 compared to Starship, then instead of needing 600 tons of propellant, you'd need 120 tons of propellant, and you could do that with a 120 kilowatt reactor. Okay, if you use Starboat not to go from Mars surface to direct return, but to rendezvous with a Starship in Mars orbit, you only need 50 tons of propellant, and therefore you need 50 kilowatts of power to make that propellant, which is something within the range of extensions of the kind of technology that NASA is looking at now, tens of kilowatts per reactor. A couple of such reactors would get you to 50 kilowatts. Okay, so that's what is needed. Starship plus Starboat gives you both the moon and Mars on a technical basis. Now, I've talked to Musk about Starboat personally, and he just says, oh, what do I need it? Show me, prove to me why I need it. I only want to develop one flight system. Well, it's not fine, but that's how it is. I believe that the National Lander Program needs to be repurposed. That is, the lander that is funded by NASA to support Artemis, which unfortunately, given that they were already funding Starship, they should have insisted that that use a methane oxygen propulsion system to make it compatible with Starship. But since NASA's motivation for funding the National Lander was simply a concession to get Blue Origin and Lockheed Martin out of their hair because they were screaming about how they didn't get a contract, they just gave them a contract for whatever they wanted to do. Okay, I believe that I actually am acquainted with the management at Lockheed Martin, and I believe they would be quite happy with a multi-billion-dollar contract to make it methane oxygen. Some of the engineers might have been upset that their pet ideas were not adopted, but for management, money's money, and and that's the lander that we need. That's the correct architecture for Artemis. That is the correct architecture for Mars. Okay, now that's technology. Now let's get back to this thing. Musk is right now claiming he's going to land an unmanned Starship on Mars, launched next year, and then a manned mission launched in 2028. That's nonsense, not going to happen. To launch a Starship to Mars requires not only attaining orbit, it requires developing the tanker Starships, developing the methods to do on-orbit refueling of the Starship, which would be at minimum at least 3 tankers, assuming it has a 100-ton delivery to orbit and the Starship only has a dry mass of 100 tons. If those targets deviate from that, more dry mass, less payload, you get to 4, 5, 6 tanker launches needed. And they all have to be done within the appropriate window. And then it has to do accurate interplanetary flight, re-entry, and landing on Mars. Okay, that is not happening in the next 14 months, okay? Now, with tremendous drive and ambition, and Musk certainly has drive when he wants it, and if he could focus on it, I believe it is possible to do that, to launch such a mission as a one-way unmanned mission in late 2028. Okay, now, however, The contents of that mission should not be a Tesla human mannequin robot. Okay, I mean, it was all fun to launch Starman in a Tesla thing when they were just using Falcon Heavy to show that it could throw something heavy on Trans-Mars trajectory. Okay, it was cute. Okay, but if you're going to be able to land, I mean, forget 100 tons. Let's say Starship's real capability, Musk claims the Starship could land 100 tons on Mars. Let's say really it could land 30. That'd still be tremendous. That's 30 times what we can do now. What do you do with 30 tons landed on Mars? You send a robotic expedition to Mars. Okay, instead of landing one rover on Mars, you land 15, and you land 15 helicopters too, and not tiny little ones like Ingenuity, but much more substantial ones that can each carry, say, 50 kilograms of instruments. And so we go from the Sojourner class helicopter to the Spirit and Opportunity class helicopter, and they can fan out, and the rovers and helicopters can go all over the place, bring samples back to the Starship lander, and where you would have a well-instrumented static lab, and the samples can be brought in there and looked at, by 12 different instruments or 50 instruments, and now you have all these different rovers and helicopters and the drillers and life detection experiments and all sorts of stuff deployed on Mars. You're talking about a Mars mission with at least, at a minimum, 100 times the punch, science punch, that the kind of robotic missions we've been able to do to date. And what you'd have with those 15 helicopters and 15 rovers and the other experiments is literally hundreds of science teams, because there's a science team associated with every instrument that's on a rover, okay, that'd be part of this mission. And therefore, you would get the overwhelming support of the science community for this mission. And not just because you're giving people money, okay, but because you're actually producing terrific science, okay? And that would get the public support for this mission. And that's what would make this mission and this program something that would have enduring both scientific community and widespread public and political support, okay? Because people would be able to see that this is not being done as the whim of an eccentric businessman, but something which is truly grand, something truly worthy of what it is doing. And people would see in general that this heavy lift capability, low-cost heavy lift capability that Starship represents enormous opportunities for science, for much bigger space telescopes and all the rest of that. But if you're going to do that, okay, if we're going to send a robotic expedition to Mars in 2028, you can't be cutting the Mars program now. In fact, you need to be expanding it, because the development of all those rovers and helicopters and the instruments for them and all the rest of that, okay, costs money. So if this is incoherent, what is going on? We should be planning robotic science expeditions using Starship. Okay, 2028, some people may say that's ambitious. Well, in that case, it could be launched in 2031, and that's certainly possible. That this needs to be a coherent strategy where we take the imminent arrival of heavy lift and heavy Mars payload delivery, and we say, we're going to exploit this by developing the robotic instruments, that is the actual rovers and helicopters, as well the scientific instruments that go on them, to have a grand scientific campaign on Mars. And then if the Planetary Protection Program people should come up and say, but wait a second, you didn't sterilize the Starship on orbit, they say, go away, okay. Right. Whereas if it's something that you don't want to happen, you say, hey, that sounds like a good reason to cancel the launch. And that's where this is, okay? That's where this is. So this is how we get the nation behind it. This is how we get tremendous science out of this program for real. And of course, yes, this it prepares the way for humans to Mars, conceivably in 2033, which, by the way, is an excellent launch year, and which I do not believe is unfeasible if we adopt this approach. That's 8 years from now. We went from Kennedy's speech to landing on the moon in 8 years, and frankly, from a technical point of view, we are far better prepared today to execute this program than they were to send people to the moon in 1961. 1961, we had 15 minutes of human spaceflight experience. We didn't even know if people could eat in space, okay? Okay, so this is how this can be done. This is how it should be done, and this is how it must be done. Thank you. And I see I have 5 minutes, 5.5 minutes left. So let's take some questions. Are there some questions from the floor?
Hello, Robert.
Jan, yes.
Yeah, I'm Jan Spacek from Alpha Mars and Foundation for Applied Molecular Evolution. This was great talk, very inspirational. One thing you didn't mention was geopolitics. We, of course, know that China plans sample return from Mars. And that means that maybe in 2031, when they bring the sample back, we will know if there's life on Mars or not, and China will find it. So maybe if you can comment on this geopolitics situation.
Well, I think that the program that I outlined would be a far more potent science program than bringing back a couple of kilograms of samples from Mars. If somebody brought back 5 kilograms from Earth, would you know that there were whales on Earth, or elk, or birds? No, or people for that matter. No, the idea that you could characterize Mars with a kilogram or 5 kilograms of samples is, I mean, obviously it would have some scientific value. I'm not denying that. But it wouldn't compare to this, okay? If we had this kind of robotic expedition on Mars with, 30 exploration rovers and helicopters and, and a bank of instruments there, and by the way, there could be immense broad participation in this mission because the whole territory of the area could be mapped out with virtual reality, and people from the public could go and be looking around the area and say, look, there's something really interesting on the north side of this rock. Can you send a rover over to it and see what's there? This would be exploration on a grand scale. And this would be doing, once again, what Apollo was, which is Apollo didn't send people, or didn't just send people to the moon. It astonished the world with what free people could do. That's what the purpose of Apollo 1, that is what it did. Okay, that's what Artemis will not do, okay? But that's what this will do. And I mentioned, though, that this architecture does enable you to do the moon as well as Mars. And that's important because in addition to the people who are adverse to Musk or Trump, there's another set of enemies that this program could have, which are the moon freaks. Okay? And if they see this program as causing the end of their program, they'll also be against it. So we need to have a program that gets everybody on board, and that's what this would be. Sir.
My name is Doug Gage. In addition to your rovers and your helicopters, how about some orbital assets being deployed at the same time? For example, a successor to MRO and communications relays and a complete weather coverage for Mars.
Well, that could also be done. It depends somewhat on the architecture. If the Starship was to capture into Mars orbit before it lands, then clearly you could deploy a bunch of satellites too. Or you could have a second Starship that is assigned to that task, and then you could have a whole bunch of orbital assets deployed as well. So that's a very good point. That could be part of this. Next question. Any other questions? Well, I actually finished ahead of time. So once again, if you want to know more about how I think Mars missions can and should be designed, got my book. And otherwise, please come to our conference, Mars Society at University of Southern California, Los Angeles, October 9th through 11th. And there are more details, including an open call for papers at marssociety.org. Thank you very much.
Okay, so now to take us into lunch, we have an exciting panel on a topic I think we've all been hearing a lot about lately. How big a priority should beating China back to the moon be? And to moderate that panel, we're very pleased to have Kara Kunzman. She is with the Aerospace Corporation. She's the Director of Strategic Foresight. And she has held positions prior to that with General Atomics and Raytheon. And my favorite line here in her bio, though, was she's been declared a mad scientist by Army TRADOC. So I'd love to hear more about that, maybe tonight at the whiskey reception. But of all, most important of all, Kara got her undergraduate and master's degree in aerospace and aeronautics and astronautics at my alma mater, Purdue University. So boiler up, Kara, come on out and bring on your panel. Thank you.
All right. Never mind. Yes, Scott's here. All right, everybody, we're just waiting for Dr. Pace, who's in the back. I didn't practice my tap dance, but I certainly can get started and kind of contextualize some things. So we're really, really excited for this panel. Come join the party.
Thank you.
Yeah, what's your stuff here?
Sorry, doing the absent-minded professor late to
I
class
mean,
kind of
this
thing.
is-
You give me
this is the
10
drill.
minutes and then everybody leaves.
Yes, this
Yeah,
is the
okay.
drill. This is the drill.
I know the
oh my
drill.
gosh, we're so excited for this panel. Who do we have here today? We have Dr. Scott Pace, Director of Space Policy Institute at George Washington University, Dr. Namrata Goswami, Professor of Space Security at Johns Hopkins University, and Todd Harrison, Senior Fellow at American Enterprise Institute. So why are we here? So as we're looking to 2030, China's relationship with the moon is becoming increasingly central to its ambition in space exploration, symbolizing both technical prowess and an integrated part of its larger geopolitical strategy. Through Chang'e's lunar program, China has achieved landing on the moon's far side and returning lunar samples, and plans to establish a robotic research station at the lunar South Pole by the end of the decade. This positions China as a major competitor to the US, which has led its course in leading the Artemis program in partnership with allies such as ESA, Japan, and Canada, with a focus on returning humans to the moon for laying the groundwork for a sustained presence. So that brings us to this very important question today, which is how big of a priority is it to be beating China back to the moon? And we left this question very ambiguous on purpose, and you guys can feel free to fight the question in your responses. So before we kind of dive into some of the meaty questions, I wanted each of you to kind of just provide your perspectives on what you think this should be, and also kind of in the context of, if we were answering this last year, have our perspectives changed, just everything going on in kind of the political and geopolitical environment? So we're just going to go down the line. So Dr. Pace, we'll start with you. That's the clicker.
Okay, and let's see, we have a chart.
Yep.
Let's go back. Okay, yeah, so I sort of feel like there's a standard joke about the grandfather who worked on Apollo and his grandson, Granddad, what did you do during the great moon race? And the grandfather says, glad you asked that. First view graph, please. As we're limited by these things. So what I want to talk about, of course, is this phrase about China, a new moon race. One of my colleagues, Dean Cheng, wrote a paper, a little monograph called China, New Moon Race. But I got to tell you, I don't like the term moon race. And the reason I don't like the term is not because I don't think there's a competition going on that's of, I think, existential importance, but because moon race kind of conjures up a particular geopolitical time and condition of the 1960s, not only with the Soviet Union, but also with working on influencing the aspirations of newly independent countries that had been coming out from under colonialism in the 1960s. They were becoming members of the UN, they had votes, and so we were pursuing a geopolitical problem, or Kennedy was, and the moon race was part of that particular time. So we have another competition going on today, again, shaping the international order, but to my mind, a moon race is a little too simple, and it implies that there's actually an end with flags and footprints and we all go home, which I hope is not the case. So very, very briefly, try to run through this. China does write about what its ambitions are, at least publicly. They'll have a series of white papers that come out about every 5 years, and they talk about them. This, of course, is not totally complete. The PLA doesn't really talk about some of its military space ambitions in quite unambiguous terms. You have to do more work to do that. But China does lay out a space white paper that's pretty clear. In contrast, Russia really doesn't. It's very striking how Russia does not have really a vision for the future in the same way that most other countries do. It's a separate discussion. Human spaceflight has a high degree of symbolism, I think, as we all know. And not only was that true in the 60s, it's true today. And a lot of the Chinese space achievements are for reasons that are very understandable. Of course, a source of nationalist pride, prestige for the Communist Party, support for party objectives in terms of economic, scientific, and sort of soft power kinds of development. Social development, some of those posters down there on the bottom, the last places where the hammer and sickle is used unironically. Picture in the center, almost a vaguely Christian iconography. It's fighting against superstition, which is kind of a shot at Falun Gong. And then placing China's achievements today in space in the context of several thousand years of history. So the Chinese National Museum, starts at the beginning and it winds around the room till the end is of China expanding into space. Of course, they're in space. There is a Chinese space station. Perfectly reasonable looking design, somewhat familiar, sort of like if, Mir was upgraded. They have, as someone said, it has that new car smell to it. It's nice. Of course, the U.S. International Space Station has, wires and things hanging down. Kind of looks like the Rebel Alliance, inside. We have Chinese astronauts that are quite active. They're rotating crews. They went from not having any humans in space, 20 years ago, to routinely doing crew rotation exchanges. So they've certainly mastered that. They have a fairly steady program for lunar exploration. So the Chang'e missions, of course, landing on the moon, doing sample returns. And one of the things you see is a high degree of technical inheritance between each one getting bigger and bigger and more sophisticated. So I have no doubt that if there is a human landing on the moon, it will be in a lander that will have a technical heritage that traces back to what's been demonstrated in multiple landings at smaller scale beforehand. So a fairly steady step-by-step approach. They have this concept for an international lunar research station. I went away. Do I exist? I don't exist anymore. Am I still back there?
I feel like I heard the meter go off. Did we lose?
Nope. But the thing about the International Lunar Research Station is that it's very heavily robotic oriented. Yes, there'll be humans visiting there, but you could certainly make an argument in terms of sustainability. The Chinese approach, thank you. The Chinese approach is probably more affordable, more sustainable than many of some of the concepts that we have. More modest in many respects, but I think more attuned to current geopolitical reality, which is about being there. We have influence over, say, the Antarctic Treaty System because we put 3,000 people on the ice every summer. We're there. It's not a matter of, nobody remembers the 2 Norwegians that got there first. They do remember the fact that, and understand the fact the U.S. and its friends and allies are a big part of what shapes how you actually operate in Antarctica. So sometimes people have heard me say, well, the rules are made by those who show up first. I really don't say that anymore. I say the rules are made by those who show up. And if you stop showing up, then you get less say in what goes on. So the Chinese have a way of trying to be there in a longer-term sustainable way. Various development phases, we can talk about. Everybody loves doing rocket design. And their space science approach also has this kind of like phased approach. They're not looking to replicate things that have been done before, but they are looking to find areas where they can carve out something new. So landing something on the far side of the moon that we hadn't done before, which then requires a relay satellite. Doing science missions that hadn't been done before, looking for niches where they can claim things that are unique to themselves. Some cases they'll repeat things that have been done before, but they're not being unthinking about that. They are looking for areas that they can claim as special Chinese contribution. And so we end potentially with a vision in and around the moon of a lunar research station, probably has some international participation in it. And in this environment, the question is not what are the Chinese doing, but what are we doing? And who else is there with them? Let me pause there.
Wow. Wow, that was surprisingly succinct. Great job.
Surprisingly. Thank you, Kara. Thank you.
Dr. Goswami, I'll hand it over to you.
Yeah, absolutely. So first of all, thank you for that fantastic overview. And I do have to issue a disclaimer. Everything I say is my own opinion and does not represent the perspective of the US Space Force, the Air Force, or the Department of Defense. So what I'll do in the 5 minutes I've given is to offer you answer to the question you asked, that if you had asked this question a year before, would it have been different? Yes. So I would argue that something very interesting happened. And I just got back from Japan. I also went to India recently. And what is interesting is that the global narrative has totally changed from last year to this year. And there are two events that have actually changed that specifically in terms of the moon. One is India's landing, of course, in August of 2023. But last year, China actually did something very interesting, and for the first time for any nation, they went to the south pole of the moon and returned with samples. And then they offered those samples to be studied or researched by universities across the world. So what this has done is a fundamental shift from last year to this year. Last year, there was still questioning whether China is actually serious about some of the programs it's talking about. For example, lunar resource utilization, studying lunar regolith. Are they really serious about going to the South Pole, since no one has done that before? And so once the capabilities have been demonstrated, I noticed this extreme interesting narrative in Asia, for example, by major spacefaring nations like India and Japan and middle powers that, wow, China is actually shifting the narrative in terms of how important is the moon. The second interesting thing, which I noticed specifically in regard to the moon and China-US, is that there is interesting development at three levels. One is, of course, the civilian space program, which includes all the programs Scott talked about, for example, the Chang'e missions. But then what is China doing is that they're also demonstrating logistics infrastructure capability. So besides doing sample return, going to the moon, autonomous docking, using artificial intelligence, 3D printing, they're also showcasing and very transparent about, for example, a lunar retrograde orbit. So just last month, they actually gave you the pictures of that they had successfully done that. What they also are pointing out is that in terms of infrastructure, so the narrative is set and then the infrastructure, is that they are serious about building communication and lunar time zone, for example. We heard in the panel before us the importance of relay communication if you go to Mars. So you can see that China is serious because they are the only nation that has a relay capability, for example, on the Earth-Moon Lagrange point. And then the fascinating thing in terms of policy and institution is that they're talking about going to the moon as an infrastructure project. It is not really about human landing. They do put human landing there, but their argument is that, well, actually, we do want to build permanent presence, and what Scott pointed out is the International Lunar Research Station, which is a permanent capability, and so infrastructure. And then finally, they are not actually afraid to talk about how such capability can improve China's power projection capability. So they do argue that this can have effects, for example, in military power capability, for example, the utility of cislunar space. The People's Liberation Army Aerospace Force, very interestingly, gave a press conference, and I'll end with that, and that is different. This was impossible a year ago, right? But now they have restructured their military. They have a new service, which was a continuation of the PLA Strategic Support Force, but much more focused on space. And the spokesperson of that particular service, when he talked about it, argued that, well, the PLA has a role to play, for example, in China's power projection capability. It includes zones that they identify as vital, low Earth orbit, geosynchronous orbit to cislunar space. And then he points out that, well, we also have a big role to play in terms of shaping the governance structures. And this is a military representative. So I think I found all that insightful, and coming from such direct source, very fascinating.
Yeah, thank you so much for that. All right, Todd.
Yeah, no, I guess, yeah, I agree with a lot of what the panelists have already said today. What I would want to put a finer point on is what has changed for me in the past year in terms of the reason, the justification for why we need to be in this competition with China to get back to the moon. A year ago, if you'd asked me this question, I would have said, you know what, The competition with China to the moon is part of a much broader competition with China, a geopolitical competition in all domains. And even the race to the moon, if we want to use the word race, that is even, just a part of the overall competition with China in space. I would argue, and I've written about this before, that it's not just a race to the moon. It's really like the Space Olympics, right? Where we're competing in commercial space, we're competing in military space, counter space, and science and exploration is definitely part of that. And the moon has been the main focus until now. And I think the reason, the main reason to go to the moon right now is not just to beat China, because it's not about putting flags and boots on the moon, right? It's not a destination, it's the journey that's important. It's how you get there, right? And so I think the competition to the moon really should be about who gets there with the biggest and the broadest consortium of nations. Who brings the biggest alliance network with them to the moon, because they will have much more influence in the long term for how precedent is set and for how lunar governance and the infrastructure and all of that works. So you want to get there with the biggest and broadest alliance possible. You asked me that today, and I think that justification has been completely undermined. Whereas a huge strategic advantage of the United States for decades, for more than my lifetime, has been the asymmetric advantage that our broad network of alliances and partnerships on Earth gives us. That is being systematically dismantled by a new administration. That is a policy choice. It shouldn't be a surprise. It was up for election, and that's what our nation chose, is to dismantle that. So I think that that reason for getting back to the moon, quite frankly, no longer exists. And especially you look at the changes they're talking about with NASA. I was never a fan of Gateway, but Gateway was all about bringing our European and other allies and partners with us to the Artemis program. So we are blowing up all of these reasons that we had to get there, and the real value in beating China to the moon was going to be the nations we bring with us, as compared to the nations that they're bringing to the International Lunar Research Station. So if that's not the reason anymore, I think you do have to try to fall back on things like science, but politically, that's not going to cut it. I don't think that is a reason that will endure, that will motivate people in Congress to spend the tens of billions of dollars necessary to make an enduring presence on the moon possible. So what do? I think that's why you're hearing more and more about resetting the goal line. Reset the goal line to something that we can win more easily, like Mars. And yeah, that is not necessarily about getting there with an alliance network. It's just about getting there and setting that long-term vision and goal and something that we can achieve. So for me, I think things have changed a lot over the past year.
Wow, thank you for those three perspectives, all very different from each other, but all, I think, setting the stage, I think, for our discussion. I think I want to start us off, because I'm a futurist, I'm a big picture. I think, stepping back and really, I think, kind of pulling the thread a little bit further from what all three of you have said, in this changing landscape, and almost, when we, even in the question where we're asking you, how important is it to beat China, right? This idea of national competitiveness, and each of you had kind of listed out elements, both from our perspective as well as the Chinese perspective. What's the range of importance that we see now? We obviously heard Todd kind of say how things are shifting. Maybe Namrata, you can kind of maybe speak from a Chinese perspective on how important is this competitive environment in this changing environment, with all these additional activities and relationships changing on the Chinese side, with the fact that it's not a lunar race, but also that we have maybe a moving goalpost. How important is this in broader terms of national competitiveness?
I think it's vitally important, and I'll list out the reasons why I say that. So one, because when you think about geopolitics or the larger international order. The US is competing with China. You cannot deny that. There is competition for narrative, there's competition for legitimacy, especially who should be building, for example, say, even a capability to go to Mars. And when we think about Mars, even there is competition from China, right? China is the first Asian nation to land independently on Mars' surface, communicate back, and now they have actually announced officially several missions to Mars as well by 2045, including a human landing mission. And biology, we heard in the panel earlier that there is really not so much thought, but China's doing that, right? So in that context, I think at one level, the competition is about who is the legitimate nation that can lead this particular vision, for example, to get to, say, the moon or Mars. And there is a competition there when you go, and you notice that perhaps not here, but if you go, say, to Asia or to, say, you talk to nations in Africa, they are really interested in hearing what is that US vision, for example, that we need to actually tie up to. And because they play such an important role, and that brings me to my second level of competition. So one, it is at the level of the international system. The second is at the level of international institutions. So what I'm noticing is that nations are actually extremely serious about what is happening on the moon and are very concerned about what could be that order that we are seeing, say, in the next, say, because they're futurists, they're actually talking about that in the next, say, 20, 50, 40 years that would enable what kind of, say, resource extraction regime, if I may, right? And then finally, I would argue that I think it is a competition because of the fact that China, and from the Chinese perspective, what I'm noticing is that they're very active in terms of, first of all, showcasing their program as global. Second, building international partnerships, for example, in regard to the moon. And you know what is interesting, and I'll end there. It's not just the rhetoric, it's what they're doing. So first of all, they are including partners in the Belt and Road Information Corridor. Now they are arguing that they will include things beyond LEO and geosynchronous orbit, which means they're going to go beyond BeiDou, navigation capabilities, or launch, right, to the moon and beyond. And they're arguing that, well, we can also think about the International Lunar Research Station within that context. And then you could say the seriousness of diplomatic effort in getting nations to sign both sides. So Thailand is the first nation, as you know, that did that. And so they're pointing out that, well, we have several nations that can also sign the ILRS. And the fascinating thing is, their conversations are not limited to just norm building or building regime. They're actually talking to nations about what it means to partner with China in terms of what kind of infrastructure that might include, what kind of funding, what kind of technology that might develop for the future. And so they're really talking about the future. So I would argue that there is a level of very serious competition. It might not be the kind we understand from the Cold War. It's different, and it's global. And so...
Yeah, well, and Dr. Pace, I know you had mentioned, earlier that, you say it over and over, this is not the space race, it's not the space race, but, kind of given this context of changing kind of priorities and messaging, where does this leave the US and how important would you prioritize the moon over other initiatives like something closer to home? Yeah.
Sure. Well, I think you have to look at the different aspects of national power, diplomatic, military, economic. I leave sort of science out because it's nice, it's there, but it's not really at the leading edge of what's going on. I would say China has both strengths and weaknesses, and I think if we were over in DoD, we would talk about net assessment. How do we put our strengths against their weaknesses? How are they putting their strengths against our weaknesses, and so forth? So looking at it from a net standpoint. I think one of the weaknesses that China has in the diplomatic side, on one hand, yes, they are competing for friends and allies. China is looking to be the leader of the global south. They're leading role in BRICS and all that. But they don't really value alliances quite in the same way that we do. They have a very much more hierarchical, view of those alliances. It's much more of a transactional kind of thing, and one may say that maybe that's where we're going to. But alliances don't really quite mean the same. For China, alliances actually are particularly a source of weakness because alliances can be betrayed, their alliances can be compromised. So again, we should be careful about mirror imaging what we think about alliances with what they think about alliances. And we should understand that the international order that they're looking for is a much more hierarchical one, which aligns with strength. We're a big country, you're a small country, get in line. And if you don't, you're the one causing disharmony. And a lot of countries don't really like that. So that's a weakness, I think, for Chinese diplomacy. The second is the commercial side, which we really haven't quite seen yet. China is primarily an export-driven economy, and for a variety of reasons, they have not been able to generate domestic consumption quite the same way. And under pressure, this is producing, I think, an economic crisis in China that may or may not lead to political crises at home. But I think China economically is in much more trouble than maybe they would like to present to the outside world. And a standard technique, of course, is to take the means of production and to export their way out of problems. Well, if China comes into the commercial space market, what are they exporting? Well, maybe launch services, maybe mega constellations, certainly Beidou has been part of that. And they're trying to launch their own version of mega constellation. They're running into a challenge. They don't have quite the throughput. They're not able to loft at the same rate that, say, that certainly SpaceX can. But they're building their own version of maybe a Starship or a big lifter. So what would that world look like if you're doing the futurist thing? We could imagine a world where there's Starship and a Chinese version of that competing for payloads in the developing world for influence, so Africa, Asia, and so forth. And traditional launchers, say Ariane 6 or Japanese H3, to really survive and maintain national autonomy will have to withdraw behind protectionist barriers. So I'm looking forward to a future international launch market competition between China and SpaceX that looks something like King Kong versus Godzilla, with everybody else kind of standing to the side and wondering who's going to get crushed next. So that will be a kind of the way the commercial world might look, is that we'll see the same sort of global struggle showing up in the commercial realm. And then finally, there's the military part of it, which again depends a lot on an industrial base. I know there's a lot of people who talk about the strategic military significance of the moon and even of Mars. I have a hard time with that because I'm probably much more short-sighted. I'm worried about Taiwan. I'm worried about the Western Pacific. I'm worried about the role that space plays, both in terms of improving resilience as well as providing force capability. One of my friends from our colleagues from the first Trump administration is a guy named Matt Pottinger, who edited a great book called, you probably know, called Boiling the Moat, about the defense of Taiwan. And he talks about space in there, about the defense of Taiwan, but he also talks about the importance of industrial capacity. Space is important, but you also have to have anti-ship missiles, anti-air missiles, stuff underwater. There's a whole future area emerging of precision swarms, which we're seeing the Ukrainians start to demonstrate. And so industrial capacity as part of our military needs is important. So space is necessary but not sufficient. And so given that that's the maybe more immediate need, I have trouble thinking about the military value of the moon or Mars. I do think there is a governance and alliance value, and I wish to strengthen those alliances. I may be swimming upriver on that one. But I think that the value of the moon and Mars is in shaping what that international regime looks like. Not that the Chinese will go along with it or necessarily obey it, but because it reminds other countries what values we do share in common, despite all these other stressors in the system. So it means, well, who are we? Well, we are the people who believe in values of the West, of the Enlightenment, rule of law, democracy, human rights, however imperfectly followed. But that's, who we are. And so that's how I would think about the alliances. But I would think much more about commercial and diplomatic and military challenges that shape this current space competition. So it's bigger than just a simple race.
Yeah. Well, and kudos to both of you, because you guys both went to the future without me having to pry, so I appreciate that. Well, I want to pull a little bit, Scott, on what you were talking about in terms of military value, because I think there is this big question on lunar resources. And, how do we determine what's even up there and what matters and where is it? And depending on what that answer is, there could be potentially some very interesting global power dynamics, especially given maybe some differences about where US and Chinese activities are. So I kind of just wanted to pulse each of you to kind of think about, like, yeah, what depending on what answer we get back, how could that influence competitiveness? So maybe, Todd, I'll start with you and just kind of go down the line.
Yeah, sure. And I'll pick up where Scott left off and to answer this question. Ultimately, we're in a competition with China in general because we have conflicting values. We value free markets and free people, and they do not. And that is the source of our competition, is those competing ideas, competing values. And so I think that plays itself out in space. In particular, when you get to resource utilization, whether it's near Earth orbit asteroids or on the lunar surface or one day Mars, how is that going to happen, right? There's a lot of science that has to happen. We have to figure out, is it going to be economically viable to extract, certain minerals or water ice or whatever the case may be? Does that business case close? There's a lot of science and research and experimentation and engineering that needs to happen to figure that out. And a big part of that depends on the cost of launch continuing to come down. But assuming that we one day get to that point, then yes, it is. Then you have a competing systems, if you will, for how we would, and many Western countries and others would want the system to work versus how China, Russia, Iran, North Korea, those countries would want it to work. And so, yeah, it comes down to competing ideas, and I think precedent is extremely important. Not because I think that China will respect precedent at all, but we do, is the thing. And so we self-limit ourselves because we come, whether we realize it or not, we come from hundreds of years of tradition of the common law, right? And many other nations do too. That's all about precedent. It's all about how have things worked before, how have things been decided in the past, and that determines how it should work in the future. We've got to be the first ones there setting that precedent so that they don't set our precedent for us. I think it's important psychologically for us as a nation. That is a big part of our own self-legitimacy in how we operate in the global stage, is how we perceive ourselves. And do we perceive ourselves as breaking precedent, as being contrary to what has been normally done? Or do we perceive ourselves as setting the precedent and then expecting others to follow and stay in line with that? And so I think that is an important reason. We want to be there. We want to be at the forefront of finding if there is something economically viable to mine for on the moon, and determining how that system is going to work. How this, cislunar economy should work.
Namrata, I want to come to you, but I want to be a little fire starter because I think I'm actually hearing a little bit of opposing perspectives between you and Scott, right? I think in some ways, you're saying precedent doesn't matter. It's like the scale. It's who's enduring, who's.
No. I think precedent matters. We're a common law country, and that's who we are. But I think there's just the point earlier of what we just don't know. There's just a lot of science still to be done. And my own personal biases, and I put them out as biases, not fact, I think that there probably is lunar water ice, and we could probably profitably extract it, but you're not going to ship it back to Earth. It will lower the cost of ownership, if you will, of a lunar facility. Now, there might be something in like surface lunar helium-3 mining. There already is, in fact, a small market for that sort of thing. I think asteroids, rare earth groups have maybe much more promise for actual economic extraction, but a lot of it we just simply don't know. But in terms of the competition and precedence, I think the more fundamental reality in that competition is going to be that China is still going to be an export-driven country. And so if you have China on the moon, say extracting resources or asteroids or doing something, they're still in a situation where they've emphasized, as good Marxists still, the means of production, but that doesn't mean they're a source of consumption. That doesn't mean they're in a market. So they've got the same problem they do with all kinds of other parts of their economy, of being dependent on other countries absorbing their surpluses so that they don't have to confront the political tensions that arise if that were to fail. So, you know, the Chinese Communist Party is somewhat riding the dragon at the moment in terms of their reliance on export-driven policies, because it depends on the rest of the world being willing to tolerate that, whether on Earth or in space. And of course, increasingly with this administration, and I think in others, and with the last administration, that tolerance is gone. There may be a necessity of still relying on China as a production facility, but the willingness to absorb their surpluses so they can put off their political internal reckoning, I think is a lot less. And that would be true on the moon as well.
And how about you, Namrata? What do you think about this resource question and competitiveness?
Yeah. So first of all, to answer your question, what is out there, right? Especially the moon. So when you look at the global narrative, and I want to put it at the global level, because the conversation on the moon is not just American-centric or US-centric, it's become global in the post-Cold War period. And the vision and the identification of the moon is really interesting if you look at it from that perspective. So for example, let's take China. So when I listen to Chinese space scientists or engineers very seriously involved on their lunar program for the last 30 years and a huge commitment of time and resource, they argue and they influence the Communist Party Standing Committee, for example, in their thinking for funding purposes, which is that the moon is strategically important for its own sake. So we are not going to the moon because we want to think about it as a stepping stone to Mars. We're going to the moon because the moon is vital. And Wu Weiring, who is the designer of the lunar space program and was awarded a very high civilian honor by President Xi Jinping for his contribution, points out that there are three important things that China needs to focus on in the long term. One is, of course, water ice, which Scott pointed to, and he identifies and breaks it down, why that is vital, including for their lunar research station one day when it might have humans. So you might need oxygen from that, or fuel, right? The second resource is platinum rare earth metal. The moon is thought to be rich in that. And in fact, every mission that China is doing, and I looked at their data in the last week from the official source, and they point out that, well, you can use iron ore, for example, to build, say, a rocket or aluminum. And the idea is not to bring that back to Earth, it's to actually scale it up from there. And they give a very scientific explanation for that. You might question that, but at least let's take them in their word, right? So the argument from a scientific perspective is that, well, the moon has so much less gravitational pull. So it makes strategic advantage to launch from the moon, for example. It's 1/6 the gravity of Earth. So you need less fuel. And that's something that Chinese scientists are thinking through, like why? Well, we think about reusable rockets. The Long March 9 is very important, which is their version of Starship that they are launching by 2030, which is reusable. They point out that it's still something that we are launching from the deepest well, gravity well in the solar system. Doesn't make sense, right? And so that's their argument. So I'll end by saying that when you think about space resources, water ice, helium-3 for nuclear fusion, we heard a lot of conversation about nuclear propulsion in the panel before us. They focus on that, and they also focus on platinum group metal. Now, they also argue that, well, these are not at advanced stages of development, but that's how technology progresses. You know, you invest in it, you actually demonstrate, you actually go there, and which they're doing, right, in terms of their capability. And then finally, how do I understand the seriousness of their missions, right? So that's a question we get asked a lot. That, okay, China's saying all this, but maybe they're not serious. Maybe they're not going to do it, right? Well, look at their position papers at the United Nations. So in 2023, and I've been to China, I've asked these questions to their engineers and policymakers. They argue that, well, we will come up with something that will give you more concrete evidence that we are very serious about this. So besides the white paper, they have position papers at the legal subcommittee, where in 2023 and then 2024 again, for the first time, they included their entire lunar program within a resource utilization perspective, and they made it official. So, and then Russia, we talk about alliances and partnerships, Russia, who was very much against this resource utilization, including the Artemis Accord, agreed with the Chinese position. So that's how resources are important, and including the shaping of the narrative to set a precedent, which Todd was talking about. And I would argue that they are actually doing it well. And I would also caution that when we think about Chinese partnerships, they're actually quite steady in terms of the alliances they have formed. Think China-Pakistan, think China-South Africa, think China-Thailand. Years of building up of partnerships.
Yeah, thank you for that. We're going to open up for questions, but I'm going to ask one more spicy question because I can't help myself. How much does Congress matter in how the U.S. advances its approach to space right now? And again, have things changed significantly, both with the political environment, but also with privatization of space? And yeah.
Okay. So I would say, first of all, Congress does matter as a very strong moderating function, meaning that post the Columbia accident and NASA authorization bill in 2005, NASA came with this sort of stepping stone approach, first moon, then Mars kind of approach. That was attempted to be changed in the Obama administration, Journey to Mars and all that, or cancellation of the moon and so forth. And Congress, on a bipartisan basis, pushed back. And so you've seen authorization bills after authorization bills and appropriations going with it that has supported that stepping stone approach of moon, then Mars. More recently, when there are discussions about going directly to Mars, the moon is a distraction, as infamously said, Congress has pushed back against that. And so we've had these sort of hearings. So there is this great sort of moderating function against these sort of large swings. Now you can argue, well, funding and other things also matter, but that's also true coming up. That we have the skinny budget proposal, but we still don't have a budget. Okay, so we may be in a year-long CR. There is other priorities. I'm not terribly surprised at some of the cuts and so forth that were made, Gateway, Mars sample return, and so forth. But on the other hand, I think there are things that are left unfilled that Congress will probably have a say in. One is with the commercial LEO development, such as, are we really going to have that? And if the station goes into the Pacific and the Chinese are the only ones up there, is Congress going to care about that? Second big one is, what do we do after SLS? I talked about Artemis 2 and 3, but is there a heavy lift, commercial program, and is it more than one out there? That's kind of a black box as to, what would fill that. And then finally, if we're really serious about being back on the moon before the Chinese, and I completely take seriously Chinese statements of 2029, 2030, the party has said this, so it's not just some random scientist, it is very senior level, said that. If we think that that's really serious and we care, then we need to think about extra margin for HLS and for test flights, because we're going to probably have to do more test flights than you expect if you're going to have a high confidence. So HLS, heavy lift, commercial LEO development, those are three big boxes that have yet to be filled in. And so that's where I see Congress probably playing a role.
Yeah, if I could jump in here. I completely agree Congress does play a big role. However, right now, like this particular Congress, I don't know that they're actually going to have that much influence. I think the influence will come back, but right now, Congress is highly dysfunctional. You have narrow majorities in both chambers, unruly majorities in both chambers. They can barely get anything done, as witnessed by the FY25 appropriations bill, where they ceded tremendous amount of power to the executive branch. They basically abdicated responsibility for doing the regular appropriations for all of government. I mean, that is really unprecedented, what we're seeing. Now they're trying to, stack as many things, must-pass pieces of legislation into this one bill and pass it using the reconciliation process. They're putting things in there through reconciliation that have never been put through reconciliation before because they have no other way of doing it, right? So I don't know that this Congress will actually be able to moderate the shifts that we're seeing come in terms of our space program. Give it a few years, and I think that in all likelihood Congress will come back to that being that moderating role. But I mean, there's not a Senator Shelby right? There's not a force like that that is willing to stand up and go to bat for, certain programs. Not that Senator Shelby was always right, but I think we don't see a lot of power. This is a very, very weak Congress, probably the weakest we've seen in a generation. So I worry that there will be a lot of kind of extreme movements possible right now. And for anything like going back to the moon and enduring presence on the moon, going to Mars, you need a program that has stability, that has endurance, and the only way to get that politically is on a bipartisan basis. You've got to have bipartisan support, and if the changes they're making now or considering making are changes that won't engender bipartisan support, then that is a real risk in the long run.
Yeah, no doubt it'll have some impact on our competitiveness. All right, we're going to go to questions.
Hello. I'm Issam Ahmed with Agence France Presse. How much of a Sputnik moment would it be for China to go back to the moon first, and if China were to do its grab-and-go mission first, given the recent advances in the AI sphere where you have DeepSpeak, the India-Pakistan air war where Chinese technology helped Pakistan down a number of Indian jets? Would this be another sort of adding to that growing kind of influence of China in geopolitics? Thank you.
So sorry, you said China going back to the moon. I didn't catch that.
How much of a Sputnik moment would that represent? China getting to the moon before the United States, and also China completing a grab-and-go mission on Mars before the United States?
Okay, well, so China's already on the moon. So, with human missions. Okay. Well, I would argue that if you look at, and that's why strategic culture really matters. So they're not billing it as for example, the human mission as a Sputnik moment. So when they talk about their human missions, they're talking about it from the context of infrastructure. So basically, even if you look at the design of their lunar suits, for example, the spacesuits they put out, it's more functional. So they would argue that the more important thing is to build the infrastructure, and humans are going to be a part of that infrastructure building. So you see the difference. The focus is not to send back flags and footprints. The focus is a permanent research station that's going to enable both science exploration and then they use the word space development. Now that's something, again, and I'll end there, I noticed both in Japan's space policy, India is starting to talk about it, is that they're going beyond just space exploration and science to use the word space development. So yeah. Sorry, to answer your question, I don't think they talk about, their narrative is not like, oh my God, if you do this, it's gonna be the most, it's much more comprehensive and different.
Yeah, Todd.
Yeah, so I guess I would look at it on the other side as well. So I think, I can't disagree with you. I think you're right on their intent is not a surprise Sputnik-like moment. But I think it would have an effect kind of like that on the United States and much of the Western world, quite frankly. It would be different than Sputnik. I think Sputnik was a huge blow to the American psyche, in terms of our diplomatic power, our informational power, and our military power. I think this would just be the D in the eye of dime. I think it would be a blow to kind of our diplomatic prestige and our informational presence around the world and influence around the world. But I think it would be a huge shock to Americans if China landed on the moon. I mean, I wouldn't rule out a surprise landing. That maybe in 2028, we think they're sending an uncrewed lander, and all of a sudden they send back pictures of people walking around on the moon. I wouldn't rule that out, and I think that would be a huge shock to the system.
Yeah, sorry, I understood your question. I thought you're asking whether for China it's a Sputnik moment. No, for the US, yes. In fact, the US was totally shocked when China landed on the far side of the moon. It was such denial that China would ever do this. I gave presentations on that, and they wouldn't even want to look at the facts, the audience that I talked to. But then when they landed, I mean, it was a total shock. So humans building permanent infrastructure, that'll be a Sputnik moment for the US, I think. So yeah.
Okay, I'm going to hijack the time and ask that we have one more question.
Okay, Jan Spacek from Agnostic Life Finding Association. There's I really like the point about the Olympics, that you have different disciplines. And for me as a scientist, it's very frustrating to see that United States is retracting from some of the disciplines, especially the ones I want to compete in. So there's another resource you don't talk about. I moved from Eastern Europe to United States because that's the place where I can do the best science, but it seems that it's not going to be going forward. So obvious that United States is the best place. So the resource you are losing as well is actually the human brains coming in. So that's my frustration to share.
Any final words?
Well, I think, I think that's certainly a legitimate concern. For example, NASA Goddard, a lot of their scientists there compete. They only, as the saying goes, only eat what they kill. They have to compete for grants, which means that some of the scientists at Goddard are really world-class competitive. And so if there aren't opportunities for that, they're scientists and they will look to go someplace else. I don't think many of them, unless they have cultural history and ties, will want to go to China. China has a number of problems. Yes, they're very attractive in many ways in terms of resources, has burdens of its own. In a similar way, Europe is offering. I mean, the EU has been offering, and many universities in Europe, I'm kind of seeing this personally now, reaching out to people. But Europe has its own problems, particularly in terms of, not in terms of doing science, but in terms of connecting science into the economy and in terms of doing better. When we look at commercial space, for example, many reasons why Europe lags in commercial space is not because they don't have technology and they don't have smart, ambitious people, but because they lack other parts of the ecosystem. So people, whether it's financing, spirit of entrepreneurship, tolerance for failure, a more integrated market, and so forth, regulatory burdens, and so on. So the U.S. is definitely suffering some risks and will suffer some losses. I don't yet see some place that's that astonishingly better. So maybe least bad is maybe where we are, and therefore I think we have an opportunity to recover and to do better. The question is, will we?
Great, that's a great way to end. I just want to say thank you to the three of you for a really good conversation. This question, I think, is really, it's an important time for us to be asking it together. So big round of applause for Scott, Namrata, and Todd.
Thank you very much. Very interesting panel. So we're going to go off to lunch right now. And just remember also, if you're planning on going to the reception tonight and you haven't registered, please do so at the front desk or just go online and purchase your ticket for tonight. Wonderful Ardbeg whiskey tasting, as well as the Washington Tonback signing ceremony. You don't want to miss that. Also, Jim Green will be signing books upstairs. I will also, whenever I have time to get up there. So if you haven't purchased Jim's book, that can also be purchased online on the registration page. So see you back here at around 2 o'clock. Thank you. Oh, by the way, for people looking for restaurants, okay, across the Marvin Center, the Student Union Center, there's a Panera Breads. Next building down, there's actually a little mall, inside mall, with multiple restaurants also. There are quite a few options around the area. So.
And we are actually a little past the halfway point for day one of the Humans to Moon and Mars Summit. Amazing panels, really, really excellent panels. That last one talking about what's happening between the United States and China, absolutely fascinating. A lot of interesting new ideas there. I'm Matt Kaplan, Senior Communications Advisor for the Planetary Society, and every year for quite a while now, come here and host the webcast, this live stream that is coming to you from Washington, D.C. and the George Washington University. We are going to continue with H2M2, day one, at about 2 o'clock today. But during these breaks, we'll have a few other things to talk with you about. I'm hoping to be joined, in fact, here she comes right now, by one of the officials who has helped to put all of this together for Explore Mars. Tiffany Vora, welcome.
Matt, always a delight to see you. Welcome to the summit.
Thank you very much, and the same here, obviously. Vice President for Innovation Partnerships, right?
That's right. I was really pleased to enter the Explore Mars community to try to expand our community of stakeholders to not just be our classic space enthusiasts and companies that know their space companies, but also to get more people and organizations to have skin in the game in seeing a human presence beyond Earth.
Let me ask you about a concrete example of that I was lucky enough to participate in not too long ago, just a few months ago, at, of all places, the SETI Institute up in Silicon Valley, and it was your Mars Innovation Workshop, which was more than a workshop, it sort of built a community.
That was the idea, right. So we put on the Mars Innovation Workshop exactly to bring together people who know they work in space and people who think maybe they don't work in space today, but you and I think in 20 to 30 years that will really be there. And what I really want to see is a community of people who can strategize together, can work on tactics together, can form unusual collaborations and partnerships, and perhaps most importantly, pick up the phone when someone that they know calls with an ask or an offer.
You don't have a panel today, but you have a really interesting one tomorrow with some very distinguished people on it, talking about analog astronauts, analog visitors to places like Mars. You're one of those, aren't you?
I was. I've done 3 analog Mars simulations a long time ago now. That's actually how I know Bob Zubran from my days with the Mars Society 20-something years ago. But so at the Analog Astronaut Conference just 3 weeks ago, we had the first part of this conversation where we wanted to see what are the possibilities of using the ISS, while we've still got it, as an analog for that transit phase between Earth and Mars, which is about an 8-month journey or so in microgravity. And here's what we think needs to be dug into a little bit more. We already know a lot about what happens to the human body in extended spaceflight, but when folks come back from the space station today, they go home. They don't go to work having to do the hard manual, psychological, and intellectual labor of actually being on Mars. So could we do a new type of analog where we get the people on the ISS or another, say, a commercial space station for that transit period mimicking the journey to Mars, but then we put them straight into a Mars analog after that to make sure they can do all the things they need to do. You're going to see some more of that conversation tomorrow, so be sure to tune into that. We have a variety of perspectives from our 2 astronaut panelists as well as our excellent analog astronaut panelists tomorrow, so stay tuned. And Matt, of course, you know me. I'm not just doing that one panel. I have another panel tomorrow. We're going to be looking more carefully at how innovating for Mars can deliver value on Earth starting today. So I'll be joined with several really fantastic businesses that are spinning up products for benefits in space, but the idea is we want to have successful businesses delivering these breakthroughs now for Earth. So be sure to join us for that conversation.
Excellent teaser for just a fraction of what we can look forward to tomorrow. And of course, we have much more to look forward to today as well. Thank you very much, Tiffany.
Thank you so much, Matt.
Dr. Tiffany Vora, Vice President for Innovation Partnerships at Explore Mars, which of course is the creator of the Humans to Moon and Mars Summit, which we are now going into the lunch break for. As I said, we should be coming back at 2 o'clock. I'll come back then just to help get things started, and we've got other people lined up to talk to you, including Bob Zubran, Robert Zubran, the fellow who gave that passionate, he only speaks passionately, who was talking, gave that little half-hour address a little bit earlier today. Always fascinating. I want to talk to him about his new book that came out last year, The New World on Mars. It has a lot of fascinating concepts. So hope that you'll be able to stick around through lunch and join us for the rest of today and tomorrow here at H2M2. Thanks for watching. And we're back from lunch for the second half of the first day of the Humans to Moon and Mars Summit. Coming to you live from Washington, D.C. at the George Washington University. I'm Matt Kaplan, Senior Communications Advisor to the Planetary Society, but very happy to be back for yet another year of hosting this live stream and otherwise helping out with Explore Mars' big summit, the H2M2 Summit. And it is always a pleasure to talk to Dr. Robert Zubran, the founder and CEO of the Mars Society. Bob, welcome again.
Well, great to see you again, Max.
So, you made a wonderful presentation earlier today. I don't think you've lost, in the last 35 years, is it, that since you first presented Mars Direct, I don't think you've lost a gram of your passion for all of this.
Well, I try to hold on. Think young, stay young.
So we were talking about you were talking about the immediate future in the next, 10 or 20 years of getting humans to Mars. I want to talk about your book, which of course you were my guest on the Planetary Society member book club not too long ago. And that was your book that just came out last year, which I think I told you at the time, it's almost every page has some amazing concept that came out of your mind.
Okay, well, thanks. So you're talking about the new world on Mars. What can we create on the red planet?
Let me give you just one example that I've been sharing with other people, and this is only one example. Of course, I am a big believer in domed cities on Mars, but I thought that those were over because of radiation and maybe other factors. But you came up with this concept of a double dome with fish in between the domes.
Okay, well, you can have a dome where, you have an upstairs, outdoors as it were, where people can go and walk around among, as it were, ponds and trees and such. And then you have an underground section, which is shielded from radiation. Now, it could simply be underground, because under a couple of meters of dirt, you're completely shielded from the space radiation for all practical purposes. And if you think about it, most of us spend say 90% of our time indoors. I mean, how many of us spend more than 2.5 hours a day outside? Okay, maybe there's some people that spend 5 hours a day outside. They're still spending 80% of their time indoors. And that, if you regard the downstairs, it's shielded as indoors, and the upstairs isn't. You're cutting your radiation dose by a factor of 5 to 10. And since the radiation dose on the surface of Mars is about the same as that at the space station, that's acceptable. So fine. So combined downstairs that's shielded, upstairs that's not. But why shield with dirt when you can shield with water and make a fish farm out of it? So because water is great shielding, and it has the advantage that it provides living space for very useful things like fish, and it's transparent, so it lets light down through, so you can have natural light coming down into your city, and people can be looking up and seeing fish swimming above them instead of just dirt. So it's more fun.
And so you do still see an important role eventually for cities on Mars, if not the million-person cities that you talked about and discounted that Elon Musk envisions, but these smaller communities, you said tens of thousands, interconnected.
Well, eventually some might be interconnected. I mean, the vision that I have in the New World on Mars is that once reusable rockets become common, and they will be, because if this thing works, there will be copycats. There'll be Chinese knockoffs of Starship, and there'll be other free world competitors of Starships. And the fact that you're going to have reusable launch vehicles means that not too long afterwards, there's going to be a market in used launch vehicles. And just like used cars can be bought that are perfectly functional, that are 1/10 the cost of a new car, soon, not necessarily soon, but in the course of time, there's going to be possible to pick up launch vehicles at a very small cost. And so different groups of people that after the exploration phase, where we learned how to explore on Mars, and we probably built some scientific bases on Mars to support expanded exploration. This will create all the technologies needed to support larger groups of people on Mars. then at that point, okay, groups of people who decide they want to establish a colony on Mars will be able to do so. They'll pick up a used starship and they'll go. Okay, so you'll have diverse groups of people with rather diverse sets of ideals, founding colonies according to their own lights. And the question of what form of society eventually prevails on Mars will be determined by natural selection, not by violence between the cities, but simply by which one draws the most immigrants.
And all of this is in the book. All of this is in The New World on Mars, 2024 publication from you, Dr. Robert Zubran, our guest. They want us to get out of here because they have to start the program again from the stage. I'm being looked at by Chris Carberry right now, who's smiling at his old boss. Very, very quickly, the Mars Society Convention is in October.
Yes, it's in October at the University of Southern California in Los Angeles, October 9th through 11th. So I hope everybody can come. There's lots of information about it at marssociety.org. We have an open call for papers. If you want to talk at the conference, send in an abstract.
I look forward to joining you. Thank you very much.
You're most welcome.
And let's throw it up to the stage right now to the leader of Explore Mars, Chris Carberry.
Thank you, Matt, and welcome back, everybody. Well, you know our next speaker. He's been on 2 panels before us, but you know him. He was the former chief scientist at NASA. For many years before that, he was head of planetary science and responsible for, frankly, most of the planetary missions we've sent out over the last few decades. He's also, last year, became the chairman of the Explore Mars Advisory Board. And as you probably know, he has this book that's on sale today, and he's still signing, and we'll be signing tonight at the reception as well. So if you haven't gotten your seat, please sign up for the reception tonight. But, ladies and gentlemen, Jim Green.
Thank you very much, Chris. All right, so what I'm going to talk about today is really the importance of the evolution of the volatiles in the permanently shadowed regions. This has been some really exciting results that have come out over the last decade or so, focusing our attention when we go back to the moon to indeed go to the southern pole or the northern pole. Now, it really starts, of course, with the Apollo program. So 69 through 72, we had 12 humans walking on the surface of the moon. And what were they doing? Well, they were putting out retroreflectors so we could see the distance from the Earth to the moon. We fire lasers at these retroreflectors, measuring the speed of light of the return signal and getting a distance from that. And we do that every year. Well, we do that every year because we're finding out the moon is moving away from the Earth. In addition to some of the experiments they put down on the surface, they also brought back samples. In fact, there's an enormous number of samples that came back. About 382 kilograms of samples, not only regolith, which is the broken up rock that is many meters thick, laying all over the moon from a process that is now clearly the raining process, which is through impacts. Not only the larger stuff, but the micrometeors just garden it, it's called, impacting the surface and destroying rock and creating these very sharp little particles that we call lunar regolith. In addition to that, these rocks could also be age dated. And because of the unique areas that they went, they were able to determine a lot about the age. And the age of the rocks they brought back had some variation associated with it. And so you have to put that in the context of how the moon evolves. In addition to that, the rocky material could tell us all about how close to Earth is it, and the isotopes that they could measure inside the rock told them that it was Earth-like. Now, bringing all that material together enables them to come up with theories on the origin of the moon. And in this case, what connects the best and what has been the prevailing theory for at least several decades now is the giant impact hypothesis. And here's how it goes. 4.6 billion years ago, in and around the neighborhood we're at today, away from the sun. Material was gathered and created several bodies, one of which is the proto-Earth. It turns out another one is another object, about a Mars-sized object, that the planetary scientists called Theia. Now, because of the gravitational pulls, tugs and pulls that happen by bodies that accrete a material, begins the process of pulling Theia in. Theia, at about 2.5 billion years, impacts the proto-Earth and creates a giant collision. And as you see here, we can model that. We can take this whole concept, break it up into individual pieces, both Theia and the proto-Earth, and we can then model that and determine what happens. Well, this is total destruction for Theia. Material is spewed all over the place. And so as you see in the modeling, material is flung out, and the Earth begins the process then of going from proto-Earth to the Earth we know today and accreting that material into the new body that we call the Earth. Well, there's another physical process that happens that's extremely important, and it begins with the knowledge of a location beyond the Earth called the Roche limit, and that is anything inside the Roche limit. Gravity is strong enough that as material tries to come together, the differential gravity and distance keeps these pieces apart. Think of Saturn's rings. Saturn's rings will never coalesce into one object because it's inside the Roche limit. But outside that Roche limit, objects can accrete and become larger. And so what happens over time, and it's actually fairly quick, the modeling seems to indicate on the order of months, a new object is created beyond Earth, and we call that today the moon. Well, this particular object, once it comes together, is only about 4 Earth radii away from the Earth, okay? So it's a huge object in comparison to other moons that terrestrial planets have, like Phobos and Deimos around Mars, and is very close to the Earth. And of course, the Earth is spinning real fast based on these impacts. And what happens over time is as the moon begins to drift away from the Earth because tidal forces, the pull and tug of these two bodies, that energy gets dissipated and the Earth slows down and the moon moves out. Well, the Earth started out with a 5-hour day, and the moon, just at 4 Earth radii away, begins that process of moving outward. If you were living at that time and you could stand out and look at the moon would dominate the horizon. It would be 16 times larger than it is today. And it's really a fantastic object. And the ability that the moon has to keep the Earth's rotational axis, as I mentioned earlier, to only change by a few degrees has really helped the Earth's climate in particular, to be modulated very smoothly or very mildly over time in comparison to larger excursions like Mars has. So that obliquity is extremely important. Today, the moon is 60 Earth radii away from the Earth. And our day, of course, is 24 hours long. Another really fantastic thing happened, and this is because we continue to analyze the samples that are in our archive. You know, we haven't analyzed all the samples we have. Those samples have come into the curation facility managed by the Johnson Space Center, and some of those samples then are preserved, not touched, and located in a different position, but a lot of the samples then that are available then go out to scientists all over the world to propose to analyze them. You can propose to destructively analyze the samples, that means break them apart, or non-destructive methods to get the information that you're interested in. All that is peer-reviewed, and the best activities and the best proposals win out over time. Well, Harrison Schmidt, our first real planetary scientist that walked on the surface of the moon, really understood, well, we have this rock, I'm not taking that back, and here's what we don't have, let's go get this. And oh, by the way, when I go and I look at this rock and we bring it back, I want to know its orientation. I want to know where the rotational axis is, and I want to really get the provenance of where that rock is relative to the rotational axis of the moon. Now, this turned out to be incredibly important because the samples we brought back had a remnant magnetic field trapped inside the rocks, okay? And the concept is, well, where did it get that? And if the moon had an intrinsic magnetic field, what kind of field would it look like? Now, it turns out, and this has only been discoveries within the last 5, 6, 7 years, that indeed we now have determined that the magnetic field remnant that's in these rocks came from the existing magnetosphere of the moon. So the moon had enough of a core that it generated its own magnetic field. And that permeated through the crust and through the rocks, and during impacts where you then have molten rock being flung all over the place, and as that rock cools, the magnetic domains of the atoms that are in the lattice line up, producing that remnant magnetic field. Well, because Harrison was able to get the orientation correctly, he could determine, scientists can determine what this field was like. And it turns out it's like this first one, which is a dipole-oriented field along the rotational axis. That fits the analysis of the remnant magnetic field the best. Well, this is fantastic because now we can measure that remnant field in these rocks, we can age date these rocks, and we can come up with a distribution of what that field was like over time. Because clearly the moon doesn't have a magnetosphere. And here's here's a summary of the results that came out. And indeed, that magnetic field early on ramped up. And at 3.8 or so billion years ago, when life was starting here on Earth and potentially at Mars, as we've discussed before, the magnetosphere of the moon was the largest. And then it began to taper down. Now, this is really important to understand because it fits into a larger picture of what was happening within the solar system. Carl Sagan has always brought out the fact that the sun, when it first was created 4.5 billion years ago, was very active. It also was very faint compared to today. About 30% of its light hadn't been created. And so, indeed, now we have the faint young sun problem with a very active sun, with the moon generating a magnetosphere, and we can model that magnetosphere, and we can really take a look at what it looks like. Well, here's some of the results, some of the scientific results that come from modeling these fields, and we see the moon's field is large enough that both the field of the moon and the field of the Earth can interact. They can connect. And as you see, even when the moon is out to 25 or so Earth radii, and even further, about half the distance of where it is today, that the Earth's field and the lunar field are really well connected. So the moon's magnetosphere lies within the Earth's magnetosphere. And this also allows an opportunity to protect the Earth. Because of these large solar storms, the moon can run block and would be the first thing that would be hammered or interacted with coronal mass ejections and how active the sun really is. Once again, maybe meaning that the moon has been really helping the environment here of Earth to become uncommonly habitable. Well, another event happened based on bringing back these rock samples and age dating them, and that is there appears to be impacts that occurred, and a large number of them, between 4.1 billion years and 3.8 billion years ago. Scientists call this the late heavy bombardment. And not only is there a lot of impacts, these are impacts of very large bodies onto the moon. And in fact, what happens in these impacts, you blow away a significant part of the crust. So you end up with the lower crust or upper mantle, which is molten rock, which then pours into the crater. And what it does is it fills the crater up. It brings up heavier material from the interior, more iron, more aluminum. Many of those heavy mass materials end up in this mare. And that's what it is. It's the mare of the moon, is really lava rock that's poured into the craters that were made during the late heavy bombardment. Well, as you can see on the right, interior-wise, we can model how one then flows this molten rock onto the surface of the moon, and that causes an equilibrium change in the area of gravity, meaning the near side becomes heavier than the far side, allowing then that rotational axis to change, to move. And in fact, during this period of time, it moved perhaps by 8 or so degrees. What's fascinating about this is this picture really fits well with what we know about the volatiles in the polar regions of the moon. So here is an example of a water signature observed by orbiting spacecraft. We can see that water signature has this shape from the old pole back to the new or present pole. It's an oblong shape, and it matches both the north and the southern hemisphere. This fits really well with that analysis. To really tease out what else might be in these permanently shadowed craters, LRO was launched, Lunar Reconnaissance Orbiter, in 2009, and with it was another mission called LCROSS, and LCROSS was designed to go and hit a permanently shadowed region, and the ejecta material that would come up would be then examined, would be then looked at, both spectrally, also imaging it, and many different science analysis occurred. And of course, they were looking for water, but they found far more than just the water. They found a whole set of volatiles, which were sulfur-bearing in addition to CO2, CO, in addition to H2O, also nitrogen. This material then that they were finding was quite a puzzle at the time. Did we bring it to the moon with LCROSS? Are we really looking at the material that's being ejected from the crater? And so that kind of knowledge was had to factor into what we believe was really happening. In addition to the magma that is filling in, creating the mare during the late heavy bombardment, we also can calculate the outgassing that was going on. And it turns out it was significant. Current research seems to indicate that the lunar atmosphere, which is being created because of the late heavy bombardment and the volcanic outgassing that comes with molten material coming out onto the surface, the pressure might be as much as 12 millibar. 12 millibar is twice the surface pressure of Mars, all right? So this turned out to be an extensive atmosphere. Now, of course, what happens is the sun's ultraviolet light ionizes that upper atmosphere, creates an ionosphere, and then what happens is that ionospheric material is trapped by the magnetic field, which is the roadmap out away from the moon to somewhere, and that somewhere is to the Earth. And the same happens at Earth with the higher ultraviolet light coming from the sun because of the solar activity that's going on. Streams of particles that were being ionized coming out of the Earth's ionosphere were moving to the moon. And where does it go? It goes into the polar regions. So in other words, during the time when the moon had the maximum magnetic field, during the time of the late heavy bombardment, during the time of generating gases, an artificial atmosphere, if you will, a temporary one at that, because it may have lasted for maybe 100 million years, the magnetic field was actually protecting it. And so consequently, the exchange of information between the Earth and the moon was going on. Now, what happened since then has been measured by the LADEE spacecraft in particular, and that is there actually is a water cycle on the moon that's going on today. So for the last 3 billion years, what's happening is micrometeors will hit the surface and shock water that's in the crust out of the surface, and then it hops around or it gets ionized and the solar wind pulls it away. Now, how it found this was with the neutral mass spectrometer on LADEE. LADEE was the Lunar Atmospheric Dust Dynamics Explorer. It was designed to measure lofted dust, but also that what we call exosphere, what kind of outgassing the moon is currently doing. Doesn't produce a fully collisional atmosphere, but we call it an exosphere, so it's very tenuous. And over time, LADEE was measuring clouds of water. All of a sudden, they'd come out of nowhere. And this was going on, as you see in that upper graph, very sporadically. And so the sun would ionize it and pull it away. Some of that water would move to other latitudes. And of course, the latitudes it's going to move to is towards the cold traps. That thermodynamics tells us that. And that turns out to be the poles over time. What really gave it away is when the Gemini meteor storm hit, and we had this huge cloud of water. And it's tenuous, of course, all around the moon, which really gave it away. We then could go back and they could look at the data and they could see these are indeed meteoric storms that occur, and they found several that they didn't even know about. So this is really an exciting time. And it causes this water cycle of water being extracted out of the lower latitudes, moving to the higher latitudes, and therefore producing more water into these permanently shadowed regions. So when we step back and we look at what are the volatiles in these permanently shadowed regions, a more complete picture is being put together. And in fact, there's a time history associated with it. The beginning, of course, has comets hitting the moon, along with asteroids, both with significant amount of water in them. And then there's also the lunar atmosphere. So you have a lot of volcanic material. Those volatiles are going to move also to the cold traps and precipitate out, so that atmosphere will collapse in the cold regions into these permanently shadowed regions. And you'll also have the early Earth atmosphere. Some sort of signature of the early Earth atmosphere might be there. This is tremendously exciting. We only have anecdotal information about what that early atmosphere might look like, and maybe we can determine what that would be even better if we actually had this kind of ground truth, not on Earth, but it's on the moon. And then, of course, you have the lunar water cycle going on. So now that we know that, that these volatiles are there, and perhaps there's a stratigraphy associated with them, and we're questioning how much of that stratigraphy is actually going to be there because micrometeors continue to hit the moon, continue to garden it, okay? It might be mixed up. We expect that. But there might be some sort of trend that we could look at. It's clear to the scientists this is the place to go. It has resources we want. It has resources we need in human exploration. And it's not just water. It's not just H2O. You can get hydrogen in many other ways, in addition to oxygen many other ways, because it'll have CO and CO2. Both of those will have collapsed out of the atmosphere and into these permanently shadowed regions. Scientifically, I want to go there, but I want to core it first. I want us to go, just like we do in Greenland and Antarctica, to core these areas so that we can lay them out and get a basic history of the evolution of these volatiles over time that allows us to fill in this picture even more. And so, consequently, we need to start planning on how we're going to extract these resources. And once again, science needs to be in the lead because of all the information that we can gather from the existing material that's in these permanently shadowed areas. So thank you very much, and I'm willing to take some questions.
Test. Hi.
Hello, I'm Chris Temby with the Agnostic Life Finding Association, or ALPHA. So we're seeing with CLIPS, the commercial lunar payload services, there's a interest in bringing a lot more payload to the lunar surface for less, as a way to basically prove out a bunch of different technologies, hopefully to sort of do the Moon to Mars architecture, right, so that those sort of capabilities and technologies can also be applied to Mars. There's been, I would say, a focus on ISRU, in situ resource utilization, and also there's the plans to have refueling starships, for example, on Mars require large-scale water mining. Is there any sort of intention or plan to do large-scale water mining on the Moon, especially with these PSRs, or sort of just smaller-scale ISRU, I guess is the question?
Yeah, that's a good question in the sense that to get to that point, we're going to have to evolve that. ISRU is critical because scientifically, we're going to want to know what's there. We're going to want to verify the concepts that we've put together to understand this evolution, and we want to be able to then learn new things by doing that. But with that comes the resources that we bring into the laboratory. At large-scale mining then would start, well, you need the water. You break up the water, of course, and you can breathe the oxygen, or you also you can drink the water. H2O is H2O, whether it's here or on the Moon. And then you can make the rocket fuel associated with it. So what will drive that more than anything else will be the need. You know, what kind of base do we create? What kind of capabilities do we need that extend well beyond the science that we can do, that then supports larger exploration initiatives? You know, maybe the base develops into a capability where astronauts are needed to go over the horizon and down on the far side to help pull together a radio facility and be able to then look back in time to what's called the Dark Ages, which is a 21 centimeter line that's been Doppler shifted now into the very low frequency radio regime, where we can only see it from the far side of the Moon. So there's many things like that where science and exploration is going to be connected. And the key to that in terms of large-scale mining will be based on needs.
Thank you.
You're welcome.
So Jim, how does the lunar North Pole compare to the South Pole for coal traps, and what kind of stuff we might find there?
Yeah, the estimate is they're about the same. You know, there's billion plus ton of water in the South Pole and in the North. So we could go to either one. The decision on the South Pole, I'm not sure I understand even how it came to that from a human exploration point. I'm just excited we're going to an area where we can do a tremendous amount more science, well beyond what the Apollo astronauts could do, because none of those craters are in shadow. They're all in direct sunlight in some way or another within a month period.
Hi. I had a question. So you mentioned that the astronaut Harrison, he determined that the orientation of the moon rocks, that was going to be important later on.
Critical.
Are there any curation techniques that we couldn't take advantage of now that we're thinking of using in the future?
Well, it tells us that when we go back to the Moon in this manner, we need planetary scientists that can actually determine what rocks we need, their provenance, all the how to manage it and take care of it, such that we can get the most out of these samples. This is like going to a brand new place. It's, you know, in a way, it's hard to think of it as the Moon because of all the other things that we're going to find out about it. That regolith has also been holding aspects of the solar wind. The solar wind generates helium-3. Helium-3 is a potential nuclear resource, all right? We don't know the distribution of helium-3 because we haven't really prospected. But when you think about it, on the far side, which as the Moon moves around the Earth, it's being hammered straight by the solar wind. On the near side, when it's a full moon, it's in the Earth's magnetosphere and protected. So potentially the amount of helium-3 might be much larger on the far side than it is on the near side. We don't know. The only way to do that is prospect it. Now, one of the reasons why scientifically I like the South Pole is that there's a huge impact area called the South Pole Aitken Basin. A basin is a very large impact. And so that basin has not been filled in significantly with magma, all right? When that impact occurred, most of the magma in the upper mantle lower crust was being shoved to the near side. And so consequently, there's mantle material laying there. Now, the Chinese have been there, and they brought back samples, and some of that's been analyzed, and there's some really exciting things about this mantle material we're bringing back. But with that, we're going to find that what hit the moon in that location must have had a differentiated core, and therefore it leaves iron and platinum group metals sprayed all over the place. So there's other resources that we might be able to get access to. On this Earth, between 50 and 200 years from now, our crust is going to be mined out of platinum group metals. And if we don't go through a recycling effort right now with all the equipment that we have, and we do, and we need them because they conduct electricity, but they don't rust, we're going to have to go to the moon and get new material. That's the place to go versus running around in the asteroid belt.
Thank you.
You're very welcome. And I think with that, I will have to turn the podium back over to Chris Carberry. Thank you very much.
Good afternoon, everyone. I'm Tiffany Vora. I'm honored to serve as the Vice President for Innovation Partnerships at Explore Mars. Today, I'm here to welcome you to this amazing fireside chat. We're going to be joined first by J.R. Edwards, the President of Explore Mars, who I believe you met earlier today, as well as Vanessa Weich. Vanessa is the Acting Associate Administrator of NASA. She's the Senior Advisor to NASA's Acting Administrator. In her role, Weich leads the agency's 10 center directors, as well as the Mission Directorate Associate Administrators at NASA headquarters here in Washington. She acts as the agency's Chief Operating Officer for more than 18,000 employees and an annual budget of more than $25 billion. Previously, Weich was the director of NASA's Johnson Space Center and its more than 11,000 civil service and contractor employees. Her responsibilities included a broad range of human spaceflight activities, including development and operation of human spacecraft and NASA astronaut selection and training. Weich also oversaw NASA Johnson's activities supporting the commercialization of LEO, supporting the agency's needs following the transition from the ISS in 2030, and led the center's programs supporting the exploration of the Moon and Mars, including surface system capabilities for human and commercial robotic missions, as well as simulated missions for crews on Mars. During her distinguished 35-year career, Weich has held several other leadership roles, including Johnson's Deputy Center Director, Director of Exploration, Integration, and Science Directorate, Flight Manager of several Space Shuttle program missions, and Executive Officer in the Office of the Administrator, as well as additional center-level technical and program organizations. A native of South Carolina, Weich earned a Bachelor of Science in Engineering and Master of Science in Bioengineering from Clemson University, and was inducted into the Thomas Green Clemson Academy of Engineers and Scientists in 2019. She received an honorary Doctor of Science degree from Coastal Carolina University in 2022, as well as an honorary Doctor of Humane Letters degree from Texas Southern University in 2024. Please join me in welcoming our speakers to the stage.
Thank you so much, Tiffany. Good afternoon. Vanessa, welcome. It's so good to see you.
Oh, well, thank you. I'm excited to be here.
Oh, thank you for joining us. we all love NASA. I think it's been 13 years, right, that NASA has been selected as the best place to work in the federal government?
Yes,
Yeah. So
And
you're
we
here.
recently just announced being selected as the recipient this year as well.
Wonderful. Congratulations.
Well, thank
Congratulations. Well, we're so excited to talk to you today, and I know we have a lot of topics to present. So let's just jump into it. So the first topic, there's been a lot of renewed interest in Mars exploration, right? Can you help us understand, what is the administration thinking about Mars? What are their plans?
Well, yeah, JR, it's exciting time, I believe, in space writ large, all of space. And especially right now, we are looking at the priorities that we're getting from the new administration, the focus being on going to the moon, going to Mars with humans. And the budget cycle is just now beginning and coming out, and we're understanding what the priorities are selected to be. For Mars, of the budget itself, there is an additional $1 billion of new investment for technologies to go to Mars. Most of that with a focus of what is it going to take for humans to get to Mars. We've been working, as you know, for some time with the Artemis missions of Moon and Mars, but this will give additional emphasis on what it means for us to go to Mars. So I'm excited about that. I'm also excited that we will be getting a new administrator very soon. Jarek Isaacman has been identified as the nominee. He's gone through his initial confirmation nomination discussions with the committee, and we're hopeful that he'll be voted on very soon by the entire Senate. And I think he has expressed, his commitment to those priorities as well.
That's really encouraging to hear, and we enthusiastically welcome the new administrator to visit with us as well. Yeah. You talked about human exploration, the fact that we are on this path to Moon and Mars. Can you help us understand NASA's view of the humans and human exploration?
Oh, well, since I hail from the Johnson Space Center, and one of the things at Johnson, our main focus is on human exploration. And having over 60 years of experience, first with Apollo, then building with the space shuttle, space station. And so we have the fundamentals that we've been learning about the human body, what it experiences, but we're also have been looking at, what does it take for a human to actually travel to Mars? And what does it take for us to be prepared for such a lengthy mission? The International Space Station is an analog. And what we're learning on the International Space Station, some of our missions are planned as 6-month missions. We have some that we go into it knowing that they're going to be lengthy. We've had at least 2 missions that have been over a year long. And so what we're learning about the body, what we need to be preparing for. Additionally, using the International Space Station as an analog for technology and being able to test out your environmental systems, those things that we could potentially try to study and simulate on the ground, but we know that it's a difference when we go into space. And so we have been learning those things, and then we have been planning and working towards, with our architectures, what does it require for us in terms of the requirements for not just the human, but all of the systems that we have to take when we go on these extended trips for extended durations.
Actually, you beat me to it. I was going to ask you about the tech. I'm a tech guy. So we're thinking about those future missions. Can you provide some insight to the relationship between human exploration and the robotics and the science? What role does that play?
Yeah. So right now, one of the things that we've been looking at, and I'm not going to steal all of his thunder because Jake Bleacher is going to come up after me and he's going to talk about the architecture, but how do you have the humans and the robots working together? We know that together that we'll be able to accomplish more, and so we're putting those into our plans. But actively, right now, we're looking at robotic missions. We already have robotic missions that we have sent commercially to the moon. And so as we're continuing to do those types of missions, and with our first Artemis missions and sending our humans, and then we'll be able to robotically set up habitats. We'll be able to robotically have the robots go out and do excavations while the humans are preparing and getting things ready for further exploration. We've looked at what does it take for us to be able to just do these missions robotically, but to have the human then to be there, especially if you're at Mars. And you have a time delay. You're not going to be waiting for all of these things to go back and forth. With the human's mind, you're going to be able to actually do things quicker. And so putting and pairing the two together to actually extend the capabilities that we have are one of the big things that we've been thinking about. And we can simulate that here on Earth, but again, we can also do that with the other platforms that we have as well.
You mentioned Artemis. So in this audience and those watching, many of us are space enthusiasts. But for those who are watching who may not have been plugged in and have not been following all the missions, can you tell us a little bit about Artemis, those programs, any progress made to date?
Yes. So, with Artemis, we have successfully completed an uncrewed test of Orion with the Space Launch System, which is the rocket that we'll be using for that. And so we've been preparing for our second mission, which is now a crewed mission. And we have, I was recently just in Florida and had the opportunity to go over to the vehicle assembly building and see the booster all stacked up, and it's going through its final preparations to get it ready. And Orion is actually just was turned over from Lockheed for the mission itself. It is right now being fueled, and our astronauts will actually, in about probably another month or so, they'll be able to go in with the suits that they're going to actually be using during the mission and get into the spacecraft. That'll be the first time we're able to actually make that. And then we'll be ready following some additional testing to put the spacecraft with the launch abort system on top of the rocket, roll out to the pad. So we're on track to be able to do that mission. We announced the actual astronauts now, gosh, it seems like it's been a couple of years ago, with Reed Weissman is the commander, Victor Glover is the pilot, Christina Cook is mission specialist, and Jeremy Hansen, Canadian astronaut on the mission. So they have been training. They are very excited about the mission, but now it's getting all of the final integration, all of the preps done, and actually being able to launch them from the Kennedy Space Center in early next year.
Okay, one of our charters for the organization is that we must ask some critical questions. Mm-hmm. We must ask, are we on track to realize our visions for exploration? Are we making progress? And in your view, are we on the right path? And then the follow-on question would be, when? We often hear that question, when will we set foot on Mars, right? So any thoughts about that?
Yeah, so, I was thinking about it on my way over here. So when I was in what was then the Exploration, Integration, and Science Office at Johnson Space Center in 2016, I remember we were trying to put together what the plans were. How could we get everyone in the community to get on a singular plan? And there was a lot of work done by a lot of people all around the world to get us to the plan and to the path of Moon to Mars. Before that, it used to not necessarily be. And so, but having a, hey, we're going to figure out what are the things that we can get done at this body that's closer to Earth than this other one. We can lay out what are the technologies, what are the requirements, what are the things that we can do at the moon that will help us to be ready for Mars as we mature the technologies that we need for Mars, the power systems, the propulsion systems, what are the capabilities that we don't currently have that we can test out at the moon and then go on to Mars. So I think that the path that we're on, I'm not going to steal Jake's thunder, but putting together an architecture that identifies these are the steps that we need to take. And it's not looking at it just from the human side, from the vehicle side, from the science side, from what are the new techs, but actually rolling all of that together. And so what we've been able to do is we rolled out the Artemis architecture, Moon to Mars architecture, and so we've been each year internally getting together and saying, okay, what are the progress, what are the milestones that we've actually met, but also meeting with industry, meeting with academia, meeting with our international partners on a once-a-year cadence and checking back in and saying, what are the things that we might need to tweak? What are the things that, where have we made the progress? But doing that in an annual cadence so that we are measuring what we're doing.
Thank you for that. It's an exciting time for all of us as we think about those future missions. Last year when NASA visited, NASA shared with us that the missions were upon us. So we've heard that message consistently that we're making progress towards those first steps on Mars. Over our careers, we've seen this evolution, the changing landscape of the workforce across government, across industry. I think back to the rise of new space, which essentially has now become space. Help me understand, from your background, having worked at Johnson Space Center, do we have the right workforce in place to realize the vision for exploration?
Yeah, so in terms of, to me, the vision for exploration is inclusive of our industry, again, of our international partners, our academic partners. It's inclusive of how we do things. So doing some of the activities in a purely commercial aspect. Some of the activities where we're investing in. So again, if you think about the missions that we've been doing to the moon, the commercial lunar payload services, where NASA is investing, but then the companies are actually going out and they're getting other investments, other people that want to go to the moon, that are wanting to do things that are separate and different from what NASA's doing. And partnering together. So the workforce that it takes to do that within the government, we need to have people that are able to look at doing hands-on technology. We need to have scientists that are putting together new research, but we also need to have people that have the ability to identify innovative ways of doing things and to say, okay, NASA doesn't need to do this. Someone else can do this. How do I empower that? We call that being a catalyst. How do we have people that can be a catalyst as well as people that are doing hands-on work? Ultimately, what we're trying to do is build a workforce that has, I would say, the technology, the scientific knowledge, but also a workforce that is willing to think outside of the box of how we can do these things. So I think it's important for all of us to work together on ensuring that we have, the workforce that we need. If you think about where we are today versus where we were 10 years ago, I think that the skills that we have internal to NASA, as well as the skills that we have external to NASA, have evolved. And so what we're trying to do is make sure that we're building a workforce that can actually do that as we move forward. Taking advantage of AI. I know you probably have had a session on that. I've had a session where someone asked, should we be afraid of AI? And it's like, no, AI has evolved. It hasn't been, when we first started working on it back in the early 80s to where it is today, it certainly has evolved, and we as humans evolve, so we have to have our workforce evolve as well.
You gave me so much to work with there, because what I'm hearing you say is that NASA is seriously thinking differently about how business is conducted. About it warranted this. The new contracting vehicles, for example, they warranted a different way of thinking about how we move along this path. When we talk about efficiencies in the federal government, we talk about being a catalyst to spur that innovative spirit. I mean, all of this is really exciting and seems to be a crucial element for those future missions. How do you nurture that innovative spirit and drive within NASA?
Yeah, I think, JR, it's about helping people to understand, the vision. And for me, when I think about the what NASA, what, we as a country or we as a world plan to do in space. We do what we're doing because of scientific discovery. It's what we want to discover. And so how we go about doing it is the opportunity. We can, decide that we're going to rest on our laurels and try to continue to do something that we used to do 60 years ago. But we also know that, others will leapfrog us. So then if we don't take advantage of new tech, of new ideas, of new innovations, then we're not going to be the ones that are leading going forward. So I do think that, as a world, it's a great opportunity. If you look at, especially the commercial aspects of space, how much it has grown and is expected to grow. And so, some of it, yes, I would love for us to be doing some things today that we've not yet figured out how to do. How can we get to Mars faster, than having to go for several months? But to me, that's going to really take us, really having a workforce that can think about, yes, we can do that, but we just have to put it out there, and we got to figure out.
You are singing my tune, because from a business background, we were always focused on faster, better, cheaper. Where are there opportunities to improve? How do you inspire greater agility within the organization at an enterprise level? And it sounds like NASA is seriously thinking about these things and taking meaningful actions to help move us along this path.
Yeah.
You actually moved up from Johnson Space Center as center director to assume this role about 3 months ago, right? How has your view of NASA within the agency changed? What have you seen that's different or that might have been surprising coming from that role as center director to this position?
So as a center director, typically you have your portfolio of things that you're responsible for. And so at Johnson, human spaceflight, but we have responsibility for science and for technology as well. And so we work with internationals. However, a lot of the evolutions that we've had within NASA has happened in the human side. The work that we've done with commercial cargo, with helping others that have developed their own vehicles that we now pay them as a service to provide cargo back and forth to the International Space Station. We've done that with commercial crew. We've had with SpaceX and with Boeing on the commercial crew side. We've also been working with the Science Mission Directorate on the commercial lunar payload services. We've actually been running that program for them, executing that from Johnson. So a lot of the evolutions and things that we've been working on, I've seen that from the center level, but from across the agency, how do we instill that? How do we have that happen through our cross directorates? And so seeing that from that perspective, and then also from my standpoint, I've been actually, I'm a nerd at heart. And so I've been learning a lot. I've been learning about all of the great things that we're doing in terms of like helping with like firefighters, forest fires, using our assets that we have for space to help with that. How do we use drone technology to help with the fires that we've been having across the United States? It's been fascinating to me. So expansive, and NASA, you know, when you tell people, you know, space is large, space is, you know, and they go, you know, of course it is, but when you're looking at all of the science missions, it's discoveries that happen every single day across NASA. It's phenomenal.
You just hit on something really significant. You speak about the vision, and you speak about value, value in so many aspects, value to the nation, value to the taxpayer. So thank you, NASA, for all that you're doing that has helped to improve life for us here on Earth. And we are certain that that same benefit will extend throughout this journey as we return to Moon and then on to Mars.
Right. Well, NASA, you know, and I you know, want to make sure that everybody is clear. You know, yes, there's the 17,000 civil servants, but there's all of our industry representatives. There's all of academia. I mean, there's a lot of people that are a part of NASA. You know, when I meet people and they ask me, oh, how can I get a job at NASA? And I said, well, the government isn't hiring, but guess what? This company is hiring. This company is hiring. You know, we're all a part of NASA. You know, I think it's more of an ideal.
Yeah, that raises another question. As we think about the evolving landscape of the workforce, do you see that changing across government, across private sector in the out years?
Well, you know, the only thing I would say, I think they're going to be the fundamental basics that we're going to always need to have, right? But I do think as we, you know, learn and have use of different technologies, you know, there may be, for example, I would say, maybe 10 years ago, we didn't maybe have as much of an emphasis, probably should have, on cyber, right? But now, of course, everybody understands that value, right? And so now there's more emphasis, more going into that. Likewise, you know, I believe that it's in terms of the skills that we need for the acquisitions, right? And so making sure that we have people that are prepared to actually have the ability to help us to acquire things. It's more important.
You know, I'm also reminded, you know, as you talk about, you know, the evolving landscape of these new technologies that are coming online for young people who are watching, there were certain things that fascinated me when I was young about, you know, space exploration, about the great possibilities. What inspired you to even consider a career in space?
You know, so for me, JR, I grew up in South Carolina. There was no space, you know, center nearby, but I did have Star Trek.
Okay, yes.
And
a lot of Trekkies in the audience,
yes.
right?
And you know, and that's what inspired me. And what I loved about it was, you know, yeah, beam me up, Scotty, and just you could I could imagine that was possible. Yeah. And so I think for most of us, you know, it was something like that. That, you know, just kind of sparked the idea that we could do something.
Like the holodeck.
Yeah, exactly. Yeah.
Well, we are so grateful that you joined us today for this really timely conversation. We, as you see, this is the inaugural Humans to Moon and Mars Summit.
Yes.
So we're very much emphasizing the link that exists between the work that we're doing now to send humans back to the moon and how that folds into that exploration vision for Mars. So thank you, NASA, for all that you're doing to lead us forward, and thank you for all the great work and the discoveries that are happening. Before we conclude today, I did have one final question I wanted to ask. If you don't mind, what is some advice you would offer to our audience? What are the key takeaways that you'd like us to have about these plans for Moon and Mars exploration, and how can we, as a community, help to enable, to accelerate that path going forward?
Yeah, what I would say is kind of like, as I mentioned, years ago when this was just, human to Mars, that was, the summit when it first started. But now with it being Moon and Mars, and it takes all of us to give our ideas. And so there's different ways to be able to do that. Like, the academies has studies, members, there's probably members of the academy here, being a part of those studies, giving your input to like the league and to the MPAG, and making sure that you're getting your thoughts in. As I mentioned, when we have those Artemis workshops, we go to industry, we go to academia, we want feedback. We want you to give us what your thoughts are. But also, just together, the ideas, putting together, hey, here's an idea of how we can do something differently, and submitting these ideas. Unsolicited proposals will be, I feel, very welcomed, because, there's many very smart people that have ideas that they probably want to put forth. And so I would say to anyone, encourage you to bring them forward, and let's talk about them. Let's figure out, because we need the best and the brightest. I know you had a panel earlier that talked about, are we in a space race, and should we be in a space race, and all these different questions that we have. I think it's about us being in a race for humanity. And so everybody should be thinking about what we can each contribute to helping us to win the race, but winning it for all of humanity.
Thank you. That was a powerful closing comment. That inspires me in this moment to as we think about all of the deals that are taking place. This is an environment of negotiations. Now seems to be the time for folks to step forward with their best and brightest ideas, right? So it seems to be a moment of great opportunity. So thank you so much for reminding all of us that in this moment to not be shy about offering those visionary thoughts and ideas that will help to advance our exploration goals. So, thank you so much. Is there anything else you'd like to share with us to perhaps encourage young people who are considering future careers in aerospace?
I would say, now is an exciting time to be in aerospace. It's an exciting time to take advantage of aerospace. Not all of the things that we're doing may necessarily seem like they have a benefit external, but they do. And so helping our young people to know that there's definitely room for all different ways to contribute. I jokingly one time I was talking with someone, and I was telling them about all of the different careers, everything from, at least especially in human spaceflight. I mean, we need to have doctors, we need nurses, we need pharmacists. There's lots of different careers. All of the careers that apply here on Earth, there's a role in space. And so as we go forward, think about, what that looks like and how you can contribute and be a part of that. And just know that, this, what we're building in terms of, we've been working on commercialization of space at the Johnson Space Center. And so, how do we help with the commercialization of low Earth orbit and the things that you can do in low Earth orbit that you would not necessarily want to do when you go to the moon or go to Mars? but helping people to understand the opportunities that are available in terms of businesses. If you could actually be an entrepreneur, what would you want to do in space? And that excites people as well.
That commercialization you talk about, how is that defined within NASA? What does that commercialization look like?
So again, it's about meeting NASA's objectives, right? But if you can have someone spend or invest and they build something that NASA could also use, but they can use it for another purpose, then that meets both of our objectives. And so helping others to figure out ways of being able to do that. We also know that from a exploration standpoint, as I mentioned, we're using the International Space Station for those purposes today. We will want to do that on a platform that is closer to home, that you can get to within 6 hours. And so helping people to think about what would you want to do on that platform. But that's a part of NASA's role. And it's always been a part of NASA's role since NASA was formed, was to explore, but to also to do that for economic purposes here on Earth.
So now you hit on another topic, since you brought it up, this idea that space can be an economic engine for growth, right? Mm-hmm. And I just want to thank NASA again, because a lot of the work that's been done has spurred innovations in many different sectors. So we expect that will continue going into these future missions, right?
Oh, absolutely, okay. Absolutely. I think that if you ask most of the entrepreneurs that are looking at, what are they going to be doing, on the moon, they're not doing it just for the purposes of going. They're doing it to figure out how they can make a market, how they can figure out, so you have people now that are trying to figure out how can they be the first to, if you're going to have infrastructure, how can I be the power supplier? How can I be the one that's providing the communications? They're thinking about it from that standpoint, yes.
So you've heard it here, that NASA welcomes those big innovative ideas, that welcomes Absolutely. That entrepreneurial spirit. Would that be a proper assessment?
Oh, absolutely, okay. Absolutely.
Well, Vanessa, thank you so much for joining us. This has been a delightful conversation. We thank you for your leadership, and we salute the entire workforce of NASA for all that you're doing to help move us along this path, returning to the moon and then on to Mars.
Oh, no, but thank you. And thank you for everyone that's here, for what you're doing for our Moon and Mars Summit. We really look forward to, the conversations. And Jake is going to be coming up very shortly, and he's going to be talking to you more about some of the plans as well. So
excellent.
Thank you.
Well, thank you so much.
Thank you. Thank you.
All right, thank you. Thank you very much. And just so we're about to take a break, but before the break comes, we have a video statement from Representative Herodopoulos. So can you cue that up, please? Then we'll be 15-minute break after that.
Mike Herodopoulos, a proud member of the United States Congress, and of course the subcommittee chairman for space. I work with Dr. Babin from Texas, of course, as the full science committee chairman, and we are leading the fight to make sure we stay space dominant. It's an incredibly important issue, not only on the Space Coast, but of course here in the United States as we take on the communist threat around the world and other rogue nations. I want to say thank you for allowing me to speak to such forward-thinking people who understand the complexity and just the fact that space is difficult, it is hard, and we need to do everything we can to win this space race and stay space dominant as we face these emerging threats. It's a national security issue as well. My own son serves in the United States Air Force, and we want to make sure that they are protected. Those men and women in the military rely on our satellite technology to make sure we know where the bad guys are and operate successfully, especially the new emerging weapons like hypersonics, etc. We also want to make sure that we are moving towards going to the moon first. Artemis is almost ready. As you know, it is prepared to go next spring. We're excited about Artemis 2 as we get closer and closer to going to the moon for the first time since 1972. But it's not just about exploration, it's also about national security. Ultimately, we'd love to go to Mars, but it's the moon first, because the national security component is the most immediate threat in which we face. So I want to say thank you for your forward thinking and making sure we're always staying one step ahead despite some of the devious acts by the Chinese, such as stealing technology and other, let's just say, unique actions by them, which included, of course, collisions in space, etc. In my home community, of course, we have some of the most amazing companies in the world leading on the front edge. L3 Harris, Boeing, Lockheed, SpaceX, Blue Origin, just to name a few of the companies such as ULA that are doing remarkable things right now in space. And these are not just jobs, these are careers. These are people who are dedicated themselves to science and moving this country forward and making sure that we stay one step ahead in the technological innovation. So thanks again for allowing me to speak with you today. It's an important issue. I look forward to you visiting with me here in the Congress as we take on these challenging issues. And remember, our goal is clear. Make sure the United States is space dominant.
I guess we're up. Okay, we are beginning the last break of day one here at the Humans to Moon and Mars Summit. That was quite a conversation that J.R. Edwards had with the acting associate administrator. And J.R. may be joining us in a few moments. Go ahead through, folks. We don't want to hold you up. Fly on through there. It's only television. So while we wait for JR, we wanted to talk to someone that, if you were with us, you heard earlier today in the discussion about well, here's the title. What are the most significant hurdles that need to be overcome before humanity steps on the surface of Mars? And someone who I think was critical to that conversation, because really human factors are what frightened me the most, is standing with me now, Eric Antonsen. And you are, with Mass General Hospital, associate physician, it says here. You got to explain, first of all, that NASA-worthy acronym SPEAR.
So SPEAR Medicine is a new division at Mass General Hospital and Harvard Medical School in our training curriculum. It is Space, Ecological, Arctic, and Resource Limited Medicine.
It covers a lot of ground.
It does, and part of the reason why it does is because we believe that health in resource-limited settings exists on a spectrum, and they are heavily ecologically dependent. Here on Earth, our health depends on our climate and what is going on around us, and pollution, and all those types of things. And when we go to space, we have the most fundamental job is rebuilding an ecology in which we can survive as humans. And we've done that since 1961, step by step by step, going a little bit further out and sometimes staying a little bit longer. But when we try to go to Mars, it's going to be the largest leap we've ever tried, and it's going to be a much larger leap than what we did trying to get to the moon for the first time, for a whole variety of reasons. So a big part of the Artemis program, the Moon to Mars objectives that NASA has and that others are signing on to, is trying to make sure that we have the opportunity to iterate on how well are we doing with supporting the humans who are going to do these jobs, making sure that we can maintain their health to the level where they can actually do the jobs that we want to send them to do, the science. But beyond that, also their lives and the success of the mission depends on their ability to be able to maintain, repair all of their equipment, the vehicles themselves, be able to take care of each other. And they have to do this in a new paradigm where they're not getting to rely as much on the real-time support from mission control. So taking that out and then re-envisioning how we do that is a critical part of our stepwise iteration through the Artemis program that needs to be done and demonstrated before we try to go to Mars in a meaningful fashion.
Part of the discussion was on exactly this, and it was so interesting to hear this conversation. I'd never really sunk into me before. Yeah, they'll be out of touch with ground crews on Earth, but you're going to be asking these astronauts, these Martians, to do things that no astronauts have been asked to do before, like maybe refueling their Mars ascent vehicle, which normally would be done by specialists on Earth. It's a lot to ask. Are you hopeful that we can keep humans not just alive, but able to do all of this work, especially after 8 or 9 months in microgravity.
So I am hopeful, and I think that we absolutely can do it. The real question is not can we technically achieve it, but how much risk are we taking along the way? So if we were to bypass the moon and go straight to Mars, we would be doing a whole bunch of things like you just described for the first time, right? Trying to have our crews get out on the surface of Mars after 6 to 9 months in a transit in microgravity. When they come back from the space station, they have 40 people there helping them. That's not going to be there, right? How long does it take for them to actually get up, get moving, be able to be functional enough to do the jobs we send them to do? What happens when you remove that real-time link and they're the ones who are responsible for identifying when small problems have happened in these complex systems we've built? Not just identifying them, but figuring out what went wrong and then determining what to do to fix it. Because it's a completely different operational paradigm than we've been through before. So even though we've been learning every step of the way, these are new steps that we're taking. And it's critically important for us to kind of take them in a stepwise fashion, make sure that we get through the Artemis missions, iterate on the things that we find challenging. I mean, we had a fantastic picture of all the different Martian core samples that are waiting there for humans to pick them up or to be sent back by a Martian mission. And that group talked about the Apollo 17 mission where they did the first core samples, and they're still opening them. But here's the funny thing, from the human side of that story, what I remember is that Apollo 15 tried to do that first, and this drill got stuck in the regolith because it wasn't designed. They didn't assume it was going to be as hard as it was. So they had to iterate and do it in Apollo 16 and Apollo 17 when they went back. We can't afford that in the first Mars trip. We have to try to fix and set up these problems with the right designs on the front end so we have the best chance for success for the science and human survival.
You made me think of a robotic mission that also had trouble with the drill, the InSight mission, with its mole, which was tested endlessly on Earth, got to Mars, couldn't get down more than a couple of inches, a few centimeters below the surface. I think this also says something about the value of having humans, as difficult as it is to keep them healthy and happy.
Absolutely. And this is part of the reality of ambitious engineering projects. Things don't usually go right the first time. That's why we have to iterate and try to learn from every analog that we have for Mars, to get good enough to make sure that we meet the mission objectives, right? And try to get everybody back safely. But the risk is going to be immense. There's no way around that. One thing I will note is that all of those samples that are sitting on the surface of Mars right now, they were collected over a period of several years. And that rover went about 35 kilometers.
Still going, but yes.
Going.
Right.
Apollo 17 went about 35 kilometers and picked up 110 kilograms of rocks that were human selected. And so it really kind of highlights the value of the humans and the ability to help enable the science that builds on all the success that we've had with the robotic programs.
Let me follow up on something that I think you implied when we first started to talk a couple of minutes ago, and that is what we learn about keeping humans healthy in environments like Mars and deep space. Is that helping us keep humans healthy and happy here on Earth?
Absolutely. And I think that it's not just in the health domain, but health domain is one of those areas. Everybody can go to nasa.gov and look at the spin-offs page, right? There are so many different ways that the things and the technology that we were forced to make in order to meet problems in spaceflight have spun off into Earth technology. Many of them have existed within the health domain. Some of them led to new valves for artificial hearts and other things like that. And you can find complete lists of that up on the NASA spin-off website. But it's also helping us to look at how we do medicine in remote environments, in resource-limited environments. People go all over the world to very challenging environments, and space is just one more extension of that. The lessons we learn in space translate backwards. When we look at the first Mars mission, what better way to really learn a lesson about resource management and renewability and reusing everything that you have than in a place where you absolutely have to do that to survive? It's teaching us a lesson about our climate. It's teaching us a lesson about how we live as humans. We're not just going to Mars to learn about Mars. We're going to Mars to learn about us.
Great way to finish. Thank you so much, Eric.
Thank you.
Eric Atkinson, Dr. Eric Atkinson, MD, from Mass General and that SPEAR program, that great acronym that he just told you about. I'm Matt Kaplan, Senior Communications Advisor for the Planetary Society. We have a few moments left in this last break of day one at the Humans to Moon and Mars Summit. And so we hope that you will stick around. There's some more great stuff coming up, including Janet Ivey. I haven't seen Janet yet, but I think she's going to be here to give out an award, the Mars Innovation Challenge Award. And JR is here. I'm sorry, I looked right past you, JR. Come on over. I was just opened this little segment. Come over here on this side of me so I can get you looking over at the camera. Marvelous interview with the Associate Administrator, Acting Associate Administrator of NASA. Great job with that.
Oh, thank you. Yeah, NASA's in a period of transition. I mean, we're accustomed to these changes that happen periodically.
I know why I'm here. This is so much work to put together, so much coordination. Why does Explore Mars go to the trouble of putting together this summit every year?
Oh, great question. This is an incredible time to be part of this experience. As we mentioned in that conversation, this is an opportunity for the best and brightest ideas to come forward. And what better way to help inspire those conversations than gathering together and exchanging those ideas in person?
Yeah. I'm thrilled by not just the program this year, but the caliber of people. Your interview a few moments ago was a good example of this. Certainly my opening panel this morning, I was blown away by the 4 scientists that I was able to host up there. And these are difficult times. It's a difficult time for NASA. Everyone's a little bit uneasy about where things are going, and yet Explore Mars has still had this amazing turnout of people that we're seeing on stage.
Well, that is our commitment to the community. Our commitment is to stay the course. We are laser focused on realizing those visions and following around those critical paths. I grew up in Indianapolis, Indiana. I'm a Hoosier native, a proud Hoosier native. I've heard those 33 engines start in the Indianapolis 500. I was there this past weekend. But I got to say, 33 Raptor engines, that's nothing to sneeze at. so I get it. But here as a community, periodically it's useful for us to gather together to take a serious look at these wonderful ideas that are being brought forward by visionary minds throughout the sector, and then chart those paths forward, and then hold ourselves accountable as we're thinking about progress made, thinking about the opportunities ahead, and ensure that we don't allow slippage in the timelines as we move towards returning to the humans and then stepping forward to put humans on Mars.
Just say a word before we wrap up about what else Explore Mars is up to. I mean, as an example, I had Tiffany Vora a few minutes ago standing where you are. You're Vice President for Innovation Partnerships. I was at the Mars Innovation Workshop that she headed out in Silicon Valley. I mean, that's a good example, I think, right?
Absolutely. So from our workshops that happen throughout the year, I mean, what you're experiencing now is the summit, where we bring all of the stakeholders together to do a tag up of sorts. But day to day, we are there, engaging with policymakers and key stakeholders around the country, not just around the country, but around the world. And in fact, as you know, space is one of those areas where we have strong bipartisan support for all of these missions, and we want to make sure that we sustain that going forward. So we, along with other organizations, are right in there having those crucial conversations to ensure that we have the proper resourcing required to realize these missions, and that we're demonstrating the value back to our citizens, the value back to the taxpayers who are investing in these programs, and also sharing that message. How does this benefit my daily life? How does that benefit life here on Earth? There are immediate benefits to all of these journeys that we're taking.
As we just heard from Eric, who was standing here a few moments ago. JR, thank you so much. Longtime board member for Explore Mars, and most recently, president. You serve as president of the Explore Mars nonprofit, and thank you for bringing us all back here again this year.
Oh, thank you so much. And again, thank you to all those who are watching with us live stream. We also welcome your involvement year-round. There are plenty of opportunities to engage. So stay focused on Explore Mars. There's more to come.
ExploreMars.org.
Yes, indeed.
All right, we'll give you a couple of minutes to enjoy what's left of this last break on day one, and I'll close out with what I said before. We have a few other great segments left. We're going to be hearing from a guy that I just had on because of his fantastic book, A Quantum Life, Hakeem Oluseyi. astrophysicist, has one about Moon and Mars logistics and pulling off this incredibly difficult endeavor, which we are all looking forward to here at H2M2. So we'll leave it at that, and I think I'll be joining you again at the end of today's program, and we'll see you in just a couple of minutes as the program picks up again on stage.
Jake's, I've known Jake for a number of years, Chief Exploration Scientist and ESDMD, and he'll be talking about this ongoing process. It's been how many years, like 3 or 4 years now? Going through the objectives onto the architecture process. Basically, it's going through NASA's current progress on NASA's architecture program for getting us back to the moon and on to Mars. So, Jake?
Thanks, Chris. All right, thank you, everybody. So it's a pleasure to be here. It was great listening to Vanessa talk about where NASA stands from kind of a high level. And what I'll do now is start working on a little bit more detail about where our planning is at. So we'll provide a quick update on I'm not sure where I need to point this. Well, could I have the next slide, please? I'll provide an update on where we are Moon to Mars planning-wise and talk a little bit about where our Artemis planning is at currently, talk about how we're developing our architecture, and then give you some updates that are relevant to that Mars forward-looking plan that we have in place. Next slide, please. Oh, that worked fast. Now it's working. So we'll just start with some basic questions, and this is kind of the question that we start with is why? Why are we exploring? And if we ask, why Moon to Mars, you are all calling this meeting Moon and Mars, it's pretty straightforward. The Moon is a place that is away from the Earth. It has some commonalities with going to a destination like Mars. But it's not identical to Mars. So it's part of a path of learning to explore away from the Earth. But the Moon is a lot closer, so it gives us an opportunity to test out some concepts, some operations, some hardware, while we're still a little bit closer to home. Maybe we can get home a little bit quicker if we need to. We can ask for help a little bit more easily. Heard reference this morning to how long it can possibly take when the Earth and Mars are on the opposite sides of the solar system from each other. It's not a simple conversation. So we're learning as we go, but this is the path that we're on. But it is good to keep that in mind as we think about what we are planning for. We've talked many times in public now about why we explore, and you can kind of answer this question in different ways. We chose to focus on several areas: science, inspiration, and national posture. So from a science perspective, we want to learn as we go. We're going out to these destinations away from the Earth to answer questions we can't answer here on Earth. The atmosphere, the environment that makes life capable of growing here on Earth also erases much of the evidence about our history. So there's science we want to do, but the science is also, I like to say, the toolbox for our survival. So understanding the environments that we're expanding into, that we're growing into, that's how we learn how to design our systems. We have to query the location so that we can understand what we're planning for. But we also do that, as we do that, those are bold challenges. So we're inspiring the next generation. We're inspiring our partners as we go, because we want to make sure that someone picks this up as we move along in our career path. And then the national posture is another key piece. The things that we choose, the challenge we choose to tackle, put us in a position to partner globally. So these tough challenges we present ourselves with, that we try to address as we develop our architecture and explore into the solar system, put us in that position to partner. So these are kind of the whys that we say hold up the value of our exploration. Now I'll talk a little bit about where we stand right now with respect to Artemis. So we've got a good bit going on. If you haven't been paying attention to the Moon side of this conversation, we've flown successfully Artemis 1, learned a lot from that flight, and now we're prepping for and ready to fly Artemis 2 early next year. Here you can see just some of the activities that are underway. The last time I was at Kennedy Space Center earlier this year, the core stage was laying horizontal, getting ready for stacking. But you can see it here now being placed on that kind of on the left there, being placed beside the rocket boosters. So we're really starting to bring that rocket together. That's going to get us out for Artemis 2, which will be a crewed flyby of the Moon. So similar to the Artemis 1 mission, but now we'll have our friends on board because of the lessons we learned from our tests already. Bringing up our friends, that second video over is recovery testing in collaboration with aspects of the DoD, and now we're involving the crew in that. So when they come home, they will splash down in the ocean and we will recover them. So we want to make sure end to end we've got this process worked out and that all the entities that are involved in that process know what we're doing. And the second off from the right there, you can see working at Kennedy Space Center, our exploration ground system and teams have integrated the interim cryogenic propulsion stage. So that's the thing that gives it the kick to get out to the moon and around the moon. So all these pieces are starting to come together. And then you can see on the far right, Lockheed's completed its assembly of the Orion, and that's been handed off now for full integration into the overall system. So we're really moving forward pretty quickly now, getting ready for that flight with our astronauts on board to fly around the moon. Artemis 3 continues to progress. On the left there, we've got some testing involving some of the suit components, the boots, going through some of the expected types of steps, literally, that it might be taking when we get to the moon. SpaceX partner is working on retrieving, for the second time now, its heavy booster, so we're moving along with some of those capabilities. Again, Orion from Lockheed putting the Orion together for us. The liquid hydrogen tank for the SLS coming together so we can get these things assembled. And then off to the far right, we're starting to test out some of the operations that the crew will actually be doing when they get to the surface of the moon. So Artemis 3, after we fly around the moon with crew on Artemis 2, will be that landed mission on the moon in the South Polar region. So that's the moon end of this. And so that's kind of where we are right now with operations and getting ready to fly. As we're doing that, we continue to look forward beyond that, and we are thinking through what the architecture can look like. This process, what I want to talk over the next few slides about is the process that we've been undertaking. Our attempt now is to be very transparent, to communicate with the community exactly what we're doing. So in this diagram, what we kind of show here is off to the far right. Those are our objectives. We started with our Moon to Mars objectives, and as Chris said, this was several years ago. It's back in 2022, 2021, we started having conversations within NASA, with our partners within the United States, industry, academia, other US entities, and then even globally, talking with some of our international partners about what are the objectives we hope to achieve by going to the moon and then forward to Mars. Now that we have those codified and written out, and if you look at that QR code in the bottom left, you can go to the Moon to Mars Objectives document. That's a NASA level document. Everything that we are deciding now is in an attempt to address one or more of those objectives. So those are the guiding document for us. What we've put in place now is called the Architecture Concept Review. So each year we go through a series of studies focused on making decisions to help us establish that architecture and meet those objectives. So the first round of that in 2023 was really just getting that document written down. The architecture definition document, ADD, is what we release publicly every year as we go through that review cycle. We put that document out so the whole community globally can look at where we stand. It's a snapshot of where we are. But by consistently going through review cycles on this development of our architecture, our intent is to be flexible, adaptable to any types of evolution that we need to account for. Continuing to try to address those objectives on the right, but each year we can assess where we stand right now and we can look at trades. Each year we also, after we release the architecture definition document to the public, we hold a series of workshops. One here in the United States with our industry and academic partners, and then we also have one with our international partners, sometimes here in the States and sometimes overseas. So traceability is key to us. Everything we do traces back to the Moon to Mars objectives. We like to take those objectives and what we've done, we call it a decomposition process. We've broken that down into what we call characteristics and needs, and then ultimately use cases and functions. So really, what do you need to be able to do? Some of those objectives are written very broadly. And so you can't simply say, just go, you can't tell our engineering team, go meet that objective. So we have to break that down into a list of the specific things that we can do, basically the capabilities. All of that is documented on our architecture definition document, and you can go look at that anytime you want. As we work through this, we've set what we call a series of architecture segments. So a segment would be some piece of that overall architecture, and it shows our progressive increase in complexity, objective satisfaction, and basically the increase of capabilities that we would have by putting in place the next decided upon pieces of the architecture, elements, if you will. So right now we're in a phase we call human lunar return. We're going to a place, you heard Jim Green talk earlier this afternoon about, the south pole of the moon is really a very different place than what many of us think of as the moon. So we really are in this early stage or early segment is going and proving we can go there and get home safely. We want to bring our friends home, and that's what Artemis 3 will kind of pull that together. After that, we go into foundational exploration, which is where we start expanding our capabilities. So not just going and coming back from a series of different locations. Apollo proved that we can do that. What we're now starting to do is leave behind infrastructure so that we can reuse it. That's how you begin to increase the capability that you have on the surface, reusability of some of that hardware. So as foundational exploration proceeds, we'll start thinking about things like surface mobility. How do we cover more ground? How do we spend more time on the surface? How do we gain more access to the lunar surface itself and the lunar environment? As we're going into that stage, we'll start thinking more about how we can branch off to go to Mars. And so we'll have a Humans to Mars segment that starts off, which is the beginning of that Mars part. There will be future Mars segments. We don't know exactly what they are yet. At the same time, as we kind of branch off and continue into what we call a sustained lunar evolution segment. So that's where we start seeing increase in partnership and partner activities on the surface. It's not NASA alone and our US partners, but maybe industry and increased industry presence as well as international presence. So that sustained lunar evolution can evolve and grow from that branch off point there as we think about how we go and tackle Mars. I talked a little bit about these products, just wanted to put a QR code up there so you can access them yourself. But the ADD, Architecture Definition Document, is the key document. That's where we have everything written down. You can go look at that, read the sections that are relevant to you, read the whole thing if you want, but it is a rather big piece of paper. It's about several hundred pages long, but it's got everything in there. Again, it's a snapshot of where we are at the time we put that document out. We do have an executive overview, so that's the shorter version that kind of hits the high points and the updates year to year. So you can also start there. Then we have a series of what we call architecture white papers. The white papers are much shorter, about 5 pages long, and they focus on really questions that either we are asked by you all very routinely or questions we're asking ourselves, and we want to communicate with the community on that. So the white papers are a great place. I heard Jim talking this morning or this afternoon about going to the South Pole. We have a white paper, why Artemis is focusing on the lunar South Pole, and you can go in there and in short order kind of read up on that and understand the intent. This is a list of those white papers by the year we publish them. So we have moon focused, we have Mars focused, and we have some that are cross-cutting for the capabilities that we think probably are something we need to talk about in both destinations. I won't read through the list. Again, QR codes so you can go find them. If you get to the architecture definition document page, you can find these as well. But these are kind of, again, reinforcing the message that's in the architecture definition document. And these are probably a little bit easier to digest if you have specific questions you want to look at. So that would be a starting place I would suggest to go look if you have questions about what we're talking about. In the last round, we released some decisions on 2 new elements. One of those elements is an initial surface habitat for the moon. Down on the bottom left of this slide, you can see how we trace those. I mentioned the functions earlier. Those are the things we have to be able to do. So we show the traceability. Each element traces to key functions that are either not being accomplished in the current architecture or something that's not fully accomplished in the current architecture. So this is the traceability we're talking about. Decision on an element, how it traces to the functions that we need to have in our architecture so that we can begin addressing those big objectives that we want to go accomplish. So for habitat, this is something we have to have in place on the surface if we want to be able to begin living outside of our lander, spending more time on the surface, and eventually branching out and going farther away from that landing location. And so you can read some of the detail here on that initial surface habitat, but this is also helping us look forward to Mars because we envision having something similar at Mars in the future. So we're looking at that extensibility, not only to expanding on the moon, but what we can do as we look forward to Mars. Another new element we decided in the last ADD is Lunar Surface Cargo Lander. Again, the functions are listed down there on the lower left. These are things that we need to do. We are going to need to bring more to the surface than we can carry necessarily in the landers that we have, especially if we want to spend more time and continue to increase our capability on the surface. So we need to have some kind of capability as we move into foundational exploration and sustained lunar evolution of just getting more stuff to the surface. That stuff is then the logistics that we need to have, our crew members need to access so that they can support the activities that they have underway. Once again, extensible to looking forward to thinking about how we explore Mars. Another thing we added in the last round was we call our technology gaps. This is something that is a response to community requests, especially in industry and our international partners. Where should we focus our energy? There's a lot of things that we could do that we think would be really useful in your architecture. So as we think through that, what we've tried to do is publish a list of where the gaps are. What are we not addressing as we look at that set of functions and use cases? And what can we look to partners to potentially provide? So we're showing you what decisions we're making on what our next steps are, and then we're talking about what are the key things we don't have in there. Where do we need help? What technology might be useful to us? This list is prioritized. Here you can see kind of basically our top priority bucket: lunar dust tolerant systems and dust mitigation in general, systems to survive and operate through extended periods of lunar shadow, high bandwidth, high reliability, surface-to-surface communications, Mars transportation propulsion, and extreme environment avionics. So I know Joe this morning talked a little bit about the long poles from studies in the past. I mean, you kind of see these things popping up here, right? And the ones that we don't have decisions on, we're identifying as things that we do, in fact, need to work with partners on to help move us forward. So now I'm going to just kind of go through where we are on Mars. We've got lots and lots of studies on Mars over the last several decades. And again, you know, Joe brought up the long pole study from, you know, well, I guess it was 10 years ago. So, you know, there are many, many studies, and each one of them was done in its own kind of environment and you know, had certain constraints that were placed upon the personnel who worked on those studies. And we're trying to get into a position now where we really start making decisions on how to move forward. And so one of the things I'll talk about is what that decision process looks like. And I also want to talk about where we are in that decision process. Because one thing that I have, and many of you in this audience have heard me say this at other talks in the last few months, but there's often a sense that we've decided more than we have. And so we really want to be clear. This is why we're putting the documentation out about where we are in these decision processes. So I'll talk about that in a moment here. This is our list of priority Mars architecture decisions. Now, there are many decisions that need to be made about how we go to Mars, how we explore Mars, how we return from Mars. As one of my colleagues that many of you know, Michelle Rucker, who recently retired from NASA, she used to say, you know, what color the handrail is on the lander on Mars, it's a decision we will have to make. But it's really not one of the first ones, right? It's not a lot of other things that are dependent on what that decision outcome is. So what that team did, our Mars architecture team, did a great job putting together a model to identify the key decisions and then look at the dependencies of those decisions on other decisions. And in that way, we're able to highlight and prioritize those key high priority decisions that need to be made so we can focus our limited energy on those at the beginning. because they'll have the biggest ripples on the other decisions. They may eliminate some potential decisions that need to be made and focus our energy downstream in other decisions. So again, that process is laid out in our ADD, and you can see those decisions here. We have a different kind of colors on them here. I'll talk about a few of them. The first set that came out, number of crew to Mars vicinity, initial human Mars segment, target state, initial human Mars segment cadence, number of crew to Mars surface, Mars science priorities, Mars surface power generation technology, and Mars loss of crew risk posture was the first set that we came up with. So that's everything on the left of that dashed line, if you can make that out in the slide. That was the first set we put out. We added 5 more to that in this most recent release of the ADD, but it doesn't mean we're necessarily actively working them all. We want to make sure that as we communicate with the community, being transparent about this, you know which ones we anticipate focusing on. We have made one decision of this set that's in our documentation, and I'll talk about that in a moment. So I just want to make that point super clear. Only one of these have we made a decision on and documented. It was listed this morning in the conversation that Joe had with multiple of the panel members brought it up. And so I'll talk about that here in a moment. That decision is related to the surface power technology decision. So we had to make a decision on that because many other decisions we need to make would be related to how much power is available on the surface. So the team did a tremendous study, and I'll kind of zip through a few of the slides that they have generated. But right to the point, NASA selected nuclear fission power as the best choice for surface power on Mars. And so it's been identified as a long pole. Sorry, I keep pointing at Joe because he brought it up this morning, but it was identified, and I think Tim was talking about it this morning in a little more detail. But once we know what the amount of power we anticipate having and how we're going about providing the power, we can look at the other decisions that are dependent upon that. Now, the team went through a whole range of options to look at, both nuclear and non-nuclear options. They fairly quickly ruled out a number of the non-nuclear options. And you can see some of the rationale here. I won't necessarily read through all of it, but scalability, how much mass you have to get up to the amount of power that you're desiring. And really quickly, the team was able to get down to basically a nuclear technology, fission, surface power, and then a non-nuclear technology, photovoltaic array with energy storage. So we kind of ruled out a number of those options, and then we went into a more focused study on that. Again, conversations you've already had this morning pointing this out, the weather, the environment on Mars can generate situations, especially when dust is lofted into the atmosphere, where solar power starts to have trouble generating the amount of power that we anticipate needing for the breadth of systems we would anticipate having. So once you study that and get into that, we can't have that, right? We've got to be able to have that power in place. And so you can see some of the parts of this study here, the robustness to the solar flux and to the dust storms that are related to those is really what started pushing down on the desire to go with the solar energy. It also has some to do with some of the scaling and the amount of mass that you need. And that really led us towards that decision. Here you can just see some of the comparisons between that. None of it's perfect, right? None of these are the perfect one. But by going through the trades and assessing and comparing and being transparent about it, publishing all of this research to make sure that it's out there for the community to look at, again, we came to the decision that nuclear power was really the way to go for this. Again, QR codes all throughout my slide deck, so you can go find exactly what we're talking about. We want to make sure that this conversation is available to all of you. This is my last slide. I just want to come back to it again one last time. I showed you the details a little bit there. I just want to say it one last time. We've made one decision. It is the power system at the surface of Mars. Okay? The rest of it is in work. We're working on it. We have the workshops with the community. We're trying to be present at as many of these types of meetings as we can be to hear from you. If you go to the webpage for the architecture concept review as a whole, you can submit feedback. We've encouraged the community, if you don't come to the workshops that we host each year, they're usually in the beginning of the year, to look at the webpage. You can also submit feedback there. I hope those of you who have been doing that have noticed that we read that. We listen to the feedback that we get. We really are listening to it. That's why we are making such an effort to connect with you all. So that's the status that we have right now. Getting ready to fly to our friends, our crew members around the moon early next year, and then on to landing on the surface of the moon in the South Polar region, all while we're looking at the architectural decisions we need to expand capability at the moon in preparation for making the trek to Mars, and what do we need to be successful with astronauts at Mars. So with that, I will take questions. I think I have a few minutes left.
Hi, great talk. Quick question about oxygen generation on Mars. I've read about MOXIE. Are there any alternatives to MOXIE that NASA is looking for, like solutions from academia or like industry?
Yeah, so there are certainly resources at Mars that are potentially to be used by us. For the early, and when I say early, it might mean just the first Mars mission with crew. That is not one of our top priority decisions, but it could evolve into something that we look at. So again, if you look at the documentation on the gaps, resource generation is something that we're interested in understanding, but we really need to understand the balance between the value of just taking the resources with us versus what it will actually take to generate it. That's something to think about for both the moon and Mars. So it's a great question. Certainly folks are thinking about it, but it's not one of the top high priority decisions to set us up for that first crewed mission to Mars.
Hi, Sam Ahmed from Agence France Presse. I know you haven't made this decision, but I'm going to ask anyway. Could you give an approximate sort of ballpark or range for the risk posture, or what it might be comparable to in terms of crew loss and that sort of thing? Thank you.
Yeah, you did already answer the question for yourself. We don't have that decided yet. We're actively working on that right now. I don't want to hazard a speculation on it because it's an active study. The message we do want you to understand is that we're working it, that we do consider that a high priority decision that needs to be made. But that's where we are with that right now.
Hello, Chris Temby with the Agnostic Life Finding Association. Again, probably something that is still active study, but is there any consideration as to the actual launch vehicle that'll be used to send crew to Mars? And if it ends up being Starship, which seems likely if, given the executive intentions, I guess, to sort of phase out SLS, does that require that there's going to be large-scale ISRU on the surface of Mars prior to human arrival? Thank you.
Yeah, these are all great questions. I'm really good at giving unsatisfying answers, but I can't really speculate on that right now. Mars transportation we recognize as a gap. You saw on our big gap list. We have to think all that through, and there are going to be dependencies on several of those decisions. But I can't really speculate on that full trade space right now to give you an answer to narrow that down.
Thanks.
Hello. I came in a little late, so I just wanted to see if there was something said about, I guess, as a part of that architecture, the transfer point, such as the assist Lunar or even assist Mars, as far as just what that is going to look like, or whether or not that was a part of the presentation, because that is a key part of it.
Yeah, I agree with you that will be a key part of it. It is not something I talked about in the slide deck. Okay. We don't have that as one of our top set of 7 decisions we're making right now, but it is something we have to think through, and I think it goes to the prior question. There are a lot of questions about what that whole process of departing the Earth system, transitioning from Earth to Mars is going to look like. But same unsatisfying answer right now. I don't have an answer for you. Right. We've made one decision, and it's about surface power. We're working on the other ones right now.
Copy that.
All right. Art Harmon, SaveManSpace.com. What is being done or planned for determining long duration exposure to low gravity, like more rodent studies, things like that. In other words, can a human, will somebody need centrifuges to survive a long duration? Will people born on another world ever be able to come to Earth?
Yeah, great questions. And I know I've seen Eric already talking about that today, and yeah, those are certainly things that we need to think through. Our human research program is thinking through a lot of those questions, what the big risks are for astronauts to go to Mars and to come back. There's a lot of research underway. We're collecting as much as we can from ISS. But as has been pointed out, that trip to Mars is going to be a long one. We haven't sent human beings into space for that long a period of time. And this, my very first slide about why Moon and then Mars, is how do we learn and provide some of that data that many of folks in that community are asking for. We have to find those mechanisms to do that, or it affects our risk posture. So again, these are places where these interdependencies between the questions we're trying to work on right now exist, and we're conscious of them. They're all great questions, and I don't have the answers for you at the moment, but we are thinking through how to collect the data to help us start answering those questions.
Hello, Jan Špaček from Agnostic Life Finding Association. My question is related to planetary protection. For example, for sample return, there were procedures to prevent backward planetary protection risks related to that. Now, with humans going to Mars, obviously, according to COSPAR, there is no way to prevent contamination both ways. So is there a chance that NASA will just give up on planetary protection, or is it like we will send the humans only after we establish if biosphere exists on Mars or not? Thank you.
Yeah, these are good questions. And once again, none of that has been decided. One of the top key decisions we're looking at is what science do we want to achieve when we go to Mars? So some big impacts on the question you just asked are things like, are we bringing samples back? Are we bringing samples back that include water or ice or things that could potentially involve life? The forward part, I agree with you 100%. We're going to have to think through, but I think we have to think through it in totality, not just pieces of that question, because it really does depend on what the mission is going to look like at the beginning. So again, this is why we set up this sequence of questions, because we want to answer those first before we get too far in. But I don't think we're going to just abandon it. This is a conversation that we need to have as we move forward.
Just a little bit further. I feel there's a big disconnect between planetary sciences and human exploration. And I think a lot of these missions have very big overlap and would benefit from closer collaboration. So if you can, from top, communicate more between the departments, that would be great.
Yes, very fair point. And the one point I will make real quick, Chris, and then I'll get out of your way, is you're exactly right. And when we say the science we want to go achieve, that does not mean only the planetary geology science. That is the full breadth of science, which includes some of the questions that were already asked. What do we need to learn about how humans respond to that environment as well? So yes, we agree with you, and we're looking at that integrated solution. Thanks.
Thank you very much. Thank you, Jake. And before our next session, we're going to show a video from our old friend, Congressman George Whitesides, who many of us have known for over 20 years, and as you know, just recently was elected and confirmed as United States Congressman. So first, let's show the video from George. And I think Robert Zubran will particularly like this video also.
Hey everybody, Congressman George Whitesides here, representing California's 27th District, Vice-Ranking Member on the Science, Space, and Technology Committee. I just wanted to send a big greeting to all of you. So many friends in the audience. Sorry I can't be there, but I am with you in spirit. As many of you know, I got my start in the space advocacy community by going to the 1998 Mars Society Convention, the founding convention of the Mars Society. Got to know all the folks back there and remain an advocate for an ambitious future in space. I am looking forward to working with all of you as we try to fight off the terrible cuts that are being proposed to NASA's budget and to other science agencies. I remain hopeful that if we can get past these challenging next few years and next few budgets, the future remains bright. We can do incredible things on Mars, and the technologies, the vehicles, the industry, the people, the science that we have now assembled put us within reach of going to Mars for sure in the next generation. But it's not going to happen automatically. It's going to take the work of all of us to set up things in the right way. And you know you'll have a strong partner in myself on the science committee. So please stay in touch. Let me know how I can help. Give me good intelligence so you can point me in the right direction. And let's make sure we have a great future in space. Thanks, everybody.
All right, now we have a little schedule change. The lightning talk that was supposed to be this morning is actually now moving to right now. And actually, as it says on the agenda that Hoppy Price is giving this, he's not. Joe Cassidy from Aerojet Rocketdyne and Explore Mars board member, will be giving the lightning talk, Short Duration Crewed Mars Mission Opportunities. Joe?
Thank you, Chris. Hello again. So yes, a few changes. And this is, just a really quick overview of something that we looked at, again, a few years ago in one of our workshops. And I guess I have the clicker, so here it is. And here's, again, the picture. And you can see, in this case, a lot of the same characters. In fact, I noted that two of the folks who like to get in the back row and stand on things so that their heads are apparent above everyone else seem to be doing that in this picture again. But this is just another example of how over the years the Explore Mars, Achieving Mars workshops have really done some really good work. And again, I'd reference, for anyone who's interested, go on the website and you can find all of these reports. This particular one came out of an architecture-focused workshop that we were doing. And we ask ourselves the question, what is achievable if we really wanted to do something in the 2033 very favorable opportunity that we have between Earth and Mars? And so we looked at that, and this is the result of that. And then a subsequent paper that Hoppy and some of his colleagues did that I'll reference. So here we go. So what we took out of AM5 was this configuration that you can see here on the screen. We assumed a lot of things were available, including Orion. You remember this morning in our panel discussion, we talked a lot about that transit hab, and that was what Hoppy described to you this morning. A little bit of malice aforethought there on my part, because that was something I knew we were going to want to have in this case. So that's the real key thing that we really ought to be doing if we wanted to do something and take advantage of this 2033 favorable opportunity. If we had a transhab, and you can see it there, each of these elements on the screen, you'll note down below there, we've put a reference, and I noticed it got a little messed up when I went to the PDF, I think. But you can see the metric tonnage of each piece, and I'll show you the launch strategy in a moment here too. But the transhab is about 45 metric tons, and it's similar to what Hoppy described this morning in terms of keeping a crew of 4 comfortable and happy and healthy on their way out to Mars. Now, a key thing that Eric mentioned this morning was that human health is dramatically affected by the total time and the duration, because obviously you're exposed to the radiation, the microgravity, you can get a toothache. All those things can go wrong the longer you're out there. So what we were taking, trying to take advantage of this very favorable opportunity in order to bring that into a time frame that we were comfortable with. And that's about, roughly a year and a half, because we've had people on the space station for, year-long missions and things like that. So I put this together. This is an update that, as I say, Hoppy and some of his colleagues did, and actually got written up in the Journal of Spacecraft and Rockets. I put the reference down there at the bottom of this chart. And again, this basically took our concept that we came out of AM5 with, added a few things to it, but the key points really are that we had all near-term technology, no new technology developments required, some assembly in orbit, but no propellant transfer, and a bonus, we get a twofer, because on the way home, we actually have to fly inside the orbit of Earth, so we can not only send a crew doing a flyby of Mars, but also of Venus. So you talk about an inspirational mission that could happen in the 2030, early 2030s to mid 2030s, and again, only using technologies that are fully developed and elements that would, the Transhab being the main one, that would have to be kind of accelerated a little bit and brought into the flow. It would be launched in segments by SLS and different commercial rockets. It could be assembled in either high Earth orbit or at the gateway. And the crew then could come home to Earth once the mission was over, directly in the Orion capsule. And as I said before, it's a very unique short-stay orbital mission of about 1.6 years total duration. It also gives us a pathfinder for a lot of those systems, so it's not really just a stunt or a one-off. Here's the kind of bat chart that just shows the overall mission and how we would do it. So again, it's a mix of commercial and SLS launches. You can see the 4 SLS launches there shown across the bottom. We launch the bipropellant stages up on commercial launch vehicles, and those are assembled there in the low Earth orbit, used to boost to trans-Mars injection, and then used out at Mars for Mars orbit insertion. And then the Transhab itself and some of the other major large pieces are launched in addition with the crew there on the 4th SLS launch. And then you can see the transit times shown there. You spend about 30 days, then after MOI, 30 days in the vicinity of Mars, you come back as you fly by. You've got a total round trip time of about 570 days. And as I said before, you actually get to have a flyby of Venus as well. And then come home in Orion for direct entry to Earth. So overall, 15 low-cost conventional hypergolic propulsion stages could be designed to be mass-produced with just simply kind of varying tank sizes, and no in-space cryo, no propellant transfer, using Orion, using SLS already, and potentially using Gateway as an assembly point. So again, what do we need? We need that Transhab to make this a reality. And there it is on my first bullet of my last chart. Main need we need is the transit habitat. All this storable stage design is very similar to upper stages that we've already built for other rockets. We'd need to build a few of them. That's actually probably a good thing because that's a cost savings. We've got the engines. We ourselves have them, and so do other people. But they're very high TRL engines. And you can launch on existing launch vehicles, and you can certainly take advantage of Orion as well for the crew. So no technological breakthroughs required, provides us with a pathfinder, an inspirational mission, takes advantage of the unique 2033 opportunity. And it turns out it also would work in 2035. In fact, just hallway discussion with Hoppy this morning, he was telling me that actually 2035 is a little bit more delta V on the way out, but actually I think gives you some benefits in terms of the overall trip time, and you don't necessarily need the Venus flyby, I think, Hoppy, is what you told me. That's right. No, that's what I was. Yeah, it eliminates the need for some of the deep space maneuvers. So we could probably save some delta V out in the latter part of the mission. So that's what I had for you in the lightning talk. And if anybody has a question, I guess we have 1:30 left. So feel free to come on up. All right, great. Well, we don't have any questions, then I'm going to go ahead and get us a little bit more back on schedule. So it's my great pleasure to introduce our next panel, or the moderator for our next panel, is Dr. Hakeem Olushedi, and he will come out and introduce his panel.
All right, thank you very much. Hello, everyone. Yeah, it's good to see such a great turnout. You know, last week I held a summit called Humans to the Sun and Venus. No one showed up. Thank you, whoever laughed first. I appreciate that. All right, so I'm going to introduce our wonderful panelists here. When I was asked by JR to lead this panel, I thought this is amazing because you don't hear about this particular topic very often when you hear about humans going to having a permanent presence on the moon or Mars. So sitting beside me is Ernest Sanchez, who manages the cargo mission contract at Leidos. Did I pronounce that correctly?
Leidos.
Leidos. Yes, which supports both the International Space Station and Artemis logistics operations with over 25 years of end-to-end space logistics experience, starting when he was 3 years old. His team, y'all didn't catch that joke? He looks like he's younger than 30. His teams have overseen more than 15,000 shipments and delivered over 380,000 pounds of cargo to orbit, from Earth to orbit, cargo to orbit, from Earth to orbit to the moon. Ernest handles the unglamorous but essential challenge, getting the right stuff to the right place every time.
Unglamorous. Oh, man.
Hey, you got to make it. You got to get there. Seamus Tui, who has a last name that is very similar to mine. Does not sound how it looks. Seamus oversees robotic and operational systems for space missions at MDA, the Canadian company known for building the robotic arms aboard the Space Shuttle and International Space Station. A specialist in robotic autonomy and systems integration, Seamus is helping engineer the backbone of surface logistics and infrastructure for the moon and Mars. If it moves cargo in space and isn't human, he probably helped design it. Wow. All right, and next we have Jackie Cortez, the Senior Director of Civil Space at Blue Origin, where she helps shape the next generation of human and robotic space transportation. With a background spanning aerospace engineering, government affairs, and program development, she bridges public and private sectors to support NASA's lunar ambitions and beyond. Her work supports Blue Origin's visions of millions of people living and working in space. I would argue that we are already living and working in space.
Not millions.
All 8 billion, how many are we? 8 billion of us.
Oh, that's a really good point.
Yeah.
We're all on Spaceship Earth right now.
That's right. And you know what's crazy? Spaceship Earth is weightless, even though we have weight as we stand on it.
What a deep realization.
Right? Yeah. Yeah.
We
What
need to
did you
change
get
the
in his
whole
box water?
tagline. We got to change everything about Blue Origin now.
There you
the
go.
vision has changed.
My consulting fee is not as high as you would imagine. All right. And finally, Tim Bulk. And so those of you who are into cosmology, in the green room, I just introduced him to the bulk and brain model in cosmology. Look it up. But anyway, he's the Chief Technical Officer for Special Aerospace Services. He's the co-founder and the Chief Technical Officer, a leader in systems engineering, manufacturing, and mission-critical aerospace solutions. Formerly with NASA, Tim helped shape the Commercial Crew and Cargo program and worked on missions to the Moon, Mars, and Pluto, a minor planet. Today, he's also president of SAS International and the visionary behind Who Dreams Wins, a foundation using aerospace to drive global STEM education. So what's going to happen is each of our panelists will have a brief presentation, and then we will go into a discussion about logistics of humans in going to the moon and Mars. So let us begin, sir. We start with you.
Okay. I wanted to start off by saying, I just want to give a high-level overview of what Leidos is and how we support logistics today on the ISS side as well as the Artemis side. And just to make a minor correction here, you know, I'm 33 years in the space business for logistics, but 25 years if I look at the next page here, so there's 25 years of Indian logistics experience within the Leidos company. You know, as Hakeem said, we're currently the prime logistics contract for the ISIS program. What that means is we are responsible for all the receiving, integration, packing, planning, and shipment of all the cargo to all the launch vehicles throughout the year. We're supporting probably around 14 to 15 flights a year, as well as the return aspect of it. So literally, you know, 40,000 pounds of cargo that our team is touching and shipping to the launch sites. We're probably integrating probably 98% of the pressurized cargo that goes on the vehicles itself. We have, like was mentioned, we supported over 175 missions to the ISS, well over 100 return missions as well, and almost 400,000 pounds of cargo, and that corresponds to about 15,000 shipments. And so one other thing I wanted to mention also is the Antarctic support contract is also managed by Leidos, and that is another big logistics contract where you're supporting you know, in a very harsh environment, logistics, maintenance, operations, science, studies, and those things. So that is another great relevance there to Moon to Mars. We're also supporting the Lunar Outpost team and their LTV vision, and that is just a fantastic operations there. Our team under the cargo mission contract also is very involved with hardware certification efforts, you know, from complex items like potable water dispensers to food warmers to crew quarters. Our Dynetics team supports docking systems, air constituent monitors. So we do a lot of hardware development and design for all vehicles, all environments today. So that is very, very relevant to what we're doing. And then the other thing I wanted to just mention is, as part of our Leidos, you know, we're almost 50,000 employees, and we're supporting DOE and DOD in hazardous waste remediation and recycling. And so those are other areas. So these areas I have on this chart here are areas that we're going to leverage to put together, you know, packages. We were recently awarded some BAA Moon to Mars white papers that we're being putting together. So we've got some very talented people that are all putting together solutions and ideas for the program. So all that put together, we kind of bucketed our services into four main categories: our logistics, where we're doing all of our cargo services; our engineering, where we're doing all the design and development of various harbor products. One thing I didn't mention, but we also today are outfitting the crew for all their clothing, consumables, and so a lot of the usage rates are absolutely applicable to Lunar and Mars habitation. All the operations and mission operational support that we give as well as part of that. One thing I wanted to mention is some challenges and lessons learned. So there's many challenges in logistics, but some of the ones that we're really focused on is having an integrated logistics system to support all the tracking of all the property and all the consumables that are needed to be tracked for lunar and moon operations. Life cycle planning, interoperability is very critical. Obviously, you know, common components, common sparing, common standards help create efficiencies. Even our cargo bags today, they're very standard sizes and shapes. And so as we move into the future, you're going to have different size vehicles, different interfaces. And so it's important that we communicate often on interfaces to try to maximize interoperability and interchangeability, those kind of things. As far as learning lessons learned, you know, you saw Vanessa was up here and she talked about you know, leveraging the space station, all the lessons learned there that were accomplished over the years. And we are on the Leidos side are trying to harness that and in our area of expertise with the cargo logistics and packing integration, we've been very innovative with our tools. You know, one of the challenges we've seen on the ISS side is, you know, vehicle cadence. You know, things don't always go as planned. The flights have issues. There's weather delays, and so you're having to move cargo from bag to bag. Things happen on orbit where you have failures that you have to address. So one of the things that we've really shaped over the years is just creating very agile tools to enable us to rapidly move cargo and manifest from bag to bag or vehicle to vehicle to make it very cost effective. The other thing that's very important, I think, is automation of our consumable tracking. Today it's very manual, labor intensive on tracking consumables, even hardware for that perspective. And so right now we're engaging different technologies to try to make that more efficient going forward, more automated, to take crew time and ground time out of the equation. And that is all I had.
What did you say, go next?
Wonderful. And next we have, I guess until I announce you, Seamus Toy.
And like magic, it pops up. So let's see. So I'm with MDA Space, is the largest Canadian space prime, and very large company. We also have offices in the U.S. and the United Kingdom. And we've done a lot of work in space over our history through various different acquisitions and names, but we're back to being MDA Space. That we have over 450 space missions that run the gamut from, we develop constellations for broadband and direct-to-device systems. We develop geointelligence product based on our own Earth observation satellites that we built for the Canadian government. And where I am is in the robotics space operations, probably most famous for, we did the arms for shuttle, we did the arm, the Canada arm for station, and we're currently under contract to build the Canadarm3 for Gateway. So when we talk about logistics, it's something that is going to start small, obviously, but then grow. But the key here is trying to design it in at the beginning. Try not to backfit it later on, because what you'll find are things don't work together, or you have to go replace things early on. So for the Moon and Mars, we think there's an opportunity here to actually start fresh and to show how the current systems that are in development can be carried forward with new systems that integrated into an end-to-end supply chain. The big challenge is to evolve from having a bunch of tools that people talk about having, we're MDA Space, so it's robotic arms for us and surface mobility, but landers and cargo pallets and packages, and how all those fit together, go from having these individual items to having an integrated flow of how something goes, from an Earth production facility to a loading dock to a launch vehicle to the surface of the Moon to where it's supposed to be used, to a depot, and eventually be thrown away or reused in some manner. And when we move from, Earth operation, Earth orbit to Moon, that it costs us a little time there, communication lag, but then going to Mars is going to be ridiculous. And so going from, right now we have human in the loop systems. We have to start developing things which are human on the loop, and also fully autonomous systems that either have to have enough smarts to act on their own or enough smarts to act with a human, which is even a higher level of smarts, I think. The other thing we have to worry about is going from missions, individual missions, to doing sustainable presence. Having something which is always there and always available. Since I'm from MDA, I have to talk arms. So we're taking the C3, Canadarm3 arm that we're developing for the Canadian Space Agency on Gateway, and commercializing that to a brand of arms called Skymaker that can run the gamut from small to large, from things that lasted a lunar day to last years on the surface of the Moon in an orbit in space around the Moon. On the lower right, we're also on the Lunar Outpost team. That's why I clapped when you mentioned that, which we're very happy to be that. And so the Skymaker arm can go from in-space applications, Earth orbit to lunar orbit, down to the surface of the Moon. We also do surface mobility. It's not something we're as famous for. None of our rovers are on the Canadian $5 bill like the Canadarm is. But we've done a lot of it, but it's been component level, chassis, mobility systems, sensors, things like that. So what we're doing right now is looking at how to apply that experience we have in operating arms and developing robotic systems, and rover parts to actually looking at complete rover systems, but really thinking in the large about how they all fit together into a logistic system. We did a demonstration last December for the Canadian Space Agency and looking at autonomous roving, but also how systems actually get off a lander onto a rover, and then systems get delivered to, in this case, a pressurized HAB module, and looking at how this would be a shirt sleeve transfer of goods in a pressurized container. And when you start looking at that, we think of operations as being a dominant thing in your design, that a lot of people tend to want to fix operations after they build something. We tend to want to build operations into it. It really teaches you a lot about how you should design your systems. I'll hand over to Jack.
Thank you. And next we have Jackie Cortez.
Okay. Hi, everybody. Can you guys hear me okay? Okay, sweet. Thanks. Hi, I'm Jackie Cortez, Senior Director of Civil Space at Blue Origin. Thank you for having me. And I will say I'm embarrassed because I already now need to change my first chart, thanks to our dear moderator, for saying it's really millions of people living and working off Earth versus in space, where we're all millions of people living and working. But you know what? We won't go into the complexities of that right now. So the vision of Blue Origin, I think, is very clear, which is we want to get you all where you need to go. So once we're on, Mars, Moon, wherever we want to go, we want to help get you there. And so we're focused on developing the commercial transportation capabilities to get us all over the solar system. And a really cool thing I think maybe some people don't realize about Blue Origin is, specific to Moon and Mars, every single business unit, every single product that we're making at Blue Origin has applicability to supporting both increased activity in the Moon, Mars, lunar vicinity, and general deep space. And I'll just give you some quick examples. So our New Shepard suborbital vehicle, which is probably our most public, widely known vehicle, actually just recently conducted a lunar gravity simulation flight, completely full to the brim of payloads, where we spun the New Shepard capsule to simulate lunar gravity, and it was an amazing success. It was very cool. And so, you can do the same thing on New Shepard for Mars gravity, for example. So I think just that example in and of itself, a lot of the rest of what I'm going to talk about is a lot more obvious. But just the fact that a researcher can literally buy a payload, fly on New Shepard, and simulate 3 amazing minutes of lunar gravity for a fraction of the cost of actually going to the Moon means like we're in this amazing, brilliant commercial space revolution, and the US is undeniably the leader of that. So just wanted to start with that example because I think, like I said, the rest is a lot more direct to the Moon and Mars, but that's just an example that I'd like to highlight. So at Blue Origin, I think, a lot of our big vehicles that are really widely known are for the Moon. So I'm going to hit on those first, but there is major applicability of all of what we're doing at the Moon to Mars directly. Hopefully, first and foremost, I'll hit on, I hope everyone in January watched the successful first flight of New Glenn. New Glenn is our heavy lift rocket at Blue Origin. It really enables everything that you're going to see on the rest of the screens, but because you are all tuning in, I'm not going to spend time on it right now. I'm just going to assume that everyone saw that. So we're really excited to be flying again here soon with New Glenn. And I think one interesting thing about this chart that I want to highlight is a couple things. So our Blue Moon Mark 1 uncrewed lunar lander is a key part of our entire logistics architecture. It's a 3,000 kilogram class, single launch, no refueling lander, and it's flying to the Moon this year, 2025. So stay tuned for that. We're really excited about that. And that's a key part in our vision to sustainable lunar exploration and unlocking infrastructure class access to the lunar surface on a repeatable basis. So that's a big thing to look out for this year. I wanted to show you guys a real picture of the lander. Obviously, this is a render, but comms has some big stuff planned and they rejected me. So you're going to have to deal with this picture for now. So stay tuned for Mark 1. And I will say a cool thing about Mark 1 also is that, and I'll get into this more, we've set this all up from the beginning to be production class vehicles. So we don't intend to build just one of any of the things that I'm talking about. So again, Blue Moon Mark 1 headed to the moon this year, a fully Blue Origin funded demonstration of that capability. We're so excited. And the reason that we fully self-funded that demonstration was because we are a provider for NASA for the Human Landing System program. So the vehicle you see on the far side is our crewed lunar lander for Artemis. We're really excited. We're going to be flying that in an uncrewed demo and a crewed demo this decade. So that's obviously in that picture for people to step out access onto the lunar surface. But what's not pictured is also a cargo version of the exact same lander that can fly 20 to 30 metric tons. So again, when we're talking about setting up a long-term infrastructure on the lunar surface, on Mars, these capabilities are truly from the beginning designed to enable these big infrastructure class missions to occur. So like I mentioned, just to hit on it quickly again, sorry to render. You'll have to trust me. There's a lander, I promise you. So again, 3 metric tons flying this year. And I will say one thing that I'll hit on as well toward my infrastructure class production line point is our second Mark 1 is simultaneously in assembly. So as we all know, landing on the moon is a big challenge, especially with us having all hydrogen. So it will be the largest and first hydrogen lander if we're successful. We want to have another one ready to go so we can keep iterating in the event that we don't achieve all of our mission objectives. So that's another key part of what we're doing, is to be ready to go again, trying to be hardware rich as possible. So Mark 1 is a key enabler of our vision of logistics on the lunar surface and unlocking all these amazing things that all these gentlemen want to do. So that's key for us. Another key part of our architecture that is applicable to both the moon and Mars and is a little less known, so I'm trying to hit on some of those things, is our transporter vehicle, which essentially provides the cryo-cooled propellants from LEO to the lunar vicinity, but it doesn't have to stop there. So transporter is being developed for the Human Landing System program, but again, with our vision on production level vehicles, we plan to make a lot of transporters, and the beauty of a cryo-cooling, zero boil-off stage like this is it can do lots of things. It can deliver 100 metric tons to the cislunar vicinity. It can deliver 30 plus metric tons to Mars. It can do so much at NEOs. It's a very cool vehicle, and we're making huge progress on solving kind of one of the holy grails, which is that zero boil-off, sustained cooling and storage of hydrogen and oxygen, which is core to our vision at Blue Origin. So just hitting on transporter because a lot of people don't know about it. And then lastly, I did have to show you guys some hardware since I got rejected at the other turns. So just so you know, the heart of our entire lunar and Mars architecture that I've talked about in this presentation. So please tune in tomorrow because Dave, our CEO, is coming and he's going to share a lot more than I shared. Again, I'm being restricted, I'm being held back, but that's okay. Dave will share a lot more with you guys tomorrow. But the core of the architecture that I just discussed that Blue Origin is working on is the BE7 LOX hydrogen engine. Again, a core commitment at the company to hydrogen and mastering kind of that holy grail propellant mix for the future resource utilization. So here's just some great successes. We presently have BE7 hardware on 4 different test stands simultaneously. So again, really trying hardware-rich production class mindset so we can have, predictable, reliable, and affordable access to the moon, Mars, and the deep space exploration environment. So that's all I have. Thank you.
Thank you. Now to Tim Bulk.
All right. I'm still wrapping my brain around bulk membrane versus bulk modulus, which I used to get teased about in college. So,
totally different scale. Yeah.
Okay, so who is SAS? We are somewhat the stealth-like company that helps companies like Blue Origin and others like ULA in making their systems safer and more reliable. Just a quick story, when I left NASA in 2007, my third contract with the company was with a small company called Blue Origin, which was 45 people. And they wanted to understand how to put a propulsion test stand in the middle of Kent, Washington, in the downtown area. So just a little history on what sort of the things we started doing. Sure. So we are a new aerospace and defense technology company founded in 2007. Last April, we transitioned the company to majority ownership to Godspeed Capital. So I've sort of come full circle in the whole startup to transition phase. We are located in Boulder, Colorado, with a manufacturing facility in Arvada, Colorado, which is about 30,000 square feet, where we make hardware for companies like Blue Origin and ULA and others. Last year, Godspeed also acquired 3 other companies, Quintron, which makes secure communications, located in Santa Maria, California. Also, Willbrook Solutions and Concordia Technologies, which was heavily in the missile defense side of the business. So when the company was transitioned, we were about 155 people. Now we're about 300 people and growing with other acquisitions coming this year. So we are a trusted provider of high-value mission-critical solutions and hardware as well as services. We are not truly a CETA contractor to the government. The whole idea was to be small teams doing great deeds for the primes and the developers, because my background, I came from a hardware development background and from industry prior to going to NASA, and worked successfully on the Atlas III and Atlas V programs. Currently, the company has embraced a full life cycle model to help our clients, strategic services, program and mission planning, then engineering services, technology development, and specialty products. As we grow, we want to be making our own systems as well. From the strategic services side, helping companies win new space work throughout the 17 years. We've helped companies win over $10 billion of new space contracts. And so again, when we do that, hopefully we're providing engineering services to make them a safe system and a successful system. Growing, we serve the needs of NASA, the DoD, the intelligence community, missile defense, and as well as I mentioned, the civil space companies and other space customers. I'm not going to read all this of what we've done. I'll just highlight some of the stories. People, at least NASA and others in the industry, know us through spaceflight safety. That's a trademark process and system we apply to our clients. We've applied that over 7 years, helping Blue Origin with New Shepard. I briefed the founder prior to the first human flight on how his team did in qualifying the hardware. And of course, that flight was successful and a high point for SAS to make that happen. We were also involved, of course, with the Antares Cygnus program, delivering cargo to the ISS. That was part of the COTS program, and then the Cargo Resupply Services contract with NASA. Our breadth of technical capability now within the company spans from the logistics work all the way to mission planning, special operations, and of course, secure communications, hypersonics work, and briefly our international business work, where we help other companies allied to the U.S. wanting to start operations here in the U.S., selling either services or products within the U.S. We had a big win this year with our STEP-R Lunar Logistics BAA win from NASA. We were one of the few companies that won all 7 critical areas, or 7 critical CLINs for that BAA. We focused on a system of systems approach, which applying some software AI tool sets that we took from aviation and special operations and applied it to NASA requirements, and really applied a system engineering solution as well as the tool set, and then some innovations with robotic carriers and humanoid robotics as part of the study. So that just kicked off 2 weeks ago, and it's going to be a very fascinating BAA and study. Our team included SpaceWorks, of course, being in Colorado, we had to leverage Colorado School of Mines, Astrobotic for cargo carriers and how they're going to apply their next generation systems. Of course, we're also open to working with others such as Blue Origin and the suite of other companies that are going to be providing cargo directly to the lunar surface. And then uniquely, we pulled in a commercial company called Agility Robotics with their Digit humanoid robot. If you haven't seen the videos of what that humanoid robot is doing in warehouses, we're going to be working with them on how that can be applied to the lunar surface. And it just goes to the point that Vanessa talked about how astronauts and robots are going to be working hand in hand in the future. So that's all I have.
Excellent.
Open for questions.
Excellent. You know, Tim, you put Santa Maria up there, man, and triggered me. Last August, I went and took 30 cycles on the zero gravity plane. I made it through the first 10 and discovered why it's called the vomit comet. Don't mention that again. All right. So what we're talking about here, establishing this infrastructure and supporting it, is going to be easily one of the most complex endeavors in human history, right? And you know, I think we really take this a little too casually anyway, because I still think of the fact that we have evolved from Homo habilis, to whom breaking a rock and creating a sharp edge was an innovation, and now we're, you know, dominating space. So I have questions for you all in various topics. So let's talk about end-to-end logistics complexity. So, Ernest, to you first, sir. What logistical challenges from low Earth orbit do not scale well to the moon and Mars?
Well, I think I touched on it. Can you hear me? I think I touched on it a little bit earlier. I think one of the big challenges for the ISS program today is just not really challenges, but we have the luxury of working, you know, several flights in parallel, and just being able to make changes rapidly and just be able to you know, to change cargo, to change vehicles, and I think you know, we're packing or changing manifest up to, you know, right at launch, you know, at launch minus 24 hours in some cases, so very late in the flow. And I think I think there's going to be less flight cadence, you know, going forward for Moon and Mars missions, at least getting started. I think so that's going to be a little bit more of a challenge. So I think the manifest of the cargo and consumables and making sure you have the right sparing identified and interoperability, I think all those are going to become even more and more critical going forward. So I think that's something that we really got to focus on.
Yeah, do you anticipate that the mass will be massively increased per mission?
My understanding is very mass constrained, and so that's another area where we have to you know, just come up with innovative ideas and solutions to reduce in mass, maybe having repurposing items, having different purposes for stowage materials, just get innovative with the way we pack. Today we've done a really good job with our stowage and packing solutions and coming up with innovative ideas, but there's always something else we can learn. You know, things that also with regards to consumables, you know, ISS has done a really good job of leveraging like pantry style functionality, and so I think we can leverage that a lot more and more like ground laboratories and do more of that to kind of save on mass. So, but mass is absolutely critical. Anything that we build or design is always very mass limited, mass constrained down to the ounce. So we're got that in.
Wow. Yeah. All right, let's turn to Seamus. Interoperability and transferability. So what does interoperability mean when you're dealing with multinational payloads, carriers, and habitats on another world?
So I think when people imagine interoperability, they try to concentrate on the physical connections. You know, does docking mechanisms work? You know, the plug, same volts DC, stuff like that. That's not the way we think. We think of the operability part, is how it fits together operationally. Because that's the thing that it really takes a lot of the time and cost. If you don't figure out how things can operate together, you know, when's the handoff? Who's in control? Who's responsible for things? You know, and as you design these logistics systems, you're trying to design them end to end to be optimal. But what that also means is that different elements may be suboptimal. You know, if you look at like the shipping industry on Earth, you know, the container size, you know, was not driven because it was the optimal container size. It was driven because the width and the height were limited by the U.S. interstate system. You know, so that was a constraint that was put on. And when people thought about how to put goods rapidly through a system, it turned out that was the easiest thing to do, you know, to make it so it moved quickly through intermodal changes, it moved quickly through the interstate system. And I think the same thing for the Earth going to Moon and going to Mars is how can things go easily through the system? You know, how can we create standards? How can we utilize things and operate together? Not so much that each element is optimized, but the whole total end-to-end system is optimized. And also it means making decisions about existing systems that you just have to live with, and not having to go back and change something that was designed 20 years ago, but how to utilize that in a efficient end-to-end system.
Wonderful. Thank you so much. Turning to Jackie. So, Blue Origin aims to be a transport backbone. Can you explain that to us generically?
Yeah, sure. I think definitely to kind of tie together everything I was mentioning earlier, we want to be a foundational go-to provider of flights for people, right? We fly people all the time on New Shepard. We're going to fly people on our Mark II crewed lunar lander, and infrastructure class cargo to pretty much anywhere in the solar system. That's the objective. And so there are some things that you see woven through, like I said, a lot of what we're doing. You see, a long-term commitment to, like I said, the LOX hydrogen vision. And that's a key part of it. We've been working on it, like Tim said, since the very beginning, in perfecting it and really trying to master it. So that's one, kind of core tenet of what we're doing. It's a core belief system of the company because, again, at the end of the day, we think a key driver of why you explore space at all is in situ resource utilization, is, finding things there, is sending 1 million of your rovers around to, to dig it up and make it happen. So to do that, you want to take hydrogen from the beginning so you can explore through cryo cooling and other key things. You want to be able to say, okay, if there's water on the ice, which, water ice on the moon, which we now know there to be, we want to use that for propellant so we don't have to take so much from Earth. So some of those core tenets, again, the second big one is that producibility. We really want to set up from a production mindset from the beginning. So that's something that we spent a lot of the last couple years focusing on. We have some beautiful buildings in Florida and Huntsville, but the lovely thing about those beautiful buildings now is they're not just beautiful on the outside, they're full to the brim of hardware, and that's where we want to be. So that's another key part of us trying to have this objective of being the transportation backbone. And the third thing I would quickly say is we did start a nonprofit called Club for the Future. And a big reason for that is it's really awesome for all of us to build all these transportation systems. But if no one's going to use them into the future to do this glorious, sustainable, long-term exploration, then it was probably not really for anything. So we need, our partners, our colleagues, but also the next generation to be thinking, how am I going to leverage these capabilities that exist into some amazing business idea or some, inspirational journey, and what are we going to do? Because if we don't have that, then again, all of this was, not sustainable actually. So those are kind of the way that we are trying to frame ourselves to be this, go-to transportation backbone in various ways. So.
Wonderful. Thank you. And Tim, sir, your team just won NASA's STEP-R Lunar Logistics BAA. What does that win say about how NASA's thinking has shifted around logistics priorities?
Well, I think now it's starting as the previous presentation stated, is that now it's real engineering behind how are we going to really do this. And it's not just studying the problem, but really applying good system engineering practices and engineering to say, okay, how are we going to limit the astronauts' time on not doing maintenance and servicing of the hardware, but actually doing science? And so balancing that whole aspect of lessons learned we've learned on ISS to now working with a robotic, humanoid robot possibly, or other type systems that allow the astronauts to really do science and do experiments versus continuous maintenance on the systems and survival.
When you talk about this doing science, it reminds me of a lot of our sci-fi movies where they typically have this science mission, but the corporation has inserted their guy who's really there to get those valuable metals that Jim told us are sprinkled all over the moon, right? So just watch out for that. All right. So to the panel, if you could design one piece of infrastructure that doesn't yet exist, and I know it's not a space elevator, but would radically simplify Moon Mars logistics, what would it be? Anybody, but all of you have an opportunity to answer. That does not yet exist. One piece of infrastructure.
So when you think about logistics, the transit part, once it's on a platform going from point A to point B, is very complex and very hard, but it's engineering you can figure out. The fun part really comes in on the intermodal parts, how it goes from one platform to another. And so if you ask me about the infrastructure elements that I would love to see exist that don't quite exist right now is how do things actually go from your lander onto a rover? How do things actually go from a rover into a pressurized hab or into a depot? And so you're talking about robotic systems, cranes, things like that. I mean, I don't think to your point, I don't think we want astronauts lugging around suitcases. They have more valuable things to do.
But they're weightless.
Well, not weightless. They're
less weighty.
Yes, less weighty. But it's that intermodal part. So it's those systems, those whether it's robotic systems or human-operated systems that cause you to be able to transition payloads from one platform to another. That's what I'd like to see. That to me is where the interesting thing is.
Interesting. Any other inputs?
Well, in my experience, everyone thinks that the rocket is always the hardest part, and it's really not. It's the concrete and steel that ends up usually holding up a launch or the overall program. And I think on the moon, how are we actually going to build things? And how are we going to do the simple things that we take for granted that, someone else is going to have that inflatable habitat module? But there's more to it than that. So I think that's, maybe that's another company that I'm thinking about is, come up with someone that you can create concrete on the moon, for example.
Wow.
Something like that.
Particularly
with the regulator.
If you go to a building site, on Earth, you look at all the specialized equipment.
Right.
They have things. They have like a specialized system that just loads sheetrock.
Right.
And is that a vision for the moon where in order to build a structure on the moon, you have to have 20 different machines? And so the idea of like how do you design things so that one machine can do what 20 do on Earth? It's how you actually construct things will be a good trick. Yeah, I like that idea. Yeah.
Well, one innovation we have here on Earth that I've seen at a lot of construction sites that could be very useful on the moon but wouldn't work is the fact that, in certain dry, dusty places, they're constantly spraying it down with water, right, to keep the dust down. And I don't know how you could deal with that problem on the moon, given its issues. So let's play a little lightning round here. You ready?
Okay, I'm ready.
All right. Finish this sentence. The single biggest risk to successful Moon and Mars logistics in the next decade is the politicians. No, I'm just kidding.
Yeah, budget.
Budget, yeah. The budget deciders.
Budget deciders. Biggest risk.
But we're just talking the next decade.
Next decade.
Yeah. Or a major risk.
I think just coming up with solutions to these hard problems. All this summit was incredible, and there's a lot of things that are happening, and I think it's we got to work together as a team. But there are a lot of challenges that go on, so it's really endless to the challenges we have. But to name one thing, I just can't.
You just did, man. You just stated education and training.
Yeah, it takes a village, and these folks in here and the folks on here on the stage are part of the team that's going to make it happen. We got to all communicate with each other. There are a lot of challenges out there. from the vehicles to the consumables to just how to do things, how to close these technology gaps that a gentleman talked about earlier today. We just got to get innovative, think outside the box, like Vanessa said, but there are a lot of challenges out there. So it's hard to just say one. There's just 1,000 challenges.
Yeah.
So, apologize for saying this, because landing on the moon is risky. I think that's recognized. But the types of systems that Blue is developing and that SpaceX are developing, because you said 20 to 30 tons. So just imagine that for a little bit. That we're talking about CLPS landers now that are in themselves very difficult in succeeding on landing tens of kilogram payloads. And we have companies now developing things which are, 20 to 30 tons at a time. And just think of how that would change things, that if within the next 10 years, if that becomes routine, that's a steady thing you can depend on, that it's like, oh, the semi truck is pulling up with 20 to 30 tons of stuff to be delivered to the moon. Then all of a sudden, all the stuff on the surface of the moon becomes possible. Because if you can't get the mass to the moon, all the stuff we're dreaming about, all the stuff we're trying to plan just doesn't occur. So to me, that's by necessity the biggest risk is realizing the routine, large landed mass capability that companies are developing. And I know that Blue will succeed in doing that. So.
Yeah. Yes, sir.
I'll just say the complexity of the CONOPS. I think that there hasn't been a good reliability assessment on the CONOPS that may be the biggest risk to.
Define CONOPS.
From processing on the ground to launch to refueling in space, the complexity of refueling in space, to we've seen the challenges of just landing on the moon, and again, to the point, landing large masses on the moon. So that entire CONOPS scenario is challenging. It's incredibly risky situation.
I would say not a risk, but an opportunity to adjudicate risks is, and I kind of said this earlier, we're living in this kind of amazing time where there's more, I'm just speaking, for US domestic capabilities, there's more capability than ever. A lot of it was self-funded, by the market or by, individuals or whatever. And I think the best thing is we need to maximize leverage of everything available right now to solve a lot of these problems. So, from suborbital to moon, Mars, beyond, there's these capabilities in industry and, in co-development with NASA that are going to change everything. But we should be maximizing them to the greatest extent possible every single day. Like, I don't want any rocket to go not full, or any lander to go not full, or any suborbital mission to not be flying, because we could be doing so much now. We have to find ways, I think, to do as much as possible to maximize this golden age of. There's a million vehicles, right? There's OTVs, there's all these amazing things that exist now in this point in time. And I just think if we can find the best way to maximize them, to do tech demos, de-risk, do maybe smaller or different science, that would be a great thing we could do to de-risk a lot of the concerns.
Thank you. Yes, that, and I think there's some public perception issues that need to be addressed as well. All right, one last one. We have 7 minutes left. Let's play Interplanetary SimCity. If each of you were responsible for one core element of a permanent moon base, what would you own and why?
Power.
Power, because then you'd have power?
Yeah, that's right. Bulk power.
Well, I would imagine, do you think that it would be centralized or would it be distributed like solar?
I think it's probably going to be a mix. Yeah. I mean, we're going to have to demonstrate nuclear propulsion in space, do test demos on the moon. And so that's really where, personally, my passion is, where I'd like to see funding be put towards. I think there's some things coming out of the White House last week or the week before about nuclear propulsion or nuclear energy in general. So to me, I think that's an area I'd personally like to control.
Power. It's interesting because when I was at NASA headquarters, I was interested in My graduate students and we developed a propulsion technology based on magnetic reconnection. But it turned out that the type of power that we would need does not exist, and for an in-space application. But continue. Yes. What would you own and why?
I'd say maybe like a carrier or lander. It'd be just kind of interesting to see how to outfit it robotically and all the cargo stowage, and I think that would be.
So would that be for the logistical landers?
Yeah, logistical landers. Yes.
Wonderful, wonderful. Yeah. Why did you say why?
I'm sorry.
Why?
I just think it'd be a great challenge to overcome.
A man who loves a challenge.
That's right. That's right.
Love that. Yes.
So if he's going to own the charging station, I'll own the foodstuffs, the agriculture system.
There you go.
How do you envision
food stores. So with all this landed mass going, you're going to have a lot of volumes that are carrying consumptions, things that are consumed and they're going to be empty. So just like people nowadays are building homes out of containers, you can imagine a world in which whatever we pick as the containers for stuff going on the moon are reused or repurposed, and repurposing them as agriculture systems, agriculture facilities. So we can start, because you can find water on the moon, you can find other things on the moon, you find other things on Mars, stuff like that. But food, that's what I'd like to own.
All this transport, it just made me realize something, that, you have to rocket things up to the moon, but you can just drop them back down to Earth. Thank you. Some people are like, this dude's an idiot. Jackie?
Well, so many good ones are already taken, I assume I can't repeat.
No, you can't repeat. You got to get your own.
Okay. Well, I'm going to envision in this future Sim City, what's Sims without people? Sims are people, aren't they? The Sim itself is a people. Yeah. So I'm going to assume there's lots of people. So I'm going to say this is not on behalf of Blue Origin. I want to own like the Walmarts. I'm trying, because if there's people somewhere, you got to have all the things that people need. So I'm trying to like land a Walmart or something.
Well, wouldn't there be like robotic delivery to your front door?
Yeah, exactly. See, right?
Yeah.
It's like, need my CVS,
You could end up being the richest person on the moon.
Well, that's what we're going for now.
That's what we're going for. Wow. We have 3 minutes left. So any last words, or the thing I mentioned about the public perception, like one thing I get about space activity is that, we could be solving problems here on Earth. What is your answer to those sort of sentiments? Because this, we in the room appreciate the big picture of where humanity is going, what's good for our national interests, because we're deep, we're involved, we're intimate with it, right? But I think the average person who doesn't have that experience can easily, just like when I watch a science television show, we tell the results, but we don't tell how we got them. I completely understand how people could say, crap, that's not real, right? But why the value of what we're doing? Very quickly.
I think if I go back to my NASA days of how many dollars spent, but looking historically from what happened through the Apollo era, and then the genesis of semiconductor technology and the revolution in computers were spawned by that investment. Look at it just in my personal experience with the NASA COTS program, where it was taxpayer $500 million that, quite frankly, developed 2 new launch systems and multiple launch pads, but then changed the way we access space now.
Wow.
And so
that actually sounds kind of cheap.
Right.
Yeah.
Which people say, where does Starlink come from? Well, Starlink would not have happened if NASA didn't kick in the $500 or $300 million and have a CRS contract.
Right.
So just some points there.
So I would say there are very few problems that are so unique that they only have application in one area. So if you talk about sending crew to Mars, you're going to need to do remote medicine. Well, there's a huge need for that on Earth, and so so just like a lot of things came out of Apollo, a lot of things have come out of shuttle, a lot of things come out of the space program that have benefited, life on Earth. That used to be one of the taglines, for the station was it's about life on Earth. That the way I would try to sell it is to say the investments here will pay back in raising the quality of life of people on Earth and solving problems that we have here. Whether it's like I talked about agriculture, being able to grow things more efficiently would be a good thing to do on Earth.
Yeah. For the record, I got chickens in my backyard. I don't know about anyone else. And I've had 3 harvests of my mustard greens already this season. Yeah, I just did this for the first time this year. So, any other thoughts?
I agree 100%. I think the advancements in technology and medicine for the better humanity is really what it's all about, and that's what we need to communicate and educate to the folks out there.
I'll give you the last word, Jackie.
I agree with what everyone said, and for the sake of not copying too much, I guess I would say I think just the inspiration and the new ideas that are going to come from all of this. Like one cool thing about New Shepard is just in flying more people to space that traditionally and historically would have never had the opportunity to go.
Right.
A big part of what we've been doing on New Shepard unintentionally is there's been a push of many people who have been the first person from their country to ever go to space.
Wow.
First of nation passengers and astronauts. And that in and of itself and that inspiration I think is just so huge. And again, coming up with the next idea, which is the next internet, the next whatever, it's going to be. So I think that excitement and the curiosity and stoking that through space is absolutely a worthwhile investment from every corner. So.
I would like to thank all of you. You guys are brilliant and love the work that you've done. Let's thank our panelists. And with that, our panel has concluded.
So quick question, how is today going? Can I get a show of hands from folks who, if I handed you a ticket, would head for Mars tomorrow? Fortunately, the lights are super bright, so I can't actually count. Excellent, hands down. How many people are maybe yes for heading to Mars, but you've got some questions? Okay? And now how many of you are, I think I can best help the future by sticking around here on Earth? Do we have any of those? A couple, okay. It's always good for me to get a pulse check on our audience because for me, the thing that is the most valuable about the Explore Mars community is the fact that we are a thoughtful, peer-reviewed community of folks with diverse perspectives and perhaps most importantly, diverse questions. I know that as I've been listening to the talks today, the panels, the presentations, I am coming up with more questions than I've ever had before, not only about the how that we're going to do this, sending humanity beyond the boundaries of Earth, but also I think the most important question is the why. Why are we doing this? And in various panels today, you heard different ways that people answer that question of why. Why do we want to send humans back to the moon? Why do we send people to Mars? Why do we spend our money? Why do we spend our time? Why do we spend our creativity and our innovative spirit? Why are we so excited to get young people to join us on this journey? And I think each of us comes to this question from a different background. So I mentioned when I was up here earlier today that I serve as the Innovation Partnerships Vice President here at Explore Mars. So for me, my not so secret why as to why I care so much about seeing humans on Mars within the next decade, hopefully, is because that I believe that innovating for space is innovating for Earth. I don't believe that we have to choose between innovating for Earth and solving Earth's problems and solving space problems. To me, they're the same set of problems. They're just more extreme in space. But it also means that we have the opportunity to think differently, to use different perspectives, to say, you know, what got us to today is not going to get us to tomorrow, and it's certainly not what's going to get us to Mars. That's my personal perspective, and I've been delighted today to hear several of our panelists talk about how innovating for space makes life on Earth better starting today. And I'm really delighted to share that in tomorrow's programming, you'll be hearing more about that as we dig into some of these big problems, how we're going to solve them for space while delivering value on Earth starting today. And when I talk about value, I'm not just talking about prosperity, which of course I believe in very strongly, but I'm talking about peace and people and our planet. All of these things to me are a future of space. Now, I spend a lot of time thinking about the future in my role, and one thing that I think is an important mindset for us all to remember is that there isn't one future. There's no such thing as the future. Instead, what I'd like to encourage us to think about are a variety of possible futures that, based on where we stand today, some are more likely and some are less likely. And the farther out we go in time, the more uncertain we become about which of those futures we're going to access. But what I'm really most excited about in our Explore Mars community is how many people and organizations, not just in the United States, but around the world, are dedicated to making choices today that make those possible futures, peaceful futures, more likely, and make it less likely that we'll end up in some of those scary Black Mirror futures. And that's why I think the moment that we stand in today is so important, right? We're coming into the Artemis years. We're going to be coming to Mars years very, very soon, which means that the actions that we take as individuals and as organizations and as a whole community, they genuinely matter. Today matters. The future is not something that happens to us. It's something that we come together, we build together. And that's why one of the things I love best about this summit is seeing all of you talking with each other outside, upstairs, in the hallways to figure out how we're going to do this together. And tomorrow you'll see some more opportunities where you can raise your hand and say, I have an offer to make, or I have an opportunity to make. Let's build this together. So I want to encourage all of you to ask yourself, what's your offer for tomorrow? What's your opportunity for tomorrow? So I really think that, again, this moment is really important. I want to point out to you that if you are enjoying what you're seeing here today at the summit, if you're online, same deal, please consider supporting the Explore Mars community now. If you look in the back of the room and upstairs as well, you'll see some flyers with some QR codes where we've tried to make it really easy for you to share your support with us. But think for a minute about why this is so important. I'm going to make a vast understatement here. These are uncertain times. Is anybody else feeling that? And all of the traditional ways that we had of doing things, innovating for space, bringing the communities together, seeding new research, starting new collaborations, we need to be opening up alternative pathways. That is very, very critical. And we at Explore Mars view ourselves as one of those catalytic pathways that helps open up these alternate pathways. So please consider joining us on that mission with your money, with your time, with your ideas, with your connections, with your networks. We are really excited to work with you to open up all of these alternative pathways to a peaceful and prosperous future of space that starts today. So like I said, keep your eyes open for those flyers, and you'll be hearing more from our community as well about ways that you can plug in and engage. I also want to remind you that this evening we have our whiskey tasting reception that's being held upstairs starting at 5:45. I am very aware that I am what is standing between you and whiskey. So I'm going to just point out two more things before I let you go off into the world to rest and recharge for tonight and be excited to be back here tomorrow morning bright and early. And those were two things that I heard during today's sessions that really, really stuck with me. The first was one from our China panel, where Dr. Scott Pace said, "The rules are made by those who show up." That's us. That's today. That's the partnerships that we seek, that's the allies that we bring to the table, and that's those opportunities and offers that we start making today. We are the ones who are going to have the influence on which possible futures we move to. Those who show up are the ones who make the rules and make the future. And the second one that I wanted to point out was something that Bob Zubran said. He said, we are not going to Mars out of despair. We are going to Mars out of hope. Did anyone else catch that? I thought that was really spectacular. And for me, that's really what this vision of a future for humanity is. It's not about fear that we've wrecked our planet. It's not about wondering how I can make the most money by mining tritium or whatever it is. It's none of those things. For me, it's about the opportunity that we have as humans to come together to be our most creative selves, our most innovative selves, our biggest thinking selves, and to do it together, and to figure out the next step in humanity's journey where we're the best people we can be. We haven't always done a great job of getting that right here at home. But now what I see is in the coming decades a chance to write a new chapter. And that's why I am so excited to be a part of this community and this organization. We're the ones who are going to make that happen. We innovate for Mars, not out of despair. We're innovating out of hope. And the hope that by building that future for off-Earth, we might make life better on Earth, starting today. Does that sound like something that lands with you all? Do you feel that as well? Is that why you're here? Yes. So I am going to thank you again for being with us today, our online friends. Thank you so much for joining us all around the world. We look forward to seeing you here tomorrow. Come full of energy, first thing in the morning. We'll be back together. Lots of new perspectives and questions to wrestle with, and lots of new opportunities to build the future together. Thank you all very much. Have a lovely evening.
Hope, not despair. Boy, I caught that too when Bob Zubran made his wonderful statement to us, his presentation earlier today. That's it. That's the end of day one, save for one more quick conversation with the moderator that you just saw on stage. I'm Matt Kaplan, Senior Communications Advisor for the Planetary Society. And over many years, the moderator, host of this live stream from originally H2M, now H2M2, the Humans to the Moon and Mars Summit. Hakeem Oluseyi, I got it right, didn't I?
Yes, sir, you did.
Okay.
Yes, sir.
Well, I had to practice, as you know, because you were my guest not long ago on the Planetary Society on-air, online book club. And so I want to mention your book in a moment, but great panel.
Yeah, that was amazing. I mean, how often do you get to look at the nitty-gritty details of the logistics of supporting such a complex and aspirational endeavor as humans having a permanent presence on the moon and Mars, right? They've really put the thought in.
I'm embarrassed to say it never really hit home that they're going to be forklift operators moving pallets full of stuff around on the moon and Mars. It might be robots doing it, but somebody's going to be doing it.
Yeah, someone has to do it, but it's not just when they're on the moon and Mars. When they're in transit, what if something goes wrong and you have to do a rescue operation? Here on Earth, we move by going from here to there. Orbital mechanics does not work that way. Right? You can't, I'm going to go from here to there. You can't have a gas station just sitting there waiting for you to pull up, right? So these are very complex and unique challenges that people have to put a lot of thought in when they're not getting anything, there's no fruit, right? This is the basic fundamental research. This is the good stuff. Yeah.
And if it doesn't happen, we're not going. We're not going to make a success of this.
It's necessary to support the missions, right? Even warfare is based on logistics, right? If without the logistics, you're losing fast. And it's the exact same way with this particular new direction that we're taking to have this sustained presence far beyond Earth orbit.
I think I'm going to screw this up, but I think Napoleon maybe, is the one who said armies move on their stomachs. They got to get food out there or they're not going to be fighting.
That's right. You got to get food. You got to get fuel. You got to have spare parts, and you're not growing your own food on the moon initially anyway, right? So how are you going to sustain those people when they're there? Because the other issue that you have is how much mass can you take on each particular mission? You can't just take an arbitrary amount of mass. You don't have big ocean liners full of containers going from the surface of Earth to the moon, right? So it's a very different type of challenge. It's a unique one.
So this was maybe less Hakeem the astrophysicist PhD and more Hakeem the science communicator, maybe a touch of the engineer Hakeem as well, right? Yeah, and so that's a role that you also fulfill across your life nowadays.
Oh, yeah. So I was an engineer officially, right, in Silicon Valley. One of the things I did, I worked in manufacturing and lean manufacturing. How do you get things done optimally? Designing systems engineering was something I was able to participate in, as well as designing various space missions, right? So when you think of a astrophysicist, some people think you're just sitting there looking through a telescope all day. But, there are so many roles you can play. And I went the role of hardware, right? I like to build things and make things because I grew up doing that, right, on the farm. Yeah.
And much of this is documented in your absolutely amazing book. There is no hint in what a lot of people saw up here today of what's in that memoir that you've written, A Quantum Life.
Oh, they're gonna know because later after I'm robbing everybody tonight, so they're gonna find out the old me. No, I'm just kidding. But yeah,
it's an amazing story.
It's an amazing story. It's a story of transformation. And the thing that really surprised me post writing the book is how many people have saw themselves in my own story. It's not unusual for me to be at something like this, and someone comes up to me and they'll say, I've never told anyone this. But when I was in my early 20s, right? Because, our lives, when you look at, when I speak to kids, sometimes I tell them, your parents and your teachers are the biggest hypocrites in the world. We were just like you, right? We were just like you. We made the same mistakes. But that doesn't mean that's the end of your story or that is your story. You're not defined by that. And so, I had the gangster and the nerd. The nerd won out.
Thank goodness. Thank goodness.
You're telling me, right?
It was kind of up in the air for a while there.
It was up in the air, man. But, the other thing about it is that life was pretty damn dangerous. And I kept finding myself in mortal danger. And so,
we're lucky to have you here today. We're lucky to have you at all.
Oh, man, thank you so much. I appreciate that. That's because you don't spend enough time with me. After a while, you'd be like, Hakeem, can you shut up about the deep thoughts?
I mean, just as a matter of survival. This is kind of a silly question, but I wonder, as you were, surviving in Compton, living on that farm, moving around, and what was it, your mom's car?
Oh, yeah, the Ford Maverick.
The Maverick, of course. Did you ever envision yourself doing something like this?
Oh, heck no. No way. Man, when I was in my mid-20s, I couldn't envision this, right? And here I am. And the reason why is because, if nothing else, I'm open and open-minded. So even though I'm putting myself in situations where I don't feel comfortable and where I'm the least educated person in the room, right, I knew that I wanted that life and I wanted that sort of those abilities and that knowledge. So I had examples. I saw it and I became it. Art Walker, Craig DeForest, Charles Kankerborg, Ray O'Neill, Max Allen.
Mentors, not just examples.
These were my cohort. They were a little older than me. They were my mentors. And when I saw them and how their lives went, and the same thing happened. I'm going to tell you a story about my niece. I have a niece who I was encouraging to go to college when she was in Makita Monique Morgan, when she was a sophomore. She wasn't feeling it. She graduates, gets a job at the chicken plant, Sanderson Farms in Ellisville. After 3 years, she announces to me that she's going to go to college. I go home for Christmas, another family comes over, and they tell the story of how they're trying to get their younger family member to go to college, but that family member isn't interested. So I said to them, get them a job at the chicken plant. The chicken plant got Monique to go to college, and Monique responded, that's not why I'm going. And I go, really? Why are you going? And she said, you. I see your life, and that's what I want. And now she has a master's degree, right? She's doing wonderful in life. And that's it. If you see it, you can be it.
Very powerful message, and hopefully one that a lot of people here are helping to communicate to young people.
Well, you know what we're doing here, man, and this is the thing that really struck me when I came into this world of research. We're doing the impossible, right? You join one of these teams, and you have this impossible goal, but then you realize that the technology to complete that impossible goal does not exist. So what do? You invent the technology. But then you have to calibrate that new technology you invented, but that technology doesn't exist, so you invent that. And you learn a way of thinking and a way of being that these impossible problems, you just go at them one at a time, and you make your way to that mountaintop, and the next thing you know, you're on Mars.
All right, so to close out here, I have a piece of advice for you. Try and show a little more passion when you talk.
All right. I'll try to have a cup of coffee or something.
There'll be an explosion. I don't want to be around when that.
Right.
Thank you so much.
You're such a gracious, wonderful host, man. I really appreciate you. Thank you so much.
That's very kind. Thank you. And it's mutual. Okay.
Hakuna Matata.
Yeah, that's not bad. Hakeem Oluseyi, astrophysicist, engineer, science communicator, and the author of A Quantum Life. You want to read an amazing book about a transformation. That's the book. That's what everybody thought in our book club at the Planetary Society, too. That's it. We're done. We're going to go up to that reception that you heard about. I'm sorry you can't all join us, but maybe next year. And we will see you tomorrow at 8:30 a.m. Eastern Daylight Time when we pick up with another full day here at H2M2, the Humans to the Moon and Mars Summit, coming to you from Washington, D.C., George Washington University. Thanks, everybody. I'm Matt Kaplan from the Planetary Society. Have a great evening, and we'll see you tomorrow, I hope.
Yay.